the thing is basically when you're starting with Cassandra, first thing I'll tell you, if you have relational database experience, even if you work with MySQL or Oracle, it's just, it's purely RDBMS side of it. So first thing I would say, open up your mind and forget about everything you know about RDBMS or databases coming into these sessions, because Cassandra is not RDBMS. And if we don't make up that mind saying, I have to forget everything I know, somebody says a table, forget that you know what is table. So when you come to Cassandra, you start fresh and you just imagine that you don't know anything about database. That will be the best way to learn Cassandra, because it's completely different and very new. Everything you learned about Oracle, they told you, you're not supposed to duplicate data. You're supposed to normalize as much as possible. All those concepts are wrong in Cassandra. I mean, let's say somebody tells you, oh, I'm not getting performance, go create an index. That is completely wrong on Cassandra. Do not create indexes because you need performance. So have an open mind, and you definitely need to learn more than Cassandra. Apache Spark is the next thing to learn while learning this. Learning Java and Python is good. You don't have to write code on your own. You are going to stay with administration, but you definitely need to know what your developers are doing. Otherwise, they can create a lot of problems for you on your database. First of all, we will talk about what was the issues or challenges 2010 time when all these RDBMSs were already there. Why do you need another database, right? So first thing we talk about is, okay, we have this server, we have some CPU, some memory, and then basically we want to increase the capacity of the server. So open up your mind, because we are talking about 2005. I'm not talking about current. So in those days, we used to have single servers, databases were running on single servers, and things were okay, they're performing fine. What we wanted was to have more memory, more CPU. So the only way we can increase the capacity of a server is by just adding more CPUs and more memory. And that was called vertical scaling. Basically, you take a server, if you buy a basic server, you can maybe increase CPUs, add more RAM. You have 16 GB RAM, you make it 32 GB or 64 GB. And the advantage was you don't have to change anything in your server, like the software wise. You just increase the hardware in there and restart the server. It will start looking at the new amount of memory. And then you go into, like, if you're running Oracle on it, you just modify the memory parameters. So you restart Oracle, so it will start with more memory now. So same server can run larger databases, or you can have multiple processes running. Like, if you look at it as, let's say Java code, you can run multi-threaded Java code, or more threads, or more connections. So the disadvantage is every server which Dell makes or HP makes, they have limitations. So beyond certain time, certain size, it doesn't support, let's say, for example, unlimited memory, right? I'm talking about RAM. So you can only increase up to a certain limit. So that was the bigger disadvantage with this. And then you also know that, let's say you hit 64 gig, like making it 128 gig, your price goes up, and price goes really very high suddenly. So that is the issue with the vertical scaling. So then, people started thinking, okay, what can we do to solve this issue? One is you come up with a concept called, okay, let's take this cheap commodity servers and have multiple of them, like 2 servers, 4 servers, or 10 servers. and make them run like a cluster. So cluster is a terminology where, you know, more than one server is involved, and usually each server is called a node in the cluster. And people started saying, okay, we'll take these 10 nodes and make them run like a cluster. Now that is called horizontal scaling. Now, why it is called horizontal scaling is, if we need to increase the capacity, now together this whole thing, I'm calling it as a system. So if you want to increase the capacity of the system, you just add more servers, more of these commodity servers, which you buy for a cheaper cost. You don't buy, like, you know, very beefy, powerful machines. You buy low-end machines, but you add those machines into the existing cluster. So you have more capacity now. And you will get more memory because you're now taking whatever memory is on the new server, adding it to the existing cluster. And those 10 servers or 4 servers, whatever you have, are acting as if it is a single system. Now, these are based on low cost commodity servers, so you're not paying too much. And they're all connected via gigabit Ethernets or InfiniBands, high performance interconnects, basically high performance network cards and all that. Now, that was the birth for distributed computers, distributed computing, distributed databases, distributed systems. What happened is, now they say, okay, it's not located in one server. Instead, it is distributed across 4 servers or 10 servers. So the cluster is basically a concept based on distributed computing or distributed databases. Now, the advantage is you say, for example, your business is going to see a spike for, like, say, Thanksgiving. So what you do is you add another 5 servers to the existing cluster. Cluster could be only 4 servers. Now you're adding 5 more servers. Your cluster became 9 servers now, 9 nodes. So you basically increase the capacity of the cluster in terms of CPUs, processing power, RAM, everything. And when the Thanksgiving sale is done, like a month later, you remove those extra servers you added earlier, and those are gone now. So this is how horizontal scaling works, or the concept, right? And basically they said, okay, you add more servers when you need, when you don't need, you remove them. The disadvantage here is the number of servers you have to manage. So you need more staff to manage more number of servers. Even though they're small servers, you need people to manage them. So that was the disadvantage with the horizontal scaling. But one very good thing happened with this is the birth of distributed databases and distributed computing. Okay. So right now we are still talking about before cloud era, where we knew we had access to all these physical servers. We can go there and touch them. We can push the restart buttons and all that. But what this particular era brought to us, this was around 2008 time, that was the birth of all these distributed databases. So forget about distributed computing, we'll focus on the database area. So distributed databases started. So that's when a new terminology came. You know, RDBMS existed for 40 years. And we started getting introduced to something called NoSQL databases. Very early in 2009 or so, with Web 2.0 standards, these NoSQL databases started surfacing. They started showing up, and people said, okay, NoSQL, what does that mean? We all know structured query language. What does NoSQL mean? Okay. So basically NoSQL has many meanings. One is it's non-SQL, meaning you don't write structured query language to query your data. Not using structured query language. Then they said, you know, after some time, yeah, we need some kind of query language, but it is not a SQL query language, structured query language. So they said not only SQL, meaning you can use other programming languages to query your data. And one other thing which is very important here to note, it's a no relational database. There is no relations in this NoSQL databases. So a generic concept saying, okay, we'll not have relations within the database, like, parent-child relation tables and whatever we learned with all the RDBMS. There was another terminology here called flexible schema or no schema being termed out. So what was happening is basically all these Oracle kind of systems, when they were using them, you create a table, you create 4 columns in the table, and then basically what happens is, oh, you have to add a column, you have to modify a column, you have to go through a process. Basically, you work with your app team, design the table, come to the administrator side, and then you say, hey, can you create that column or modify the column, right? So developers started seeing that RDBMS is, too restrictive. It doesn't allow me to do what I want to do. And they want it in a flash time, right? They want to do it quick. So there is this new terminology called flexible or no schema kind of concept, which started showing up in the NoSQL databases. Now, the NoSQL word itself is a very large word. So as we go, we'll see where Cassandra fits. Now, what are the advantages of NoSQL? They said, okay, it's a simpler design. It's not very complicated, easy to understand, and easy to develop on top of these databases. And all of these databases support horizontal scaling. And that's what we needed in 2010 time. We want the horizontal scaling. Vertical scaling was very expensive. Now, because they already know all the issues in the RDBMS, they said, okay, we need to make it fast and highly available. This thing should be by default available within the NoSQL databases. So that was the reason this NoSQL databases started showing up in the market. Okay, so that gives you a brief history of why we came to NoSQL databases in 2008, 2007, 2009 time. So RDBMS is just RDBMS. Okay, it's a database. It has tables and columns. They relate to each other. NoSQL databases were created by a bunch of developers who can write code, and they can use any software they have available. And they all wanted to create different types of databases. So there is no standard, but they said, okay, let's create database for our own use case. And overall, now after all these years, we can just categorize them as these 4 types of databases. Now, again, we are only talking about NoSQL databases. So for example, they said, okay, document stores. So what you want to do with the document store is, we want to store, there are several documents which were already introduced with the Web 2.0. So like XML is one of them, JSON and binary JSON. Actually, if you look at MongoDB, so what I did here is there are a couple of products as an example. You can see MongoDB is what used to store JSON documents in binary format. So that is called BSON. Okay, so just for your, let me put it here like this: stores BSON docs. Okay, so that's that will give you some idea about what it stores. BSON is nothing but binary JSON. Then there is this Apache Couchbase, CouchDB, or things like that. There is another document type called YAML, but generally here I'm showing you an example of these are the different products which will store documents, the whole XML file or a JSON file as a record within the database, and you're going to access the data based on those documents. You'll say, give me this document. So Anil will have one document for himself. Vinod will have one document as a user document, let's say. So when Vinod logs in, we'll just pull that Vinod.json, and that will give us everything about Vinod, like what is his address, what is the phone number, username, password, stuff like that. Then the second category you can see here. So these are called key value stores. And key value stores is basically a very simple concept of a key and a value. So key is username, password is the value. So key is username, password is the value, and they're stored together in as a pair. So what is the key, what is the value? That's all. So this looks very simple concept wise, but what people did with this is they created databases like Redis or Memcached. These are very high performing databases. What they do is simple. Your row looks like a key value, and you come and say, okay, for this user, what is the key? Sorry, for this user, what is the password? Let's say, right? And it is extremely fast because it's all running on a distributed system, and the rows are very small. The data it handles is very small, but huge amounts of data, meaning multiple millions of rows. Now, RDBMS can do this, but RDBMS has its own limitations about, like, let's say, for example, if you want to build a 4-node rack, Oracle rack, it is very expensive. Compared to any of these NoSQL databases, these are peanuts and they're free of cost. You don't pay any fee for this. Okay. Then there is another type of databases which came up is graph databases. So there is this Neo4j is a very popular database. Even today, there are a lot of people using it. There are lots of new versions of it. And there are some more examples here like OrientDB and stuff. So you remember long back, there was something like network model for the database, even before RDBMS. So these graph databases store social relationships or, public network transport links or roadmaps, let's say network topologies, those kind of use cases, they store this in the graph database, and you can navigate to each node within the graph, and you can expand that particular value. These are very specific kind. As you see, one of them stores documents, the other one stores key value pairs. We are talking about the graph databases which store like network information or information which can be explored as if it is a graph. Then our favorite, so basically we started seeing this wide column or column family stores. Okay, Cassandra falls into this category. Cassandra is a wide column or column family store. There is HBase because Hadoop was also developing this stuff, and you can see any big data product you touch, you will end up with Hadoop somehow. Hadoop is the biggest in the whole big data world. There are big companies like HP who invested a lot of money and they made products like Vertica. Vertica is very expensive. So please, when you look at this this list of databases, do not think all of these are open and free. Some of them are very commercial, like Vertica is very expensive compared to all these other databases. Now, probably Vertica is more expensive than Oracle itself. Okay. We will talk about Cassandra, but we have to understand that there are 4 types of databases. And these are the 4 types. We discussed about each of them a little bit, just to understand what they are, what they look like. Okay. Now Cassandra falls in the wide column, or I generally call them as row column store. Now, same time to 2009 to 2015, let's say, for example, some of the databases still exist, some of them gone, some of them lived for 2 years and gone. So NoSQL databases, there is a huge amount of NoSQL databases. Some of the names you can read here, some of them relate to Hadoop. Like if you look at this one, by default, you will see Hadoop here. Yeah. So see the Hadoop here, Hadoop HBase. There are a couple of other places you'll see Hadoop. What is more important on this slide is a big table. And also, if there is Dynamo, let me see if it is there. Dynamite, because this is the Dynamo. So those are more important for our discussion. So you see Neo4j, Memcached, this I mentioned all this before, like in the previous slide, React. Okay. So there are a bunch of databases. There are more than 225 NoSQL databases. There is a reference website you can read and you can find out what each database is good about and what they're good with. And then Flink is also very important in the industry. And Flink is still existing. And you can see some of these big companies wanted to get into this field. So they did create their own databases, like Redis is one more very popular one. So some of them I highlighted, but what we'll do, we'll talk about two things here called, let's focus with Cassandra, and we'll also look at one more thing called Scylla. So people call it Scylla, Scylla. Apache Cassandra is developed in Java. And it's one of the very powerful, distributed databases. I personally fell in love with it, so I would brag about saying, okay, this is one of the best, but there might be others. So there is, this Scylla is developed in C++, but it is exactly Cassandra, nothing different. It's exactly Cassandra. Apache Cassandra is written in Java, and Scylla is written in C++. So you can actually take your existing data in Cassandra and put it on Scylla and it will work. Now, what is the advantage with Scylla is people claim that it is faster because it is running on C++. It's a natively compiled code, better than Java. For use cases like large companies and large usage, if you look at, Apache Cassandra is more popular. Okay. So it is at this point of time, like we are on the slide number 7, it is good to know that Apache Cassandra and Scylla both are same. And as you go, you will decide on your own which one you would like to use. In general, in industry, Cassandra is more popular than Scylla. So it's because of the support and usage, I guess. Okay.
Why it is named as Apache Cassandra?
Oh yeah. Okay, so for that we'll take a side discussion here. So Apache org, right? As you know, this was one of the foundations, and you can see it is 20 years old. So somewhere in 2000 or 2001, they established this, and they said this is community-led development. Basically, any developer who knows how to write some code, they can come and contribute. And this is not with any big company like Oracle or commercially not sold. And they said any code you write is available for everybody else to see. They can take the code and modify it, fix the bugs or enhance it. And the only thing they expect is basically people who are changing it, contributing it. So just give that code back to the community. So it is all based on the people have their own personal time. Nobody works at Apache in those days. Now actually Apache has grown to a company where they hire people and they manage these projects. But they're still not selling any software. What they do is they collect all the software from different people, put them, organize them, and build the open source softwares. The way Apache works is there is one blanket license. You can download all these projects, any of these projects. They will not ask you for money. You can put it in development, non-prod, production. You make money out of that project. Nobody cares. And they will give you the source code if you want to look at the source code. And if you look at the products, like just look at Apache project list. See, this is a very large list. And there are very popular, very new softwares also, like Tinkerpop. And there are servers like HTTP server, Tomcat server, Flink, which I talked about earlier. I said Flink is important, so you'll learn as you go. And Cassandra is also sitting in this list. So any of these projects, if you see here, they started with Apache, apache.org. So Cassandra was not invented by Apache, but that's where it lives now, and Apache manages them. So that's why we call it as Apache Cassandra. As we go, I will talk about another company called DataStax. I will give you introduction, and I'll tell you why that is also important. So you must have heard this name, Sambari, Zookeeper, you know. So all these projects are here. Zeppelin is one more thing. You see Zookeeper I just mentioned. So there are many projects which are all free, open source, and they don't ask you for a single pie of money. You just put it in your production and run them. If you have too much knowledge, then you can also modify the code, and you know, you can make your own product out of it. Like Kafka is one more popular one. Iceberg, I don't know if you heard about it. So there are many projects, many different kinds. DruidDB is one more important one. So Apache is very big. When you get time, just go through this list and read some of them. Like in Apache, Spark is here. I've been talking about Spark since the beginning of this session. So Apache Spark also lives under the same umbrella. Okay, so we'll come back. We will be dealing with Apache a lot.
So is there any relationship between big data and NoSQL databases?
Well, big data is a concept. Like Hadoop is a product using big data concept. So Cassandra is a product using big data concept. Cassandra is considered to be big data database because it handles massive amounts of data. And it follows all the rules for the big data. So you can consider Cassandra falls under a big data database. So all of us started with RDBMS, EF code. He wrote a book and he said, okay, these are the rules if you want to make a good RDBMS database. So he said, oh, let's read all these 12 rules, right? He talks about, okay, take your data and normalize it. First normal form, second normal form, third normal form, denormalize, fourth normal form. So obviously when NoSQL databases started, there should be a theorem behind why we need to choose what. So we introduced a CAP theorem. Now, CAP theorem was initially first appeared in 1998, and the name associated with this theorem is his name is Eric Brewer, and he created this theory called CAP theorem. Okay, so there are three things we have to think of when you want to design a NoSQL database system. So he said, okay, we need consistency. Consistency is in your database system, if some data changes, all throughout the database, you should see that consistent view of the data. Meaning, if you have two nodes, the first node should see the same data, and the second node also should see the exact same data. If they don't see it, there is no consistency for your data. It's a consistent view of the data. Okay, that is the first piece of CAP theorem. Then he said, okay, there is one more thing called, let's look at availability. Okay, so you have a large system, let's say 10 servers are there. And if your systems are down, let's say if you talk about Oracle, right? If you have 4 node Oracle, 2 of them are down for some reason, they crashed, they're in maintenance. You know, DBS actually cannot sleep with that. They have to bring those 2 nodes up, and then only they can sleep. At least that's how I work at my work. So they say, oh, no, you have 4 nodes, but system is at 50% capacity. So you bring up and make sure all the nodes are always up, right? In the NoSQL world, they said, you know, availability is something you expect. Okay, so there are 100 servers. Some of them, 10% of them will be always down. So we don't care. But if the system is available or not, that's what defines the availability. Can my application continue without having that one node up? So that is availability. Then there is something called partition tolerance. So what we'll do is we'll understand these three terms and then understand the combinations. What does partition tolerance mean is, now we have, let's say, 10 servers. We'll take one large million row table and we'll split it into, like, say, 1,000 rows here, 1,000 rows there, and then we continue to distribute it across the 10 nodes. Okay. Now, each of those nodes, you can see they're partitioned. So the whole system has become 10 pieces. So that's your distributed system now, right? Let's say one server is down. You can think of it as partition is down. So one partition is down, can your application continue? Meaning Cassandra will not fall down and say, hey, one node is down, I cannot do anything, right? Or Cassandra will continue to run with 9 nodes. I'm just taking Cassandra as an example, okay? So now your 9th node also goes down. 8th node also goes down. 7th node also goes down, right? As long as you can have a quorum of nodes which say, okay, I'm here and I can give you your data, system will be up and running. Meaning, is your system partition tolerant? That is what partitioning means. Partition tolerancy means, okay? So basically what we are saying is consistency is all nodes see the same data at the same time. Meaning if somebody commits, that's what we see across all nodes in the cluster. Availability is the guarantee that every request, whether the system is up or down, or it failed or not, every request which comes in gets a response. Whether it is successful or not, that's a different story. But as soon as a request comes in, system will respond. That is the availability piece of it. Now the last one here in the 3 pieces is the partition tolerance. And partition tolerance means system continues to operate despite of partitioning due to the network failures. Now, network failure is one kind of failure where, let's say, for example, you have 10 nodes. 2 of the nodes are not able to connect to network. So we're just imagining that is a network failure, okay? So even after that failure, your system is still running. That is what the partition tolerance is. Okay, some partitions are down, your system still works, no big deal. Now, when this theorem was there, right, Eric said, okay, this is the theorem, I'm presenting it 1998. We should build a system, but you can choose only 2 out of these 3. You cannot get all 3 at the same time, okay? So then what happened is, okay, we already have RDBMS in place. So what does RDBMS fall into is consistency and availability. What they did is, imagine Oracle RAC 4 nodes. You commit on one node, that committed transaction is visible on all 4 nodes in the same state. That is your consistency. And if you have 2 nodes down in your rack, your system is still available. Clients can still connect. They can still query your data. That is the availability piece of it. Okay. So that is your RDBMS. I explained how it goes with consistency and availability. Okay. Now, in your RDBMS world, let's introduce what is partition tolerance. Let's say, for example, you distribute your data into 4 nodes. Remember, Oracle RAC, you are not distributing data because all 4 instances of RAC are looking at the exactly same data. It is the same single data. So you are not distributing them. Imagine if you are able to split your table into not the table partitions in Oracle, but if you're able to split partitions, and let's say, for example, one of the node goes down, meaning portion of your table is not available, will Oracle work? Basically, it says you have to recover, right? If your data file is not available, that whole table space is marked as unavailable. Now you have to do the recovery to make it available. That you already know. So that's where the partition tolerance issue is, meaning you chose consistency and availability to make RDBMS. You cannot get partition tolerance with RDBMS. So then there are these products like MongoDB, HBase, Redis. I'm talking about this theory now, okay? Where they say, okay, I need consistency. So you need that commit and rollback kind of functionality. I will commit the change and all nodes in the cluster will see the change. That is the consistency portion. And let's say I have 4 servers, I distributed data across, 2 servers are down. I'm still able to function, meaning my system is still up and running. My clients are able to query and run some transactions. And these databases will provide the partition tolerance. Okay, so that is the CP part of it. Now, what is that they don't provide is the availability. So the availability is, if at all any node in the system goes down, right, the whole system is marked as, okay, it's not highly available. So MongoDB, HBase, and Redis, all of them implement a partial high availability concept, but they're not complete high availability. So they fall somewhere like, in this area. But what they more follow is, like, if you think, for these 3 databases, Mongo, HBase, and Redis, they do a little bit of availability and a lot of CP. So think of it that way. Okay. Then comes our favorite, right? Cassandra, Couchbase, or DynamoDB, React, all these databases. What they say is, okay, will be highly available. Whatever happens will be available. Yeah, go ahead with the question.
Yeah. So, the example, whatever you told for the RDBMS is excellent. Okay. No one told me that example, like if any data file goes down, entire RDBMS needs recovery. That is very good example.
Yeah,
I need similar example.
At least your table space is not available, right? Until you do the recovery.
Yes, exactly.
Yeah.
So I need similar example for MongoDB. When you say availability, right? So you mean to like if
so
yes,
I will try to give you an example. I don't know how much you know MongoDB. I will try to give an example and see if it makes sense. Okay. MongoDB is something called master slave architecture. So there is one master database, a master server, and then there are several slave databases. Okay. So you can basically have one master and there are several slaves. Your clients connect to all this cluster, let's say, for example. They can do changes on each individual place, or they can come to the master. But what happens if the master itself is dead, right? So what happens is, in the system Mongo has implemented, you can actually tell, if at all the main master goes down, I can have another node elected as a master. But you see, when this particular thing goes down, it takes a couple of seconds for this master to wake up and become a master. Okay. So this is not high availability, because if the master is down, none of the other nodes in the cluster can do anything until a new master is elected. Okay. So that system is not highly available because it has the downtime for, even if it is 1 second, there is a downtime.
Yeah, perfect.
That makes sense.
Yeah, perfect.
Yeah, maybe you are not that satisfied as if the data file example, but MongoDB, basically we have to work with it a lot to understand that there is this issue, and they constantly try to improve, but it is not perfect. Again, you cannot make a perfect system which can live in this area. So that is the main theory itself, right? So MongoDB has that master slave issue, and I'll tell you when Cassandra will compare it with Cassandra, I'll tell you what is different there. Okay. So for now, is this good? Are you satisfied with the example I gave you for that? Okay.
That is enough.
Cool. So we'll discuss a little bit about what is this availability and partition tolerance and how Cassandra helps us with that. Okay. So what they did with Cassandra is, you have like a 10 node cluster, 7 of them are down, system is still available. How they do that is, there is no master in Cassandra. So basically going forward, I'll show you other images, but what happens is, Cassandra nodes are placed in a ring. So all nodes are masters and all nodes are clients, slaves. So there is no master in Cassandra. So basically they all are up and running, and if at all 2 of them are down, they're down. We don't care. There is no master. So each node will act like a master, each node will act like a coordinator, each node will act like a client. So it doesn't matter if some of the nodes are down, the ring is still performing. So meaning I will introduce ring after some time, but clients can come and they can continue to submit their requests, whether it is read or write, whatever they want. Okay. And then basically partition tolerance, we talked about having some data here. Let's say, for example, data 1 is here, 2 is here, and 3 is here, and then 4 is here. Okay. So if at all 3 and 4 are down, like these nodes are completely down, system will still work. And I'll tell you how Cassandra implemented replication to do that. Okay. That needs a little bit more discussion. But for now, what we have to accept is Cassandra is built with AP in mind, meaning availability and partition tolerance. Now, what they did with consistency is, because there is no commit rollback in Cassandra, it is actually a tunable consistency, meaning this portion here, let me draw it with green color, this portion here, you as an administrator, depending on the application, you will say, hey, let's use this consistency that is called tunable consistency or eventual consistency. We have to understand the architecture to get into understanding what this means. Okay. Cassandra falls into availability and partition tolerance along with tunable consistency or eventual consistency. Now again, Cassandra is not sitting here. I'm not claiming that Cassandra can do all these three. It can do a portion of it. Okay. Yeah, so one other thing about CAP theorem, right? There is no book to read, nothing. It's just a very simple document published in 1998. What is good about it is you just understand the basics. Why CAP theorem? That's good enough. And what you do basically is you understand that not a single product can support all three of them. There is one piece missing for any product. And the products can be categorized based on these three combinations of CA, CP, or AP. Okay. For Cassandra, it is availability plus partition tolerance with tunable consistency. That's all we need to know right now. As we go into the theory and understand the architecture, it will be much better. Okay. Now, obviously, why are we sitting in this class? Why Apache Cassandra? So why Cassandra? First of all, this is open source and it's a NoSQL database. Open source meaning source code is available. If you want, you can download the source code. You can understand if you know Java. Cassandra is 98% written in Java and 2% written in Python. So I'll just put it here that way we don't miss it. So Cassandra is developed using Java and Python. And as I said, Python is like less than 2% of the whole development process. I'll tell you where it is used. So that is the first point about Cassandra. Now remember, I was talking about Scila. Scila is developed in C++ instead of Java. It's massively scalable and highly available. So those are the two things we always needed anyway. Availability and partition tolerance, both are listed here as an option, not option, the strong point of Cassandra. Extremely responsive, again, the availability point of view. You can throw millions of rows per minute and it can store. It will never lose any of the data you're throwing at it. Obviously, you'll have number of nodes according to how much load you have. You might have to increase the number of nodes in the cluster. There is no single point of failure. When we look at the architecture, we'll see there is no single point of failure at the disk level. And I clearly know the difference between Oracle and Cassandra. I can tell you where Oracle will fail. There are many single point of failures in Oracle. For Cassandra, you can have the entire system burn and you can rebuild it. System in the instance, if you have a node which can burn in fire and you can rebuild it. Rebuild the Cassandra cluster without losing data. It supports out of the box. You don't have to do anything special. The same piece of code you download on the day one, it works on multiple data centers. I'm not sure how much experience you have with multiple data center setup. RAC has something called FAR sync implemented very recently in 18C. Basically, you have a data center in Tampa and you have a data center in, let's say, North Carolina. Connecting to them as a single rack, there is a lot of network latency, and Oracle suffers a lot with that kind of latency because it's a consistent system. It cannot have latency. But Cassandra is not a consistency-based system, so it can have latency and multiple data center setup. It's out of the box, very easy to configure, and we'll talk about it while we are configuring. I'll explain everything about it. As I said, it supports the consistency in terms of tunable consistency and eventual consistency. As you learn about the system, you'll fall in line with that. You'll understand why we are saying that. It supports structured and unstructured data. So not like the earlier, I said, document stores are JSON documents. Here it supports both structured and unstructured data. It can handle petabytes of data. Here, I'm not showing how much because nobody knows what is the limit. We know that Apple uses Cassandra, and they say it is more than 10 petabytes of data they store on Cassandra, but they're not very public about that. They don't tell us what they're doing with it. What is the kind of data they store on Cassandra? They don't tell us. I'll show you different use cases, how companies use it. Let's talk about ops, the operations per second or transactions per second, OPS or TPS. It handles thousands of concurrent OPS or TPS. The way you scale Cassandra, there is the next slide. Actually, let's move on to the next slide, which explains about the TPS and OPS. What you do with Cassandra is, Cassandra logo is this I. That's the reason I use I as a node. So you see there are 2 nodes in the first ring in this circle. This is a cluster of 2 nodes. Actually, this is a very stupid way to say. Minimum you need is 3 nodes. And anything less than 3 nodes, you should not be using Cassandra. You can live with MySQL, Postgres, or anything else. 3 nodes is minimum for Cassandra. And if you go tell your client that you need 3 nodes, they might say, oh, minimum 3 nodes, then let's not use Cassandra. You say, yeah, you don't need it because the data they have, probably they don't need more than 3 nodes. So that's why they're not even thinking about having 3 nodes. So Cassandra is not suitable when it is anything less than 3 nodes. So this diagram itself is bad. I should not be showing the 2 nodes. But what is the intention here is each node can handle 100,000 transactions per second or operations per second. Here we have 2 nodes, it can handle 200,000. And you just double them by adding more nodes to the cluster. So each node can handle exponentially more transactions. Okay, so that's how we scale Cassandra. Tokens. This is a very, very important concept. I don't want to go to the next screen. If you don't understand this, there is no point in continuing with the course. Every row which is coming into the application, so here is the 4 node cluster you have, and there are 4 nodes, okay? Every row which is coming in needs to go to one of those nodes because data is distributed here. We need to understand, okay, let me give you a small example, right? You take Oracle, because I pick on Oracle because that's one of my favorites.
All these slides are from Apache Cassandra, or you modified it as per your requirement?
No, I made everything from scratch.
Oh, I can see the difference.
Yeah, the quality is very high. Yeah, I am very proud of my work. So basically Cassandra I cannot draw again. That is the only logo I took from Cassandra side, but everything else is my own. I created all these documents.
No, the reason I asked is like I attended a couple of Cassandra sessions. No one have this kind of PPTs, so I see the difference.
Yeah, thank you.
Thank you.
Thank you. So what I want to show you is, imagine you have a 4 node cluster Oracle. Okay, your data is stored in ASM. So all 4 nodes are looking at the exactly same data. Any problem with that?
No.
No problem. This is a big problem. What happens if your ASM goes down?
Yeah, if you need to consider consistency, yeah. And if you see in case of availability, yes, it's an issue.
Exactly. So that's where the CAP theorem is, right? So what happens is it's a single point of failure with ASM. Okay. Well, there is no way you can avoid this. One or the other way, this ASM will show up. And also remember that all nodes are looking at the exactly same storage. They're not looking at their own piece of storage. Okay. Exactly opposite on Cassandra. Cassandra has small hard drives. Let's say, for example, if you look at the storage, and if I can draw this with my hand here. So there is a disk. There is a disk here. Nice drawing here. Okay, drawing skills are too much. Okay, so each node has a disk attached to it. Okay, and the data is stored in this disk here. On each node, you have a separate disk. Okay, so now imagine just for fun, let's make it blue. Okay, this particular node disk dies. Okay, you still have 3 nodes with their disks. So storage itself is isolated from each other. Okay, no single point of failure for storage. Good. But how do you know which particular data should go where? There should be a algorithm to this, right? Okay, first thing what they do is there is something called murmur-3 algorithm. On the bottom there, I have written murmur-3 is the algorithm. Token range is very high, minus 2 power 63 to plus 2 power 63. Just to understand here, we are saying, okay, server 1 is handling 1 to 25 tokens, and then server 2 handles 26 to 50 tokens, 51 to 76, and so on. Okay, each node we have divided the number of tokens. Also imagine these are the 4 houses in your neighborhood. Each house has a number, right? Exact identifier of a number of the house. So this is nothing but 4 servers here. 4 servers have their addresses assigned to them. Now the application comes in and says, hey, I want to store this data. Username is King and the user age is 40, let's say, for example, right? If you notice, King and Queen are the 2 rows which we are storing, and King and Queen are written in the italics. So basically, I just wanted to show that that is your primary key. Okay. Now what Cassandra does, the first thing it does is, so it takes this King, which is the primary key or partition key. It creates a hash token for it, and that token falls into one of these ranges. Okay. So let's say in this case, token is 35. Okay. So it goes into the second node, or this is the node. It's not even second node. There is no first node, second node, third node, fourth node, because there are 4 nodes. Okay. Now let's say King murmur-3 hash algorithm comes up with a result of 35. 35 is 26 to 50 is living here. So the King is getting stored on this server. Okay. You see that small hard drive I was showing you earlier? It puts the row here. Okay. Then the application comes and says, hey, I have this Queen, age is 35. Queen is also as a partition key. It will calculate and put Queen here. Okay. Now how Queen came there is, imagine its token number is 13. Okay. Something like this. So because it's 13, it's in the range of 1 to 25. It goes and sits in this particular hard drive here. Token is just an address. Okay, it's a murmur-3 algorithm. It's a large number. I will show you the tokens later on when we start installing and stuff. But token is the very basic stuff. If we don't understand token, then it's confusing later on. Okay.
So based on the algorithm, the record will be saved on that node. It's not about based on the data.
No, not based on the data. It is based on the partition key or the primary key. It will take the primary key, it will create a hash, and hashing is done using murmur-3 algorithm. It generates a token, and that token will match with one of the nodes in your cluster. And that's where your row is stored.
Got it.
Got it? Okay, perfect. So I want to introduce something called coordinator node here. Okay, I don't know if I have it on another slide, but I'm just going to introduce so that way we talk about it now itself. So let me type something called, okay, let's say for example, this application comes and connects to the cluster. Cluster is 4 nodes, okay? But one of the node will respond first, right? It will say, okay, I'm here, what do you need? We're talking about a listener, remember? There is a scan listener, listens to the incoming request. So think of it that way. One of the nodes in the cluster will respond, and whoever responds to the request is called coordinator node, okay? Now, there is nothing special about this coordinator node. What it is basically, that was the first node which said, hey, I'm here, right? And then application says, okay, I need to store this data. Coordinator node goes and checks the key, the token, and token falls into this node here, right? Then coordinator node, what it does is it takes this connection. Initially, it was listening to this, but it will say, hey, now we know that you are going here. So why don't you go connect to that cluster, that particular node directly? So if at all this node is busy, I will continue to handle your request, but it just forwards the request to the right node, and then it lets the actual node handle the request later on. Or cluster can decide, you know what, I'm the coordinator node, I will continue to handle your request, okay? So it's all based on a very complicated Java code in the background, and it will decide which one will handle the request, okay? So what I'm saying here is there is a terminology called coordinator node. You can never figure out which one is coordinator node because there is no special role. It is just the first contacted server which responded to the request. Cool? Don't go beyond that. It will confuse you. Now, let's review this particular slide one more time because tokens is very important. Tokens are mapped to each node in the cluster. Each node will have its own tokens assigned to it. Imagine that is your address to the token, address to the node. When data is inserted, primary key or partition key, it will take that primary key, generate a hash, and that generated hash algorithm is murmur3. Based on that hash value, it knows which token it is. It goes to the specific node which was handling that token and store the data there. And when the client connects to the cluster, I'm just generically saying this is the whole system it connects to. The request comes in as a read or write, doesn't matter. It comes as a request. First node which responds is called, in theory, it is called coordinator node. Okay. There is nothing like a special role you assign to coordinator node and you say, oh, what if coordinator node is down, right? There is no coordinator node. It's just a theory. Okay. I think for theory part, the token is the address which defines which node will handle that row. Cool. I want to challenge you with one of these things I was talking about. Say, for example, this hard drive dies. Okay, this trashed. So did we lose our data? King 40, that row should be lost because it's not there anywhere else in the cluster, right? So we definitely need to protect our system with some kind of replication. So that's the introduction to replication, okay? Now, what you do is there is something called replication factor. So you set this up, replication factor. I'll tell you when we get there, I'll show you where you set it up. You set up replication factor. We have 4 nodes. You're saying replication factor is 3, meaning every single row which is coming in, I'm going to store it on, let's say I'm going to store 3 copies of it. So you see king is stored 3 times here. And then queen is stored, like say, for example, let me see, blue might be very interesting color. So we'll take queen 3 times. Okay. we already know how the tokens are assigned. Okay, it doesn't matter which node, but there is some token, some node stores the original data. But here we are saying in Cassandra, we define that you want to store 3 copies in the cluster for every single row which is coming in. Okay, that is just a definition. You are not telling where the data should go. You're just saying I want 3 copies. Okay. Now you remember I was challenging you with one hard drive having that row which is dead. Okay, this thing is scratched out. You have 2 more copies in the cluster. Now this one is also scratched out. You have 1 more copy in the cluster. Okay, so basically you will have the data spread out in such a way that you keep multiple copies and you can recover from failures. Okay, for now just take it as okay, there are more than 1 copies available in the cluster, and this is tunable because you are defining it. And you say, for example, I don't care if I lose the data. You just say replication factor is 1. Just keep 1 copy. Don't copy it to other nodes. I'm trying to go like, piece by piece, introducing you to the complexity of distributed databases. And as we go into the slides, you can see we started with a very simple table column, and then we are going higher into like, how it can become big data. So then what happens is, okay, what if you have a scenario, you have a New York data center and let's say Hong Kong data center, who knows, US and Hong Kong, your business is big. Okay. So what we'll do is data center 1 is in USA, and then we have another one in, let's say, for example, Hong Kong. I'll tell you who has this kind of clusters. All over the world, there is a company. So what you can do in each data center, you can say how many copies of data you want based on the replication factor. You see, replication factor can be set for data center level. So what we are doing with the USA is we are saying 3 copies. So King is stored 3 times, you can see. And then basically on the other data center, in the Hong Kong data center, you're saying replication factor is 2. So King is only stored 2 times. Okay. Is that cool with the data center replication? Now you just define this once and Cassandra takes care of replicating the data. You don't have to do anything manually to, hey, go to that node and replicate it there and so on. Okay. Cool. One more introduction to a terminology called a ring. You see how I'm drawing the Cassandra clusters as rings? Because there is no master slave concept, right? There is no concept like this. So let me test my drawing skill one more time. So I'm saying in MongoDB, there is a master, and then there are like multiple slaves. Let's say you have multiple of these other nodes here, smaller ones. Okay. So all these can do the job, but master is the one which is master. Basically, this is the only one which is sitting on the top. Now you can apply this to both. You must know MySQL follows the same thing, and Postgres has the same thing, right? And let's say MongoDB has the same thing. I'm just trying to show 2 of them are RDBMS and 1 of them is NoSQL database. In Cassandra, there is no master. So there is no single point of failure. Here, if the master fails, all the clients will be like, for a second, they will wait and see what to do. In configuration, you must have configured that the other node will become a master in case of failure. It will take some time before that master comes back up. Okay. And then this master becomes a regular client here because role switching happened there. Okay. And that's all configured in the configuration. You can say, oh, truly it is not a downtime. Yeah, it is not a downtime, but it is not highly available because for that second, clients are confused on where to go. So that is the problem with the with the, what you say, having multiple nodes in the same cluster. And it's it's actually a technology called master slave architecture. So in Cassandra, we are using something called peer-to-peer technology. So this is a peer-to-peer architecture, okay? Not technology, architecture. What you see here is just if I want to draw, like that's why I'm showing you circle here, because there is no master. Every node can act like a master, every node can act like a client, every node is a slave, every node is a coordinator node. Every node can do every task. It's not like, oh, you are limited by the role. There is no role assigned to any of these nodes. So if you bring new nodes in, those nodes also will act like exact same nodes. So example with the Flex ASM, I don't know if you checked Flex ASM, it has something called leaf nodes. So leaf nodes don't have storage, they just have access to the storage. So leaf nodes also you can connect, your database can go to the leaf node and say, hey, give me the data. It does not have access to the disks physically. It just has access through the other nodes, which are acting like a master for ASM. So in Cassandra, every node has access to everything, and it is part of the cluster. There is no specific role assigned to it. And the other thing is because they're not master slave configuration, that's why they always appear as rings in circles, because there is no one node which is master of anything. Let me take a review here. 3 slides: tokens, replication, multi-data center. Okay, that product is defined here. You should fall in love right now, or you might not appreciate Cassandra. So what I mean by that is you understood the entire architecture here in 3 slides. Okay, why Cassandra is so popular is because I'll tell you earlier we mentioned this. He doesn't know why, but he picked Cassandra. All Oracle DBAs want to see their data in rows and columns format. Cassandra is row column store. Okay, and this is one of the best in the world, technology wise. Compare it to, let's say, somebody comes and says, hey, I want to store my data as JSON document. DBA first thing says, what? Right? That's the reason we fall in love with Cassandra, because it's a row column store. We understand it, and the architecture is pretty straightforward, and there is a lot of automation done on the cluster side. We don't have to manually do stuff. Let's take an example. Okay, I'll explain in a second. Okay, so you have your data centers in USA and UK. Even before you started asking, I wanted to tell you this. Who uses this kind of setup, right? Not just 2 countries, but they have thousands of data centers. Can you guess?
Okay.
So what Netflix claims is, okay, so basically, first thing I will tell you a lot about Netflix. First of all, Netflix is the company who is using Cassandra. So basically their entire database is on Cassandra. What they did is in 2009, 2010 time, they did a lot of research. They actually developed Cassandra, meaning I'll tell you how Cassandra started, but they were the one initially they said, oh, this is missing here, let me add this. So the developers at Netflix, they wrote a lot of code for Cassandra initially. What they claim is, imagine all the data is stored in Cassandra. So if you can get into the flight in, oh, I forgot. So DC1 is USA and DC2 is London, let's say, for example. You're flying from US to London. You get into the flight. In flight also, you are still watching your movie. You pause it when the air hostess says, hey, we have to shut down your electronics. As soon as they say, you are going to pause the movie, right? That pause is recorded in the Cassandra database, in Netflix, obviously, in the cloud. Okay, you close your iPad, and then imagine if you can take a flight within 1 second. If you can land in London, you pull your iPad up, and then you can play your movie. Netflix says you can play it. There is no lag at all. meaning in sub-seconds, they're able to send all the data, replicate it to the UK data center. When you land in UK, your data is local and it is ready to go. So they claim that if you can travel such a fast speed, your data is ready and your movies can continue just like that. There is no lag. Okay. Now Netflix has data centers everywhere. Like they use Amazon, and they're everywhere in India, in Australia, they're in UK, there are several places in Europe, Middle East. Any country you can think of which is open to having Netflix kind of shows, Netflix is available there, and they have nearest data centers in their network. They use Amazon, obviously. So we'll talk about that. Okay, cool. That's a very good use case, I guess.
Yeah, it's a very good example.
Yeah, and Netflix, even today, they keep writing code. So Netflix is a very big contributor. Let's talk about XML. So you know XML, extensible markup language. Sometime in past, they introduced something like XML. This is how it looks like. Okay. So XML, you see, that's how it is written, right? Say, for example, root products. In products, you have like this, the product code, product quantity on hand. This is the barcode, and then the next product, and so on. These are the rows in XML data. Cool.
Yep.
So what is the disadvantage with XML is a very structure oriented, very strict. So for example, if you don't have the stock quantity for the second entry, you have to at least put a 0. You cannot remove this tag. Stock quantity should be there. It cannot be removed. Okay. XML is very restricted, very strict, not restricted. Let's look at JSON. I don't know when JSON started, but JSON looks like this. So let's look at a JSON example. This is how it looks like. Let me take a simpler example, maybe orders.
So before going there, I have one more question. I don't know.
Sure.
So when you say HTML, right? Hypertext markup language. Why we go for HTML is for the nice look.
Correct.
Okay?
That's a presentation.
Yes. Is it same thing when you say XML also? It's like for presentation. It's
No,
a next version of HTML.
No, XML is nothing to do with presentation. XML is how you exchange data in a structured way between applications. So for example, this is 3 records. You're sending it to a different remote system in this format. And the other system can read this exact same format, right? They will translate it to code is this, quantity is this much, and this is the barcode. So you're exchanging data between systems using this format.
Mm-hmm.
Okay. And HTML has some tags which can present this in a table view. So that is only for presentation.
Okay.
Okay. Data exchange is done via XML, whereas HTML is only for presentation.
Okay, got it.
Okay. Now, because there is so much issue with the restriction or strict rules about how XML can exist, they created something called JSON. Okay. JSON is nothing but JavaScript object notation, I guess. That if I'm right, if I don't remember what it is, we can say what is JSON, right? Too many names to remember. So I'll say go here. What is JSON? JavaScript object notation, if I'm correct. Somewhere I should, here. Okay, cool. So it's just an object notation in JavaScript format, and this is how it looks like. So basically you start with a bracket and say track ID is this. Okay, so let's track ID is this. And you see, let me do one thing. Okay, so track ID is this, reported date is this time, longitude is this, latitude is this. That is the record 1. Record 2 is this, record 3 is this. Do you see any similarities? Like I was talking about a database which can store this kind of stuff. This is a JSON document, by the way.
I didn't get your question.
question is, I was talking about this kind of storage earlier. It is called key value.
Okay.
You see key values?
Yes, yes. Now, what is the column name and what is the value?
Correct, exactly. So this is a JSON format, okay? What is the advantage with JSON is, imagine you don't know when it was reported. You don't have to write that column. That data can be completely missing. And JSON is completely okay with it because it's a flexible schema, okay? You don't need to have all 4 columns all the time. That is what
So by default, it stores null value then?
No, that column does not exist.
Oh, okay.
Right?
Okay.
See, that's where we have to move out of RDBMS style. When the column is not there, it is not null. It is actually column itself is not there.
Understood.
Right? There is no allocation of space, nothing. Okay, we'll talk about this when we talk about Cassandra. I will show you what is called tombstones and how the data is deleted. You will definitely see it. Okay, so we saw the difference between XML. Here is the XML look and here is the JSON look. These are the documents. You can store this entire document into the database as a row, and that's where your Couchbase, some of those JSON document stores comes in. MongoDB is one of them.
And can I know why JSON became so famous? Like everywhere I hear JSON. Is because it like platform independent? Something?
Well, all these are platform independent because it's just a format of the file. But JSON is popular because of its flexibility, right? There are a lot of APIs. Let's say Python has a module which can convert it to JSON. Okay, actually, Cassandra has a module which can present Cassandra data as JSON. JSON has become popular because of its flexibility. Like as I said, it's not restricting you to have all 4 columns. And let's say, let me show you one example. Let's say, for example, for this record, not only 4 columns, but somehow it got one more column here, some special column, right? Never happened before. Okay, never happened before. There is a value. Value is 43. You can send that and JSON will totally accept it. No issues. Okay.
Okay.
So because of that flexibility, JSON has become very popular.
Okay. So in simple way, like if you have like data in Cassandra and if you want to send it to data to Python using the library of JSON, send the data and Python will take the data from there, read the data.
Actually, you don't need any library. You don't need any library in between. Cassandra itself will give JSON document to Python. It's just a request saying, okay, instead of giving me row columns, give me JSON.
I'm clear. Thanks for explaining.
Oracle has XMLDB. It also supports JSON. Remember that. Oracle has a native support for JSON storage. Okay. For Cassandra, I'll tell you one thing. Cassandra, there is a slide like long after. We don't have to worry about it now. Cassandra does not store JSON. Remember this. MongoDB stores JSON. Okay. JSON is nothing but, so JSON is JavaScript object notation. This is binary. JSON means binary JSON. Okay. So basically binary format of JSON. You cannot read it in binary format. Only MongoDB knows how to read it. But when it presents it to you as a client, it will give you JSON document.
It is so perfect. So what I do, I'll tell you one small story.
Yeah, go ahead.
So I mean, as we are discussing about Netflix, right? Because entire database is running on Cassandra for Netflix. So this happened in 2014. So when Amazon, they were trying to fix one bug. So that was a major maintenance happening on that particular week. So that particular maintenance, right, that will affect 10% of their cloud servers overall globe. So 10% of the cloud servers will get affected with that maintenance. So what happened? by the time only, like, there was 2700 Cassandra nodes were, was using on Amazon by that time. So because of this maintenance, right, almost like 250 nodes got affected, like 250 nodes got rebooted out of 2700 because of this maintenance. So after that, after the reboot, what happened, 22 nodes didn't come up. Means 22 nodes where Cassandra is running, they didn't even come up. They completely didn't came up also. Due to that maintenance, 218 were got rebooted, and 22 Cassandra nodes were didn't come back. But still, Netflix experienced, zero downtime, even though you lost 22 production nodes, and even they didn't come back, but still, zero downtime. So that powerful Cassandra is compared to
Very good
availability.
example.
Yeah.
Nice. Thank you.
So not everybody will fall in love with Cassandra. Cassandra is a very different kind of system. You need to adjust your own ego before you can become a Cassandra DBA. If you're especially Oracle DBA, you have to forget everything you know before going into Cassandra role. And then if you want to go and do some Oracle work, forget everything you learned in Cassandra and go do the Oracle work. Not easy for a lot of people. At the same time, Cassandra has some limitations. So it is always good to know what are the limitations. And if you ever have to face this with your application team, you will be at least having your strong opinion about what is the limitation. And again, limitation meaning this particular software is developed for a specific reason. So don't think of it as a limitation. That specific use case never required these things, and they will never develop it in that format. Meaning, Cassandra is not trying to become another Oracle, another RDBMS or anything like that. Okay, so they will not keep copying options from every single database to make it better. Instead, they will just be better in what they do, and that's good for everybody. So first thing, no joins. So basically, there is no joins at all. You cannot join two tables within Cassandra. So that's where Spark comes in. In Spark, you can do joins. You can take two tables and create a join and get the results. There is no joins, so there is no need for subqueries. And when I say there is no joins, no subqueries, there is nothing to support it. Okay, so don't think that, okay, maybe implementing that option will give it to you. So when there is no, there is no. And they will not implement it in the next version also. There are no subqueries. There are no transactions, meaning commit and rollback and checkpoint. Three of them, they don't exist. DCL is not there. No commit, no rollback, and no checkpoint. Limited aggregation or BI. I'll talk about that when we get to the aggregation. You can count how many rows are there, but that is a very bad query on the Cassandra. You don't ever count rows because, even in Oracle, if you have 1 million rows in a table, you don't want to run a count on that table. Imagine you all know about the full table scan. Now you're talking about full cluster scan. So imagine 2,500 nodes of Cassandra running for Netflix. You are going to do a select star from. It is a full cluster scan. Remember that it is going across the globe, thousands of servers, and asking every server to do a count on their local. So very bad. And that's why you don't have max, min, stuff like that. There is no business intelligence tools available for Cassandra. All that can be done with Spark, Apache Spark. That's why we need to talk about Spark by the end of this, the whole session. Brief history, we always want to know where it started, who started it, who is the mastermind behind it. Okay, some information here. Amazon published a document called DynamoDB paper, and then Google also had something like Bigtable. So those two people, published their documents. They made this small software called DynamoDB and the Bigtable separated by company names. Then Facebook came in and said, hey, you know what? There are features in DynamoDB which are good. There are features in Bigtable which are good. Let me merge both of them and make something called Cassandra. Facebook did not want to create a new product with their name on it. They gave that as a contribution to Apache. So this is why Apache. Okay. So they gave it to Apache in 2008 and they said, hey, Apache, can you actually take this? It's called incubation. So they take a new project and incubate it. So they will keep it in running for a while. And until it becomes version 1.0, it is in the incubation state, meaning they will see if anybody is contributing, will it really grow or it's going to die because there are no developers, there is no need for the technology and all. And you can see some of the dates I have marked in red color. July 2009 is the first available version. It is still available for download. October 2011, about 2 years later, the first version came out, version 1. And then there is a jump to version 2. There are several small patch versions. 3 came out in November 2015. And right now we are at 3.11.8, which is in end of August 2020, it released. And at the same time, they always have a major release and a new next release. So there is a stable release. So 3.1.1.8 is a stable release, and 4.0 beta version, right now it's in the second beta, is coming out soon. We are also waiting for 4.0 to come out. It has added many new features, including especially for the logging. They have included a lot of logging related features. So Netflix historically has published a lot of papers about using Cassandra. And what we can date to is Cassandra at Netflix is before 2010. So if you see the timeline between July 2009, first version becoming available from Facebook, and July 2010, which is the 0.6.4. Before 2010, Netflix was using Cassandra. So remember that they were not just using, they were actually developing it. They were writing code and contributing it back to Cassandra, Apache. You might ask, how do I get this? Go to cassandra.apache.org, go to download Cassandra. And then you see this version, which is the stable version right now. This is the beta version. And if you look a little bit closer here, there is archived versions, which are not supported, but you see the first version is still available for download. Here is the tar files and the source files. The original software, when it was released, is 8 megabytes in 2009. Okay. And you can see this incubating is the word added there. If you notice, Apache Cassandra incubating. So incubating, I was talking about incubation. And if you see the latest version will be like, here. So if you see 3.1.1.8 is what is going on right now for stable. And there is a beta version, beta 2. And then every single version is available for download. If you want to just play with it, here it is. And it is not hiding anywhere. It's a plain site. Basically go to cassandra.apache.org and then you click on the download. You click on which version you want, or you can go to archived, and then it basically lists everything there.
Okay. So when you say like Cassandra is developed, right? So who is the initial developer for Cassandra? Where it originated?
Facebook.
Oh, Facebook.
So basically what they did, Amazon had DynamoDB. It's still there today. Google has Bigtable, still there today. Facebook took both of those source codes and merged it and made it a Cassandra. And Facebook then said, you know what, we don't want to manage this product, which is a very good product. So we'll just make it open source using Apache licensing. So they contributed it to Apache, and then Apache maintained it since that day. So what I thought is we'll just do a couple of more slides where there is some theory introduction to what Cassandra looks like, some terminology architecture wise. So basically any cluster, when you have multi-node, each node has to talk to each other. So within cluster, there is communication happening, and that is called gossip. So basically peer-to-peer, there is a gossip happening, a node-to-node communication. And also so even clients, when they connect using Cassandra driver, they also listen to certain pieces of gossip. So basically, let's say, for example, one of the node is going down or restarting for some reason. Clients will be aware of that because it's published via gossip. So gossip is the internode communication, peer-to-peer communication within Cassandra cluster. So that is gossip. Let's talk about partitioner. So basically, partitioner determines how the data is distributed across nodes in the cluster. That is also decided. Basically, partitioner knows how many replica copies it has to keep and all that. And what we use by default, the algorithm is murmur3. So Cassandra uses murmur3 partitioner. There are other partitioners, but they're not very popular. So murmur3 is the default partitioner, and murmur3 is the algorithm used to create the tokens. There is a module called snitch. Basically, snitch knows everything about your network. So parts of it, you tell the snitch that this is how my network is laid out. And sometimes if you're using, let's say, Amazon EC2 as an example, there is a snitch called EC2 snitch. So Amazon itself implements some knowledge so that Cassandra learns about the network. So as soon as you say, okay, I'm running in Amazon, it'll know what to do with the regions, availability zones and all that in the Amazon side. Now there is a snitch called Google Cloud Snitch or Apache Cloud Stack Snitch. There are snitches which are also suitable for your on-prem databases. So we are going to use like gossiping property file snitch or EC2 multi-region snitch. So snitch knows about the network topology. Basically, that's a module which understands your network. So because it's a distributed database, network is a big part of the database. And it has to know how to distribute the data. SS tables. Okay, so let me write something here. SS tables are nothing but sorted string tables. So SS tables are the files. That's how data is stored. SS tables will contain, there will be multiple SS table files on the disk. And every server will have this SS table files on the disk level. And so basically a table, we'll talk about key spaces, don't worry about it. So for now, your data is stored as sorted string tables, SS tables on the disk. And each server will contain multiple SS tables. Think of it as data files, but they're not exactly mapped like table space kind of thing in Oracle. It's a little different. Tombstone. Tombstone is a marker for deleted data. So basically, it's just a soft marker. Let's say, for example, I'll write here, so for deleted data. So it's a soft marker. Basically, whenever you delete a row, column, that a particular row or column, what is deleted is tombstoned, and it will be removed later on based on the purge process. And Java, there is something called garbage collector. So basically, in memory, whatever objects are not being used anymore and they're out of scope of the program, they'll be removed from the memory. And so that's what compaction is. So let's say, for example, if you think of Java, Java has garbage collector, and similarly, Cassandra has compaction, as this. Okay. So basically what compaction does is there are multiple sorted string tables, SS tables. It has to merge the data. So we'll talk about how data is stored actually physically, and then we'll try to understand what happens during the compaction process. Is it cleans up all that, and also all the deleted data is not deleted immediately as soon as you delete. It actually gets deleted with the compaction process. So it's a lazy delete, if you call it lazy. Basically, it does it slowly. It doesn't do it immediately. Because if you have to delete like a million rows, like, you don't want to put impact on the system. So you slowly delete it. So next thing is, okay. There are a couple of very important things, right? It's a database. You're storing data and you're retrieving data all day. So you have to understand how data is going from one place to other place and how it is being retrieved. SS table equal to sorted string table. Oh, sorted string table. Okay. So what happens is, there is a right. Okay. So one thing here is anything above this line here is memory, and anything below is the physical storage, like hard drives. And what we are looking at is, imagine you're looking at one server, one node in Cassandra cluster. What does it contain? Okay. So when the data request comes in to store the data, so basically a client connects to the cluster and says, hey, can you store this data, right? Yesterday we were looking at example of King age 40, please store this, right? So before coming to the screen, you already have a token. It knows where to go, which node to store data. Then what happens on the actual node is the data goes into the memory first. So there is something called mem table, and mem table is a memory object. It just stores that data, the King 40 row, in the mem table. Now, exactly at the same time, there are two paths for what is happening here. Is it sends data to memory, and it also sends data to the commit log. So commit log is, as you notice, commit log is on physical disk. It is not in the memory. So basically commit log has commit log entry. And you see the memory also, memory entry is there. Okay. Now, another request comes in, and then that request also goes to commit log, as well as it goes to memory. Memory, it goes here, and then commit log, it goes here. And the table could be a different table. Basically, let me just change it to, like, say, green. And then this is a different table, different row. And then there is an entry written in the mem table. And then there is an entry written in the commit log. So it does this all day, right? Data is coming in, it writes into the memory, and it writes into the commit log. And both are happening side by side. Okay. At certain time, what happens is it fills up. So basically all the memory is filled up. See, disk cannot run out. It as long as you have disk space, it will keep writing commit log. But when memory is full, it has to do something called flush. So it takes whatever is the memory content and writes it into the disk. So what it does is, every time it writes a new file. So there is a new physical file, and the file is called SS table. SS table contains two portions in it. One is index and the other is data. So index is nothing but, we know, right? The index is basically the address of the row, and then data is actually physical row. Okay. So what we are trying to understand here is simple. Every time it flushes the mem table from memory to disk, it flushes it as a new SS table. And SS table is attached to one table. So one table has multiple SS tables, Every time it takes the memory and dumps it into the disk, it has multiple SS tables written to the disk. So you can see that's the reason I have like multiple boxes here. So you can see this represents like multiple files. Okay. So far, any questions?
Yeah. So when you say like first one insert into one table and other insert belongs to other table,
right?
Those will come to mem table, okay. And when those will come to commit log, and when it fills up, it uses it is flushing. So
right.
when it
mem
flushes,
table, when it flushes the mem table, and only when memory is full, it is flushing. Okay.
Yeah. So when it flushes, so it comes as one file, or it like one SS table consists of multiple tables, or for each table there will be one SS table.
Okay, good question. So let me repeat this, right? SS table belongs to only one table. So what it does is every table will have its own SS tables. Okay. So if there are two tables in memory, then there will be two SS tables. It will be dumped as. Okay. So one SS table will contain data belonging to only one table.
Okay.
Okay.
So yeah.
just to make the representation easy, there is only one mem table here. Imagine mem table itself is a small pieces of different tables, right? And then each of that chunk is written as a separate SS table, right? One table is here, one table goes here, and the other table goes into another SS table. So whatever data is there in memory, it's dumped as multiple SS tables. And so mainly you don't have one SS table, you have multiple SS tables. Is that concept clear so far?
Yeah. So as soon as soon as the data comes, it goes filling the mem table. As soon as it flushes, how many corresponding tables are there? That many corresponding SS tables will be created.
Correct.
But the only thing is like, let us suppose, you will tell the size of the each SS table later, right?
No, there is nothing like that. Each SS table is different size and it just dumps them. So imagine one table has lot of inserts, right? So this is a very large insert here, and that goes in a one large SS table, okay? But all the other SS tables are small. It doesn't matter, right? It just writes whatever is there in the memory. It just flushes to the disk. So not all SS tables are of the same size. Only thing you try to understand is whatever is in memory, it just makes a copy into the disk and memory is cleaned.
Okay. And when it is cleaning up next time also, it won't append old SS tables, right? It
Correct.
will create new SS table.
I haven't mentioned that yet. Okay.
Okay.
So what we understand now is whatever was in memory, it is flushed into the tables, right? Into the physical disk as SS tables. Now, you see, there was two things happening here, like commit log and the SS tables. So I want to mention here, once it basically has written the data to the disk, then this commit log is of no use because commit log was keeping track of what was in memory. Okay, so it knows that it can delete this commit log because it's already flushed to the disk. Whatever is in memory is already safely stored on the disk. It can clean up the commit log. So it basically says commit log can be deleted. Okay. So what we understood here is the data comes in, okay, control. So basically data comes in, it goes to both commit log and the memory. And then when the memory is full or whatever interval period, whenever it decides, it will flush the changes to the disk. As soon as it flushes the changes to disk, it's a new SS table, it will write it as, and SS table contains index and data. Once the flush itself is complete, it has no use for this commit log anymore. Whatever was in memory is already saved. So commit log can be deleted. Okay, this is basic path. Now we want to talk about that SS table. So basically every time it dumps the data, right, it will write it as a new SS table. So that's why you see these multiple SS tables here. So you see all this 1, 2, 3 and 4 and so on, right? There are multiple SS tables. One thing you have to remember in Cassandra is SS tables are always written as a new file. They never get appended. They never get replaced or modified. So SS tables are immutable. That's what we say in Cassandra. So let me say, for example, SS tables are immutable. Okay. This word is very important. In olden days in C, C++, what we used to do is memory allocation and deallocation. So we say, okay, we need a memory 4 kilobytes, please allocate. So then system will allocate 4 kilobytes for you. Now all day you can store something, replace it, update it. But in the newer technology, what happened is memory is cheaper now. You can have 1,000 copies of the same data. It is easier to allocate new memory than modify the existing memory. So they keep making new copies. So when you keep making new copies, that is what is called immutable. You're not changing the existing data, but you're just copying and creating a new allocation. So same way, SS tables are immutable, meaning if SS table already exists, Cassandra will never go and update it. It will just create a new file. Okay. So we have to understand how SS tables are maintained on the disk, because if you have multiple copies, that means data is in multiple files. So Cassandra has to somewhere, it has to do something called cleanup. And that's what I was talking about earlier as compaction. So let's say you have a scheduled job, or let's say Cassandra comes in every now and then and says, hey, you know what? I see these 4 SS tables for this table. I'm going to merge them. So during that merge, it will delete all the deleted data. It will make one good copy of the row, because there are several modifications. It has to just keep the latest modification, latest version of the row. So it will merge all the old data and only keep the whatever is the current view of that data. So SS tables are merged together, like, they're compacted, and the process is called compaction. So let me see, to just to review in this this particular slide. Data in the commit log is purged after the corresponding data in memory is flushed to the SS table on disk. So SS tables are on the disk and mem table is in the memory. The name itself tells you that it is physical or memory. Commit log is used for replay. If at all, say for example, server crashes or something happens with the writes, operation got corrupted or something. So commit log is used to recover the data into the memory. So if a server restarts, then it's a different story. But if at all, say for example, it was doing a write, okay, before it reached the mem table, it has completed writing to commit log, but something went wrong with that write. So what Cassandra does is it goes back to the commit log and says, hey, you know what? I see this transaction, which is not in memory. So it will bring that into the memory just as a quick recovery of the transaction. And then eventually that will be returned to the disk. So when memory table is dumped into the disk as SS table, this commit log can be deleted. It can be cleaned. Okay. SS tables and mem tables both are maintained per table, meaning in memory, mem table is also, you can imagine that is a multiple copies. Each copy is related to one table. And then whatever is in memory, it is dumped as a SS table. And every time it will dump as a new SS table, because its SS tables are immutable. SS tables contain the index, or it is also called as partition index. It contains partition summary in memory. There is Bloom filter also in memory. So there are a lot more components than I'm showing you here on the screen. Overall, there are 4 or 5 things on the screen. We don't want to put 1,000 things to confuse us. So basically data write request comes in, data goes into memory, and also it goes into commit log physically. In memory, whatever is there, after some time when it is filled or some threshold reached, That memory is dumped into the disk and it is stored as SS table. SS table contains index and data. So two things. And the process of dumping memory into the disk is called flush. That's a very high level of how data is written to the disk or it is stored in Cassandra. Then obviously we need to retrieve the data. Whatever is stored inside, we'll retrieve the data. So I used exactly same slide. You see all those things are some things you know already. The commit log is gone from here because when you're reading data, commit log has nothing to do with reading data. So same representation. I have the storage, physical storage here, under here, and whatever is in memory is listed up here. And then you see these SS tables, the same 4 SS tables you saw in the previous slide. They have their index and they have their data. Now, what Cassandra does is, whatever is in this index, right? Index is loaded as a partition summary in memory. And also it has something called Bloom filter. So I'll tell you what is Bloom filter. Now, let's look at how client comes in and says, hey, I'm looking for this user called King. I want to know what is his age. Okay. So you know that King 40, that is the row we are looking for. So what it does is, first of all, Cassandra says, is this particular record what I'm looking for, whatever data I'm looking for, is it in memory? Okay. So here it is checking. So let's say, for example, in memory check. Okay. So what it does is there is an in-memory check here. It says Bloom filter. Are you available in memory or you're not available in memory? So if you're available in memory, it just goes to the mem table direct. Okay. So if at all the data is not available in memory, then it takes the no path. It goes to partition summary. Okay. Let me first go through the flow and then I'll explain what happens on the other scenarios. Okay. Also, if I remove all these arrows I am drawing, and you see this particular arrow which was already on the slide, why I'm showing that as red? Because it is doing a hot read from the disk. So because hot read is like, obviously it is reading from disk, it is expensive. So what Cassandra does is, so what we decided here, okay, we don't have it in memory. So we have to go to the partition summary. So partition summary, imagine it's a memory object which knows the partition information, meaning your partition key is nothing but King. So where is this recorded located in which SS table on the disk, right? I'm still talking about one node in the cluster. I'm not talking about multi-node scenario. It's a simple one node got the request. It is looking at its partition summary, Bloom filter first and then partition summary. It says, oh, that data file 40, let's say data file ABC contains this information. So it goes into the disk and it reads the data and goes to the next step here. Okay. Now let's say, for example, you're running a select statement which will return 2 rows. One row is available in memory. This is first row. And the other row is not available in memory. So it is going into the disk. Okay. So this is the second row. Now what it will do, so you see how Bloom filter can say yes and no at the same time, because it has one row in memory. It does not have the other row in memory. So it has both paths in there. So whatever it was reading from a disk, it will read and bring it to here into the memory and take whatever is in memory and merge these two together as a result set, right? Now that result set is sent back to the client. So these blue arrows tell you that it is a return path. Okay. So let me clean up what I was drawing earlier. So black color, I mean, if you can make out the color difference here, the data read request came in the black color. That black color is deciding whether it is available in memory or not based on the Bloom filter. If it is not there, then goes into partition summary and does a hot read from the disk. And when the data is located on the disk, it will return it to the in-memory process using that blue path. So it comes here and says, is there anything to merge? So let's say, for example, here, I'll say, is there anything to merge here? So I'll just draw a plus sign. If it has to merge some data from here, some data from here. So it could be the same row. Some columns have updated values and some other columns are stored in the disk. So it has to merge for the latest view of that. Okay. So that is the merge I'm talking about here. So it takes all the memory copy and physical copy, merge the rows or the result set, or compile the result set and return it to the client. Okay. So client gets the latest view of the data. We'll go back to the previous slide. You knew what is commit log in the previous slide. And the mem table is nothing but your memory copy of the data. And SS tables contain index and data both stored together. Okay. I'll show you when we create the cluster, we see, we'll look at these files. So in the read path, I introduced two more things here to you. One is called Bloom filter. Bloom filter decides whether data is available in memory or not. That kind of algorithm which tells, yeah, this is available in memory. And I was telling you, right, you could have 4 copies of data stored in 4 different SS tables, and there is an updated value in memory. So your Bloom filter can say, yeah, I have some data here, some data here. And then there is a merge process which comes later in the read path, which is right here, which is merging the result set. So then I introduce something called partition summary, which basically tells, okay, in physical disk, this is the address for you to go and pick it up from that particular SS table. And when you go into the SS table, you say, look at the index and say which particular block or the data piece I have to read from the hard drive, and then return that whole result set, the perfect view of the data, whatever is up-to-date information, that will be returned to the client. But once the data read and write, we are taking a completely different view of what is data stacks. Because on the day one, you look at Apache Cassandra, it's open source. Open source distributed via Apache license. But there is a company out there called DataStax, and you go to datastax.com. What these people do is they take the Apache Cassandra and they modify it a little bit, make it enterprise ready, and they added a lot of other features to it. So basically what they do is they integrate Spark. Apache Spark is pre-integrated inside the DataStax enterprise. They also took the Lucene-based search engine and integrated it with Cassandra. They also have Graph Engine included in the DataStax enterprise. They have multiple drivers which will work with Kafka and Elasticsearch, and also supports bulk loading of the data. You can also load the graph data, which is basically like ingestion of data. And they say it is advanced performance, enhanced security and monitoring. For monitoring, they have something called Ops Center. And what they claim is they're taking the same 100% open source database, but they add some extra modules to it. And for graph, they developed something called graph query language. They support like K8, SQL, REST API, and all that. And then there is this Kubernetes support. Okay. So they added all these things and they made a product called DataStax Enterprise. So the other products they also have is they offer this as a cloud service called Astra. Astra can run on both Amazon and Google. So basically when you're launching your Cassandra as service in Astra, you can specify which cloud you want to use. DataStax Enterprise is the actual enterprise product you buy. You get the license from DataStax, and you get all these things pre-integrated. And then you also get the support along with it. So you get error. You can call them and say, hey, can you fix this? Is it a bug or what? And then there are tools like Dev Center, and then there is Op Center. So let's do one thing, right? It's easy to go to datastacks.com. Why I introduce right here is so you know what is out there. So basically go here and look at the products. They have all these products and the services. You can also look at download options here. Go all the way to the end of the page, and then you go to the downloads. In downloads, you can see they first bring you to Astra. This is the cloud service. There is Enterprise Edition, which is the DataStax Enterprise, DSE. And then there is tools, like you see this Op Center. There is something called Desktop. Studio is more like your Eclipse IDE kind of thing. And then there is this bulk loader program, which you can use to ingest huge amounts of data into Cassandra cluster. Kafka connector, it's a Kafka supported connector. Dev Center is like SQL developer. I'll show you later on. There is graph loader, so you can take data and load it into graph. Data is stored in Cassandra, but you can use GraphQL to query it. SQL SH comes with basically Cassandra, but they also have their DataStax Enterprise SQL SH, not a big different one from SQL SH itself. Then there is that Kubernetes operator. You can download this for Kubernetes support. They also develop a lot of drivers. So you can see there is like C, C++ driver, Java driver, Node.js, PHP, Python, Ruby. And then there are some community drivers, which basically is supported by the community, not by the DataStax. There is this ODBC, JDBC drivers. So you can see all the Simba, Spark drivers. Databricks is a company who support Apache Spark. So they have that. They have DataStax ODBC driver for Hive. And these are available for multiple operating systems. Community drivers, there are some more drivers like Golang, and then Erlang, Perl, Scala DSL. So these are all community-based drivers, but these are all DataStax drivers. Now DataStax, because it's a big contributor to the whole thing, so they maintain the documentation, and there is a lot more DataStax does. Like they give you training, there are like resources like certification. They have academy.datastax.com, which is free training. You can sign up for their training. I mean, DataStax is not just selling. So don't think of it as like, okay, they sell an enterprise product. No, they do a lot more than just selling a product. So you just need to keep in mind that DataStax is an important piece of the whole thing. As a DBA, a lot of people ask me when they're switching from Oracle to Cassandra, they say, okay, in Oracle, I know how to manage my database. I know how to work with RAC or Golden Gate or DataGuard. What is my role when you get to the Cassandra DBA? So Cassandra DBA, it's very important. You have your Oracle database with like Exadata with unlimited amount of memory. If somebody writes a bad query, it is still your job to control it. That is in Oracle, right? Same thing with Cassandra. As a DBA, you're supposed to know what we can do and what we cannot do, because as long as somebody puts data, they're going to do a query on it, and you should know what not to do. Okay, definitely you should know that. And then Cassandra data modeling is as important as building a cluster for DBA, because you are the one who will play a very key role in designing your tables, which are being stored on Cassandra. Because in Oracle, what we do is we say, okay, you need a table, I'll create it. And then if it is not performing, we'll fine tune the query, add some indexes. Cassandra is different. You first understand why you need that table. What are you going to do with it? If you don't have that question answered, your app team cannot proceed to creating a table. So just remember that DBA has a key role of understanding how to create tables, why they're created that way, and what you're doing by running one of those create statements. So that is a key role for DBA to understand, okay? So obviously, if you have to interact with your cluster, we need a software like, there is a SQL shell, but we also need something like a SQL developer. So DataStax has a product called DevCenter. So first thing we'll look at today is just see, like, you know, I'll show you my local cluster. I'll show you this DevCenter. So go to DataStax page and go all the way to the end of the page. You will see this download section here, tools and downloads. They renamed it to tools and downloads. So then you go to tools and you go to DevCenter. Okay, so that's as easy as you finding the DevCenter. Once you find the DevCenter, you can pick the latest version and then pick your OS you want. So I can go with Windows, and by clicking this agree box, download. So once we get the package, right, it's a very basic zip file. I'm not even going to download it. I'm just going to run it. Okay. So it looks like this, okay? Now what we'll do, I'm not using the AWS cluster today. So I'm just going to show you what I have. So I have a local 3-node cluster running on my local PC. So if you look at node tool status, okay, so I have a 3-node cluster. You can see the 3 nodes IPs, all 3 of them are up and normal. And what we are doing here is a node tool version. You can see we are running 3118, and it's open source Cassandra software. My data center is East Data Center, and 3 nodes are in there, okay? So what I'm going to do is, in my dev center, I need to connect to this cluster. So I'm going to just create a connection. So let's say cas_local, and then so what I did here is I added 2 IP addresses from my cluster. Now my cluster can be 800 nodes, but all it needs is the first 2 or 3 contact points. That's all you need. That is true for any driver which is built for Cassandra. Let's say, for example, Python Cassandra driver, Java Cassandra driver, Node.js Cassandra driver. All you need is couple of contact points you provide to the driver. And what it does internally when it connects to the cluster is, the first thing driver itself will do, it'll ask, hey, give me the ring information you have in your cluster, meaning how many data centers are there, each data center, how many nodes are there, and what are those nodes. Meaning, partially, client itself will participate in the gossip. So now what happens is client has the inbuilt knowledge about the cluster itself. And if at all a node goes down in the cluster, that gossip information is actually pushed to the client too. Meaning client also listens to that gossip, right? Not everything in the gossip, but at least it knows which node is down, which node is not down, how many data centers are there. Now, if you had 800 nodes, you don't enter all 800 node IPs here. Remember that part. Then you try to establish connection. Your connection is successful. You say finish. Your connection shows up here. Double click and you're connected to 2 nodes in your cluster. And let's say you pick the connection you want to run the query on, and you have some key spaces. We haven't talked about that yet. And then what you do is write your query, select star from, let's say, system.local. We haven't talked about any of this, but I'm just showing you that you can run your query. It shows an output. So that's pretty much like your SQL developer, where you can write your query and run it, and it runs against the cluster and gives you the output. That's all. Okay, nothing fancy. Now, during the discussion, I'm going to use both SQL Shell and Dev Center. Wherever possible, we'll switch between them. Now, how do you launch SQL Shell is basically SQL Shell with host name specified. Okay, host name could be local IP, which is like 192.168.1.153, which I'm connecting to a specific node. Okay, so when you use SQL Shell, this is how it looks like. So basically what it is doing is you're telling SQL Shell. SQL Shell itself is built in Python. So, remember I told you Java, Cassandra is built in Java, but there are very little 2% portion which is developed in Python. So SQL Shell is that. Now, you're telling which IP address, one of the IP addresses in your cluster. And then basically it says connected to, this is the cluster name. I'm connected to this node in the whole cluster. Now remember, as soon as SQL Shell connects, it knows about all the other nodes too. And then this is the port it is connected to. You remember we discussed about client to server communication using this port, which is the native transport port. Then SQL Shell version is this, Cassandra version is this, and SQL also, just like SQL, structured query language, CQL, Cassandra query language, has a specification. So this is the specification implemented in this version. We are using native protocol version 4. You remember if you enable your native transport version 6, then it will use the version 6 if you need to do that. You can run help command. So this is how a basic SQL shell will look like. And then your query will look like select star from system.peers. Okay. So this is all we need to know before we start our data modeling. And we are going to obviously explore all the options here. Okay. So Cassandra data modeling. Now, this is a very, very important topic. As I said, if somebody goes and runs a wrong query on your database, you are the one who will get in trouble first, not the person who executed it, because they'll come back and say, yeah, this is a valid query. I need the data for some executive report. That executive doesn't care what technology you're using. And you must have told them on the day one of the project, you said, these are the things you cannot do, but they forget on the next day and they expect everything to work. So what is the main rules we have to follow when you're doing Cassandra data modeling? First of all, Cassandra data modeling is based on query. So query driven data modeling. What does that mean is, we have to identify how data will be retrieved even before it is stored in a table, okay? So even before a schema or the table is designed, you need to know how you're going to, you meaning application, is going to retrieve that data, okay? This is the key to achieve fastest data writes and reads in Cassandra. If you do not do this step, the rest of the model will suffer from performance, from all other issues later on. Okay, so the common practice in RDBMS modeling, we know day one we learned about normalization. So first thing we do is we normalize the whole structure, right? And for performance, what we do later on, we say, okay, we'll add some indexes here and there, we create virtual columns and then virtual column based functions and all that stuff. That's what we do with RDBMS. Now, For Cassandra, because it's first thing is it's a distributed database. It is not any other database where RDBMS is all centralized. Cassandra is highly distributed. So normalization doesn't work. First, we have to think here is denormalize. So here is the conflict between your RDBMS DBS and the NoSQL DBS. NoSQL is all denormalized, meaning we never think about normalizing the data. First form is you keep it denormalized. Okay. So that brings us to the second point where our data model should be denormalized. Okay, that is the default in Cassandra. Now, if you remember normalization forms, first normal form, second normal form, EF card mentioned all these things. And then third normal form, then he talks about some more. And then finally there is like, okay, you're not dealing with OLTP kind, you're dealing with OLAP, which is analytical processing. Then he talks about denormalization. So imagine Cassandra starts with denormalization and there is nothing called normalization. Then the last thing is single table, single query approach. Okay. Remember from the beginning I've been telling, Cassandra does not support joins, meaning you cannot join two tables in a query. So since you cannot join two tables in a query, Cassandra does not support it. So all the data which is related for a query should be stored in that table, even if it is a duplicate data. Okay. So if you have a customer address cannot be separated from the customer table because you cannot centralize that address. If you need the customer address in 4 places in 4 different tables, you have to keep that. That's how Cassandra's data modeling is. Then, so the last point here is the single table, single query approach. That is what we use in Cassandra to get the best performance. Okay. So we'll go to the next slide and see how these small things play out, like, what are the terminology for Cassandra tables. Okay. Now, in the olden days, when Cassandra started, they used to call it as column family. So this column family is still there. Under the covers, you will still see it some places, but now we generally call it as a table. Okay. Now let's go to the smallest thing possible within Cassandra is a column and value. So a column name and a value is like a key value pair. So we saw this several times before. I even talked about some databases like Redis are key value pairs. So key value pair. Okay. So this is a key value. If you think of a column with its value is a key value. Okay. Now, if you think for a second, when you represent your tables in Oracle, you will see these columns are all joined together as if they're cells. But here they're not joined as cells. If you see there is a space between them, there is a very good reason for that, because this one small unit here is one value stored together as key value, okay, within the storage. Then you have bunch of columns, okay. So you have bunch of columns and they're all tied together using this primary key. So if you take this column is your primary key, and for few minutes, you have to keep this in your mind. Whenever I say primary key, it does mean that it's a partition key, or whenever I say partition key, it is the primary key. That's how Cassandra says it is a partition key or the primary key. It is same thing. Now the row is tied together as one row using this primary key or partition key. So that is your row. Row is not collection of columns. Remember that. So row is based on a partition key or the primary key. Now, in few examples in the next slides, I will show where you will see one partition can have multiple rows in it. So this is a very simple explanation of what a row, what a column and partition key is. but this is not the only explanation. So this is just an entry level explanation. Okay. So let's see what else we can discuss here is, okay, primary key or a partition key, it is hashed to generate a token, Marmor-3 algorithm. And based on the token, Cassandra knows which node will store this data, this particular row, okay, or the partition. Now, columns are stored as a key value pairs. Collection of columns is a row when they are binded with their partition key or primary key. Each row has a partition key or a primary key, and that cannot be escaped. A partition can have multiple rows, and collection of partitions is a table or a column family. Okay. Partitions are distributed. Remember that all these partitions are stored in different places. And then collection of tables is a key space. Key space is nothing but a schema. Here they call it as key space. Okay. Column family is nothing but a table. And remember that not only your table, your partitions get distributed, but based on replication factor, which is defined at the key space level, they will also be kept, Cassandra will also keep multiple copies of each partition based on your replication factor settings. So here is a basic example, okay? Now, remember I'm telling you, like, you know, every time I show this representation, there is a gap between each of these cells. Okay, they're not represented as cells, they show the gap because that is how storage is. So don't think of them as like, you know, a spreadsheet kind of cells within the database. Okay. So let's talk about simple primary key. Primary key, partition key is the same thing. Okay. Remember on the first slide, I said, we need to know how you're going to retrieve your data. Okay. So it is very important to understand your application will always know the email ID. Okay. Let's say, for example, you're building a website where users log in and do something else, like say they sell their products, they buy the products, or they chat, or whatever application you're building. First thing is we are looking at a very simple users table where a user comes in, and whenever user comes in, let's say Google Mail, you know your email ID. So that's what the example here is. Okay. So select query whatever columns they need, from where they need, and how you are going to filter the row, how you are going to identify a particular user. So it is very important to know how you are going to retrieve this. So the piece of information here, your application team is telling you, this is my primary key or partition key. So that is what I am representing here. Everything else is pretty basic, right? You have email ID, first name, last name, and then you're creating a users table. This syntax itself, see both of the select syntaxes, they look same, like you know Oracle, then you can understand this on the short one. But this representation is not same. Remember that. Okay. So let's talk about the representation here. So email ID is your primary key. Okay. So you see king@gmail.com is the first entry you have. Okay. He has a first name, last name, he or she. And then you see the remaining entries there. This is a basic, simple primary key. There is no complication here. Very simple table. No. So basically, why we call it as a simple primary key is because there is only one column which is acting like a primary key or a partition key. Okay. These kind of tables are also called as static tables. They're basically very simple. They only have one column as primary key or partition key. Okay. Static doesn't mean that you will not change the data. You are going to change the data, but it's just called it as static tables. And then, you know, some of this is theory part, like, you know, nobody is going to ask you what is a static table in an interview. Okay. So get to a little bit complicated scenario where we have a composite partition key, obviously 2 or more columns. Okay. First thing your application is, let's say, for example, you're building a website where you're going to show hourly temperature for, like, you know, the zip code. Okay. So basically somebody comes in, a user, provides a zip code, and then by default your application knows for which day you're looking at, like say it is current day. Okay, so these are the two pieces of information your application will always provide you. So I'm mostly focusing on the where clause. Okay, so this where clause tells you one important thing is your primary key, your application will always provide you these two pieces of information. Okay, now create table syntax, ignore all the top portion which you know, like you're going to store a zip code, what is the temperature date and temperature time. One thing if you notice here, so this is kind of denormalized forms. If you need to store a date as two separate pieces like date and time, then you will do it that way. Do not use the timestamp in that case, because as we go, we'll understand that if you need to keep date and timestamp and date and time separately, then you will do it as 3-4 columns, because that's what denormalization means. Okay. Then you're going to store the temperature, and here I'm not using the floating values. You can use the floating values, just keeping it simple for integer type. Okay. So what we have to understand with this this scenario here is, we know that we are going to get two input values, zip code and the temperature date. Okay. In the primary key, here is some action going on here. So let's try to understand what it is. So we put this extra brackets, you see. So we are saying now the data is grouped using zip code plus temperature date, that is going into one partition. Okay. Then there is this extra column. We'll talk about it in the next slide. Don't worry about it now. So for now, you understand that zip code and temperature date is your partition key. Now, because you have multiple keys in your partition key, you call it as composite partition key. Okay. Now, there is some note here which shows, like at the end of the slide, if you see, if you collect hourly sensor data, 24 rows per zip code per day. So you'll have 24 rows in a partition. So if you take one zip code, one day, this partition will contain 24 rows. Okay. We'll see some representation, then it will become easier for understanding. Now, what is a composite partition key? You have more than one key, one column in a primary key, a combination of columns. These tables, obviously, if previous one called static, then this will be a dynamic table, just for theory's sake. These are dynamic tables. And this is a very powerful and high performance storage technique for time series data. So why we have this kind of distributed databases is mostly because you have high volume data, and most likely they're time series. Basically data collected from sensors, data collected from like high volume transactions. So any of those will fall into time series kind of data. Okay, so let's look at the representation of exactly what we saw in the previous slide when we were introducing a composite partition key. I gave you an example of hourly temperature table. So here is the representation. Okay, so imagine you have a zip code. This is a valid zip code in US. And then you have one particular date. On that date, every hour data goes as one row. Okay, so here I'm just making it look like a row. Okay, imagine your Oracle representation. I removed that key, just showing you values. And this is the temperature information on an hourly basis. You can see there is between 2 a.m. and 3 a.m. there is a jump in temperature. I mean, there's only a mock-up data. But you can see temperature is stored, and this is a time series because it's based on time. And you see the values going as rows. Now, here, one partition is this red thing is, whole thing is a partition. So partition contains 24 rows if you stored all 24 hours of data. Okay. So same way here, there is another partition, and they can be in two different nodes. There is another partition here from a different zip code, a combination with a different date or same date, doesn't matter. That blue thing is one partition. It has 24 rows in it. So I'll give you a little bit more details on this. So if you look at this table, we are capturing 24 hours of, we're capturing hourly temperature per zip code. And then there will be one partition containing 24 rows in there. And then zip code plus date is your partition key. That will be stored as one partition. And this is suitable for, the requirement we got on the first slide. So if you remember, this was our requirement that our application will come in, query for zip code plus temperature date as input. And then, so that's why we designed our table this way. And that's how the table looks like if you imagine how the storage will look like, okay? Based on that partition key, we're talking about storing 24 rows in one partition, okay? So this is where I was saying, you can have one partition can have multiple rows in it. Actually, you can call them as multiple entries because row itself is the combination. So this whole thing is one row, right? If you look at in high level, but this is a partition in Cassandra and it has multiple entries in it. All the related entries are partitioned together. So let's look at this in a distributed world. What happens when you see it in a, how many nodes are there? 8 nodes are there on the Cassandra cluster. You see this ring. This is a very known representation from the day one we are looking at Cassandra. I always told masterless peer-to-peer Cassandra architecture. So this is a ring. Each of these circles is basically a node. So we have 8 nodes here, and you see the representation here is only partition key. So you see the partition key plus date, that is your partition key. And each zip code has a different date and it goes to a different place. I messed up here. Why did I mess up? So you see how the same date, so 21st should not exist again, right? Okay, that's a wrong representation. I'll fix the slide. So what I'm showing here is, or trying to show is, each partition is distributed across the cluster. I'm not showing the replicas here. They're just distributed, that's all for now, okay? So you see for this one, I did okay, 22nd, 23rd, 24th. So this side I messed up with this date here. I'll fix that, okay? So based on your partition key, which is for now, we know that zip code and the date is the combination, that each partition now is distributed across your cluster. And when you might have million partitions, okay? You are asking me like there will be small partitions, several of them. So million, if you got million rows in this table, that means million partitions distributed across 8 nodes, okay? And you actually, that's a good distribution. You want small partitions because Cassandra reads partitions like Oracle reads blocks. So this is a read at partition level, okay? So I fixed that date problem here. You see this 27th now. So I changed a little bit so you don't have duplicates. We are not talking about the replication factor yet. So I'm just showing you that each partition is distributed across the cluster. And if you have a million partitions, which is a very good thing. So do not get scared that there are small partitions, several of them. Because in the distributed world, you need so many small pieces. That way it is easier to distribute your query also. Like you can parallelize, okay? So let's, we talked about a simple partition, only one column in the partition key. We talked about composite partition key having multiple columns in it. Now there was one mysterious column in the partition key definition when we looked at the create table command. So we're getting there, almost there. So let's look at what is a compound primary key. Okay, so we looked at this query earlier, right? We know that our application team will provide 2 columns with their query. And then they also say, hey, you know what? I might be able to filter with the third column, okay? But then I have additionally other requirements, like I'm going to look at the data always using order by temperature, hour, minute, and second. Based on these columns, I'm going to get my data in a descending order, okay? So what is best thing to do is you actually store this information in the table and store the data in this format. So you don't have to reformat it while returning the data, because application, your weather.com kind of website will do million queries every day with million people querying the tables. And all the time your pattern is this, your select statement looks like this. So why don't we store the data itself in this format? Then your retrieval will be faster, okay? Because whether you spend a little bit more time in writing, but when you have your data stored, it will always give you data back in the format you need to show on your application, on your website, okay? Now, if you analyze it a little bit, what it says is, if you're collecting sensor data every 5 seconds, you remember the previous sensor data was hourly data. Now the temperature, we are saying, we are going more granular. We are saying every 5 seconds, there is a sensor data coming in. So what is this means is, for a combination of zip code, day and hour, you're going to have 720 rows. And if you take a zip code and a day combination, that will be 17,000 entries in one partition, okay? So just to realize how big the data is slowly becoming, right? We don't want to do the small data on a big data database. So we want to go into next generation where you have millions of rows, and that is the normal for Cassandra, okay? So let's look at the table structure, because here is your app team coming to you and saying, okay, this is our requirement. So then you say, okay, as a DBA, I'm going to give you this table, okay? So you can see here, we denormalized it further. So what we did is we took our temperature time and made it like 3 different columns. You made it like hour, minute, and second, because you're getting more granular data now. Keeping the data type as tiny int, your date is still intact. If at all you have a requirement to split the data and store it as temperature day, temperature month, and temperature year, you will do it. No problem here. So denormalization is a key to get more performance, okay? And then you have a temperature column where you're going to store temperature. Now, let's spend a little bit more time understanding this particular new primary key we have. So these columns, the 3 of them, which are in the special brackets I'm showing you here, which is a zip code, temperature date, and temperature hour. Because now we are capturing every 5 seconds, we are going to capture data, but we are going to group them hourly. So somebody coming to our website, looking at your where clause, you remember this where clause, your website will always show you current hour, 5-second temperature data, okay? So based on that, we are storing this group, and then there are 2 more columns here, and there is some more syntax here, okay? So let's see what these columns mean, okay? First of all, you see the inner bracket, that is your partition key. So that we have been introducing it for like past 4-5 slides. So you know what is a partition key here. Now, what are these extra 2 columns we are adding, which are like temperature minute and temperature second, okay? These are called clustering columns. What does that mean is, within the partition, you're telling how you're going to sort and keep the data, okay? So what you're doing here with the clustering columns is, you're saying temperature minute and temperature second. Based on that 2 columns, you're going to sort and store the data in such a way that when you run your query with order by clause, it will always give you that order by, okay? So data itself is stored in a sorted order. That means your application or SQL engine doesn't have to do any more sorting. Just give the data as it retrieves from the storage. Now, you see with clustering column order by, you have a option of specifying descending or ascending orders. So this thing is also written at the table creation level itself. Like here is the keyword. You can use descending or ascending for the storage. So it depends on what your application team tells you. Based on that, you can create this table. Okay. And just to repeat, this is your partition key. This is the combination with which a partition gets created. And within the partition, using clustering columns, they're used for sorting. Later on, I'll introduce something like they're used for uniqueness, and also they're used for sorting the data and store sorted information in the partition. Okay, so then we'll look at the example then. So your table now, partitions look a little bit more data in there, more entries in there. Nothing big. We already know the combination of zip code, date, and the hour. So this is the zip code on that day, on the first hour. Every 5 seconds there is data. So this is minutes, and this is seconds, and this is the actual temperature. Okay, so that's how it is. Data is represented inside each partition. So you see every 5 seconds there is data recorded here, going in a descending order. So this is how it is stored in the table partition, and that's how it is retrieved and provided to you. Okay, so it has every 5 second data recorded. So let me see. Next slide might give us some information about how big this data will be, right? We were talking about big data. So if you read that a little bit, it tells you how much data we are talking about, how much, if your partition is per day or partition is per hour, then you can estimate how much data you're looking at. US approximately has 43,000 zip codes, only US. So let's look at a little bit different kind of scenario where, let's say, for example, you're going to do banking transactions, let's say, right? So the requirement is every year end. Okay, so we are going to generate a report which is going to show user transactions done at ATM or local bank. We take the previous year transactions, all the transactions for single account in a previous year. Okay. Now I'm just looking at the select statement. Okay, select start from user bank transactions. Account number we know, definitely that will be provided to us. And then we also know the year which will be provided to us. It could be previous year, it could be 2 years behind, but you know the year, there will be 1 year given to you. And then you have order by. Within the output, I want to write order by, trans date, trans amount, and trans amount is in descending order. Trans date is in ascending order. So that is my requirement for a select statement, where every year end, I'm going to take the bank transactions and make a big report and print it and send it to the customer. Okay. So let me just take 1 minute before we go into how we create this table and what is this primary keys and clustering columns. Remember, if there was a bank, they want to store their banking transactions. Okay. Somebody might tell you, oh, Cassandra is not suitable because there is no commit or rollback, transaction consistency and all that. Actually, it is incorrect. What you do is you use Oracle like RDBMS for your consistency part of it. Okay, you definitely record your transactions, everything in that. And also record those transactions for reporting purposes in Cassandra. Why would you do that is, Cassandra eventually is cheaper than RDBMS, and you will have more resiliency because it's highly available. You can distribute the data and then run various kinds of reports, which you might not be able to run it on RDBMS. I'm not saying you'll not be. I'm just saying that what kind of reports you run on big data are not suitable for RDBMS kind of scenarios. So definitely you have two copies, one in Oracle, which gives you your transaction consistency, but you can also keep data in Cassandra where you can generate your reports. So it's a cheaper platform to generate analytics. Okay. Now I'm just saying reports, but you could do other things like, say, for example, fraud detection. So your transaction happens on Oracle, gets saved there, but immediately gets pumped into like AI kind of system where Cassandra is the storage, and Spark takes that data, analyzes it, and tells, okay, you know what? Credit card transaction 40 minutes ago happened in Massachusetts, and then physically at a different pump in a gas station happened in Dallas, Texas, which is not possible. Like you cannot travel that fast in 40 minutes. So that's a fraud detection. And that's what people are doing with these kind of platforms like Cassandra and Spark. Okay. So let's go forward and say, okay, my bank transaction table will look like, okay, a bunch of columns. And then the main interesting thing is, because you know the where clause, you always are going to get the account number and the transaction year. That is used as your partition key. In that partition, you're going to take the transaction date and transaction amount. Those are the two clustering columns. And then I put this in a special color here, which defines the clustering columns. So I'm reading the last two lines with clustering order by. So clustering columns are transaction date stored in ascending order. And if at all on the same day you have multiple transactions, then the records are descending based on the transaction amount. Okay. So now when your app comes in and says, hey, I need to run this yearly report, and our customer comes and says, hey, can you give me a report for 2017, all my transactions? They're going to hit this database, run that select statement, whatever output came, put it on a PDF and send it to the customer. Okay. This is just to show you a different scenario of, don't think that it's all time series data. It can be used for all kinds of different kinds of data. This is just another example of how you can use Cassandra to store non-weather data or non-time series data.
When you are saying, right, like the main transaction happens in the Oracle and then the data will be transferred to Cassandra. This one?
Not transferred. You know, nowadays everything is microservices. The same microservice can actually push data to both Oracle and Cassandra at the same time. Yeah. Go on.
Okay. So when okay. So from the application itself, it is sending data sending to two places.
Correct. Application is a microservice which is written in Java, and then it can do multiple transactions on two different places, sending same data or parts of data to two different places.
Okay.
And that's how today's systems are designed, with all this Kubernetes and all these small microtransaction related technologies.
Okay.
Okay. So we are talking about a very large distributed database. Okay. Now imagine you're storing this much of data per year. So how many millions is this? Like there's a billion, 267 billion. Is that correct? I'm looking at the last entry here.
Yes.
Yeah. So if you have 267 billion partitions, okay, I'm just putting it like too much. Okay. Even if it is an Oracle, will you go and do a select star from table?
No.
That will be crazy. So in Cassandra, what happens is SQL engine doesn't even take that query. It takes it, and then within 10 seconds, it will say, no thanks, it's a timeout. So by default, it will timeout in 10 seconds. Okay. Now somebody comes in with you designed all these nice partition keys, and your application said, this is how I'm going to query. You already established the rules. Somebody comes with a crazy query. your executive. Generally, they do this. They say, hey, every 5th second transaction, give me transaction count, right? That is like you were doing a full table scan before on RDBMS. As a DBA, you said, no, this is not a good query. Now you're asking it to do a distributed full cluster scan. Okay, so that's a big no-no. First of all, you don't have to do anything. Cassandra itself will reject the query. As soon as it sees that SQL engine knows that you're not using the partition keys for filtering, and it will reject. Now, as it is rejecting, it will also throw out some error along with some information saying, hey, you know what? You can use these 2 keywords. Just put those 2 keywords and I will run the query for you, right? And if your application does that every 5 seconds, then it will not show any performance, and that will fall on you. You go back to the application team and say, hey, you know what? This is a wrong storage. You redesign your tables. And I can help you how to redesign it, but this is not going to work in production. We had issues. Somebody did a wrong design, and we had to fall back onto the previous system completely. And then we had to spend like 4 or 5 days redesigning the tables. And then after that, 3 years or 4 years, app team did not talk to us. So Cassandra, you need to design your tables properly. Data modeling is the key. So a lot of people who were trying to fall in love when we built our 3-node cluster can tip off here. This is one place where they can hate Cassandra and say, oh, this is too difficult to data model. Okay, so that could be one hurdle. Okay, Cassandra query language. So just like RDBMS has structured query language, we have Cassandra query language. So here is the introduction to data types. Most of these data types are from Java. They did not have to do anything. They just took Java language, take the inbuilt Java language data types, put them in Cassandra. Nothing special. Okay, so there are all kinds of data types available. The slide also contains a URL for where you can see what is the, when we sat in the first class in Oracle, they said, oh, int can store 32,000 values. I'm not going to go into the detail. You can go read whatever Java supports, Cassandra supports, because it is written in Java. Okay, SQL shell gave you some introduction. We know how to launch the SQL shell here. So I was talking about how to launch using the SQL shell IP address. SQL shell itself is developed in Python. You can run queries, you can run help. That will provide you some help. What we'll look at basically is, we'll see what is next. Okay, so we talked about key spaces. Okay, collection of column families or tables are stored in a key space, like a schema in Oracle. So we definitely need a key space for our own use case, our own study. So let's start with how do we create a key space? Okay, so that's the basics of getting started with Cassandra SQL. So let's look at how to create a key space. Okay. Now, first of all, what you can do when you log into your cluster. So what we'll do, first of all, in SQL, here, SQL shell, okay, I can do describe key spaces. So that will tell you what are the existing key spaces on the cluster. So by default, there are some system key spaces. You see all of them. Not much to explain there. You know, the traces will store trace data about like connections and events. System schema is like your explanation about all the other schema objects. Authentication related tables will be stored in system_auth. System itself is about the cluster, like how many nodes are there, what nodes are there, what are their IP addresses. System distributed is there are some information about the system which needs to be distributed across the cluster, all nodes or some nodes. So those are the key spaces which are already existing. The same information you can look at by querying select star from system_schema.keyspaces. So there is a table inside which will tell you the same information, but with little more details, durable writes, replication settings, and all that. Now, what you can do also is to create your own key space. Obviously, you need to create your own application key space. Okay. And the way we do it, we say create key space. And there is also tab fill. So by default, if you type partially and say tab, it will print the remaining keyword. So let's say, for example, we'll do CAS demo for demo purpose, or you can have sales key space. Now, what you need to specify here is with replication equal to. So you can get some example of replication, how to specify the replication using this particular existing key spaces here. So basically you have to specify what is the class for replication, how you're going to do it. So this is where you see a little bit of Java seeping into your SQL, and it looks a little odd, but what is the Java class you're going to use for replication? And it will look like class equal to network topology strategy. So let me paste that. Okay, class is network topology strategy. You can make mistakes here. This is not YAML, and then it will tell you what is the exact mistake. Let me do one thing. I'm going to open another session. So just going into the same server, but I'm just going to run a no tool status on this because I need this data center name. Okay. So you're telling this key space will use this replication replication strategy, which is network topology strategy. This is the best strategy when you're using multi-node or multi-DC Cassandra setup. Then you specify the data center name in single quotes and specify how many copies you need to store in that data center. Okay. Now, here, if you see, I have only one data center. You could have multiple data center. Let's say, for example, like on AWS, you created east west underscore DC, and on west DC, you want to keep 3 copies. Okay. So remember that each data center can have multiple nodes, and they don't need to be equal number of nodes. So here in this case, this data center, I have only 3 nodes, but I can have 10 nodes. Now, what you're specifying here is how many copies of each partition you want to keep in each data center. So one entry you make into the table, how many copies it will be stored in this particular data center. Now, I don't have West data center, so I'm removing this from the syntax, but this is how you'll create a key space. And you can do describe sales, or you can also do describe key space sales. That will print the same thing. And that's what you use. So here, class, there are a lot of other strategies. So here you can see some of them called simple strategy or local strategy. For any application data, we are going to use network topology strategy. And what it is basically it's a Java class in the background, because your Cassandra itself is Java. So what you're doing is, instead of going and looking at what is network topology strategy, you are just letting that Java class take care of it. And network topology strategy knows how to distribute data across multi data center or multi nodes. So syntax is basically, you create a key space, you tell what is the replication strategy. You don't really remember this, you don't really type it with hand. You always copy paste from somewhere. But network topology strategy is what you use about 90% of the time.
And the durable writes equal to true means?
Yeah, this is always true. So you don't touch that.
Okay.
Imagine you want to write some data and they will disappear. Do you like that? So durable writes are that. So do not ever make it false. You just leave it true. That is the default for all of the key spaces. So here I created sales key space. Key space is just like schema. You're going to create tables in sales key space.
So before creating a schema in database, right? We define a table space, right?
Yeah, nothing
so,
here.
Okay.
It's all done for you, and the files are managed. I can show you very quickly what happened. In the background, if you look at your data folder, in that data folder, we have another data folder.
And
remember,
like it's like MySQL, like it creates sales.
Correct. But it hasn't created anything because there is nothing to store.
Nothing is,
Nothing to store there. There are no tables, nothing.
So then it says like whenever you go to data folder, you can tell like you have 5 key spaces.
But what if you drop the key space, their entries might still be sitting there. So they might exist, might not exist until the cleanup is done. Okay.
Okay.
Cool. So like here, you cannot tell that sales is there, right? Because it doesn't show anything. And also we can take a look at multiple nodes. Same thing. Data, and look at this. Okay. But remember, your sales key space is populated everywhere already. The whole cluster knows about it. Okay. So if I'm connecting to my local host, connected to eternal 3, third node, not the first node, and I can do describe sales, it will show me the key space information. Because your create just needs to be done on one node. It gets populated in the cluster. Okay. So now that you have your key space created, you can say use sales. And then in that you can say describe tables. There are no tables. So that's why just empty. You don't have any tables in there. Okay. So we created a key space. We know how to use it, and we know how to describe tables. So you see, we did all these 3 things. We haven't really looked at creating tables yet. That will be the next step. Okay, so what we can do now, obviously we need some tables, and we looked at this example before. We looked at some slides, right? We created table. So I copy pasted this, create table users, columns, and the primary key. Remember one thing, you cannot create tables without a primary key. So primary key is a must. Okay, so you can never ever create a table. It will just not allow you to create it. So that being out of the picture, I can do select star from users. Okay, or I can do select star from sales.users. All good? No data, so nothing comes out.
Can you show that key space OS file system?
Yeah. So let's do a listing here. And the sales key space got created. Okay. So look at sales, and you have one entry for your table, and then go into users. There is nothing much. Okay. So there is no data, but the structure got created. Cool. So let's insert some data, right? Now remember, this data can go distributed into different nodes and all that. So you need to provide column names. That's why it gave that error. So you're going to just do clear screen here. Okay. So that inserted a row, and then you can insert something like this. Okay. With a null value for the first name. And then, okay, so let's talk about something here before we continue. So let's do a select star from users like earlier we did. You can always use the up arrow key just like your bash. Okay, so you see the two entries here. Okay. What we were discussing is when we are inserting data, you provide columns, all values. It will just basically show up normally. Here I'm providing a null value. Okay. So if you remember, so this is the null value. Okay. And you see the last name I did not provide in the column list itself. So there is a small difference here, not like RDBMS. RDBMS is very structured and you'll see all the columns, you provide all the values, all that is stored as a very strict thing. Here, you remember there was a reason I was telling you that these things are disconnected from each other. Okay. Now, if you look at the data here, this null, you are actually explicitly telling it to store null. Okay. So in storage, that record will contain a null pointer in that particular place, meaning there is a storage allocated for first name and there is a value put inside, which is null. Okay. For last name, for this particular queen record, it will not even create that column. There is no allocation of storage for that. So just understand that. Now, why it is showing you null here is just for your representation. Okay. So that storage itself is not even allocated. Here, storage is allocated and it is storing null in that particular storage. So in RDBMS like places, right, it's very strict about structure. And when you talk about NoSQL databases, they say, oh, it is, structure free or flexible structure. This is what a flexible structure means. Okay, so some discussion about insert and how the data is stored for the allocation. So let's go see what we have to do: update, delete, and then truncate. Obviously, we want to select data and see. We did that. You can also do like selects based on the primary key. So that will look same, no big deal. And again, remember that case sensitive data is case sensitive, just like Oracle. Nothing special there. I think in this particular case, MySQL is a little different. Okay, so let's query based on first name. Okay, should not be no big deal, right? First name queen should show up. What is it saying? Oracle will say no rows found.
Yeah.
Here it is telling you cannot run this query. Come on, what are you doing? Okay.
Yeah.
So remember, you cannot use whatever where clause you want. You need to use a partition key only. So remember, I was telling you some crazy guy will come and run some crazy command. Your SQL engine will reject it immediately. CQL. Okay. Now you remember I was telling you it will say 2 keywords. Add these 2 keywords. I'll run for you. Okay. That crazy guy will read this error message properly. We don't read it, but that guy will read it. What he'll do, he'll come back here and he'll say first name equal to, and then, oh, you know what? That query engine itself told me that I can run this query. Okay. So let's actually take the first name as king, because I think we have king, we don't have queen data, and K must be with the uppercase. Okay. Let's see, run the same query without allow filtering. Okay. So I want to explain this difference here. So you see, when I put allow filtering, it is able to run the query. Without allow filtering, it is not running the query, it is failing. So remember, whenever you see this allow filtering, it's a very big red flag. You are not supposed to run this with allow filtering.
Yeah, even I thought same thing.
Exactly.
It should not give data, first of all.
Yeah, that's what, I mean, it gives you data because it is expecting your user to know what users are doing with the allow filtering. But remember that allow filtering, what it is doing is it is doing a full cluster scan. So it has no clue where the first name king is. So it will go through every single node, every single entry, every single partition across the cluster. But remember, if you ever see this allow filtering in your apps, somewhere somebody is coding with allow filtering, they're actually asking your full cluster scan. Okay. So as a DBA, your red flag will come up and say, hey, you know what? You're not supposed to do it. Even though Cassandra tells you to do it, here it is saying, oh, you know what? Maybe you can run it with allow filtering. Okay. What I would like to do is not even show this error message. I would like to say, your query failed.
Actually, what is wrong in giving first name equal to king? It matches, right?
Because in Cassandra, you're not supposed to query with any other column other than partition key.
Oh, that is thumb rule.
Yes. It's
okay.
not even your thumb. It is your entire Cassandra's life rule.
Okay.
So
once you give allow filtering, it ignores everything and goes complete
for
scan.
Full cluster scan.
Which is not recommended.
Well, will you recommend table scans?
No.
Same thing.
Okay.
Yeah. So here is your users table right now data. Okay. Let's do some updates. So I did update without where clause. It fails immediately. Right. That's a good thing because you're supposed to update it only when you use your partition keys. Makes sense, right?
Yeah.
Okay. So it is it did the update. No big deal. Update. You know how to do the update. Okay. So you can set some of these, and I was trying to show you there is another small change here. Okay. Now imagine when you're doing this, your queen at yahoo.com exists in the table. All good? So it updated the last name equal to Jones because that's what I'm updating here. Here I ran another update with a where clause where queen is written in uppercase. Okay. Do you see this? What happened?
One second. I'm trying to understand the data, what you are trying to
do. So let me get rid of the top one. Okay. Let me get rid of the error also. So now update users where email ID is lowercase queen. It worked.
Okay, it updated Jones. Okay.
Then what I did is I said email ID queen in uppercase. That also worked. Nothing happened. Nothing wrong.
It created new record.
Correct. So what you have to understand in Cassandra is there is a concept called upsert. Okay. So insert is an insert. You know that. Okay. Update is nothing but another insert.
Okay.
Why? You remember immutable?
Yeah.
So it doesn't really update. It just overwrites the existing one. It keeps doing that again and again and again. Okay. So whether you update or insert, it is the same thing. You can actually update using insert command too. Okay. Let me explain how you can do a update using insert command. Okay. Now you see this King Gmail and King Smith. You remember that particular entry. Okay. What I'll do, insert into users. Okay. Values email ID, comma first name, comma last name. And what I'll do, instead of providing first name, I'll just say last name only, values. Okay. I will use the email ID king@gmail.com. I'm using exactly same key. Okay. So your partition key, which is already existing. In Oracle, you'll get an error saying unique constraint violated. Primary key constraint gets violated. In Oracle, you will get an error saying primary key constraint violated.
Yeah, if you are entering the same value. Yes.
Exactly. But here it doesn't give you that error. Okay. What does it do? It basically goes and updates the record.
Oh my God.
Yeah. So that's what it does. Okay.
Then by mistake, if anyone does that one, we lost the old data, right?
Correct. Gone. There is no way to retrieve. There is no commit, no rollback.
It is actually shocking, right, for Oracle DBA to see this.
Well, that's why I build up that stage, you know, like presentation, example, bring it in. And then when finally that hero lands on the floor, he's just not breaking the floor, but the floor itself disappears.
See with the reaction. Oh my God.
Yeah.
Welcome. We are good. This is how it works.
No, I'm just wondering, like after giving every step, if people are doing wrong and if something is like this, so then it should be like something like no DB or nothing. No one should be allowed to do any DMLs from the console. Everything should be from the application.
Well, you cannot really control all that. I know in a real situation, somebody else will always have access to it. You know, application user can log in and they will have some DML access. They can do it. But anyway, these are the basic things, and they can. Of course,
I should not ask this question.
No,
do we have auditing?
No, not on the open source. And in DSC, there is some auditing, but not at this level. So I want to show you something. What happened is so far on the 3 nodes, I don't have any files in that sales users table related files. Anybody can explain why? We already put some data, we are doing some manipulations, but nothing is there on the disk.
Come again 1 second, show me. So on.
So we have data in the table, right?
Yes.
But none of the 3
Yeah, that
servers,
is not filled. That is not filled. That cache sheet. What is that? No.
No, you're close. Mem table.
Yeah, that is not full. It has to flush.
Yeah, it hasn't flushed. Now you're using the right words. Mem table is not full in memory, so it is not flushed to disk. So
can you show the commit log?
SS tables are not created yet. Okay.
Yes.
So now you're getting in that group. You want to see the commit logs. They're in data. They're in commit logs folder. Okay. Like here. So you see the commit logs. Yes. Now commit logs might contain more than just your inserts and updates, because they might have cluster related updates also. So commit logs will not tell you the full story because you cannot see them. But they do have commit logs on all nodes. And those commit logs will contain this data. Okay. Cool.
Yeah, I passed your exam.
Yes, you did. So that means you're paying attention to the theory. Yeah. Okay. So now delete. Let's delete some data. Okay. So I'm deleting first name, last name from users. So this is a new syntax for Oracle DBS. You delete data which is in rows, but here delete can be done on columns also. Okay. So again, every time you try to do something without a partition key, it always tells you, you know what, you need to provide me a partition key. That is a basic thing with Cassandra. Without a partition key, you cannot do anything. So let's go delete this particular.
One quick question. When you say that allow, what is that one?
Allow filtering.
Yeah. So application team are not supposed to use allow filtering in their queries, right?
No.
Okay.
I mean, see, once in a year they're running a report. That's a different story. Okay. So you see here, there is another error here. So I tried to delete first name, last name, where, oh, I did not put where clause, right? So obviously that will fail. Okay, so I deleted the data. Let's look at the table now and see what happened here. Okay, delete first name and last name from users table where user ID is equal to this. Okay, so these 2 columns, earlier they were having some values, doesn't matter what value, they became null only for representation, right? In the disk, their allocation becomes deallocated. Right now we don't have anything on the disk also. Remember that.
One quick question.
Mhm.
When you say the data is writing to commit log, right? It is writing to only that node, or it is writing to other nodes also in the cluster?
But you don't know which node your coordinator is right now, who is acting to it. It's a cluster. So commit log, wherever the coordinator is, that commit log is being recorded.
So till the flush is happened, it will not update in other nodes.
Well, other nodes will see the same thing. It doesn't matter because they all know how to read the mem table. Because see, Oracle-like thing, you have flash cache, right? In the memory, whatever is there in the buffer, it has the internode communication to transfer those blocks between the cluster nodes.
Okay, so you mean to say a commit, so the blocks will be transferred, but it won't be, it might have not be there in the commit log.
Well, yeah, commit log need not to be there on all nodes. It will be there in the node which is acting like a coordinator and doing the job.
Yes, yeah.
But all the nodes will see the data, up-to-date data.
But it can see the data. It may not be from commit log. It may be from memory.
No, they never read commit logs. They're only, commit logs are always written to. I never told you that they're read. During the read path, they don't read from commit logs. They're always reading from memory, Bloom filters, and then index summaries, then going into disk or mem tables.
So when you hit this query on the second node, then definitely this query going to the main node and pulling the data if it is not there.
So what it is doing under the cover says, it basically says, hey, I'm looking for this data. Are you the owner of the data based on the token, right? Then tokenized information, each mem table will have some information. It is not fleshed right now. So in memory, if you have anything, just transfer that information back to me. I need to give it to this client.
Yeah, understood. Got it.
Okay. So now you are, remember when you read path, your commit logs are not in place. You only in write path, there is a commit log in between.
Got it.
Okay. So all nodes will see the data. That's the eventual consistency. So within like a second or less than a millisecond, it will see that data and all nodes will see that delete you executed. Okay. Let's do one other.
So here one thing to observe is when you hit that partition key, that partition itself is not deleted.
Well, we're coming to that next one.
Okay.
Now you observe something. What happened here? I'm only deleting the last name column for queen in uppercase. So let me repeat this for you. Okay. Lowercase queen has some values before. We deleted first name and last name, but the row still exists. That partition still exists. Okay. With the null columns in the storage allocated. Then I said delete last name from users where queen in uppercase, that partition itself disappeared. You know why? When you were at the storage level, none of the columns other than partition key have any values. That itself means that you don't need that partition. So it drops the partition. So that's what you were asking earlier, whether partition is deleted or not. It gets deleted if you don't have any other columns in the row.
Okay.
Then why we have this sitting here?
Okay. Do select star from everything.
Yeah, that's what I executed.
Then why?
So why is this? Because you allocated storage earlier for these columns. Remember? We provided values by saying allocate null. Null is a value. So it is still sitting there. But remember when I did a queen insert, I only inserted for 2 columns. I did not insert values for 3 columns. I think it was somewhere here when I did a insert.
I think you did update.
Here.
Okay.
No, I did not update. This was one example. This was upsert example anyway. My previous insert is gone. But let me show you how that insert would look like earlier. So when you do insert with this kind of, okay, where did that go? Okay, let me show you with this example here. Okay, so this one I'm going to paste, but it is going to overwrite. But you see here, if this queen at yahoo.com was being created as a new one, let's say this is new, okay? I'm going to show you this, new. Okay, here, first name has a value allocated. For last name, we did not allocate anything. Is that clear? Mm-hmm. Queen new, for last name, not even allocated. So don't look at that as a null. The allocation itself is not there.
Yes.
Okay. Now I'll say delete first name from users where email ID is equal to email underscore ID, obviously. I'm typing on the last row. I cannot do anything to bring it up until I finish typing. So that's because of this. Okay, so here, now what happens is okay, I was expecting that queen underscore new to disappear completely, but not yet. So you have to understand that it will drop the partition if all the columns are gone, all the other columns, rest of the columns. So there is a scenario where it will drop the partition also. Mm-hmm. Okay. To recreate, I don't know how we got there. We have to go back and look at the whole video.
Okay.
Okay. So then the most destructive way, destruction is always easy, right? So how do we clean up this table? Just do truncate. So here the syntax, you can do truncate table name, or you can just do truncate users. It just drops everything.
And it removes that folder also, or the folder will be there?
Folders will be there. You know, folders are handled by compaction. There is a different process.
Okay.
So we can look at the data, sales, users, and then look at that. It still does not have any files.
And do we have something like flashback, something in Cassandra? Nope. It's gone is gone?
No. Yeah, gone is gone. Flashback also depends on your commit. So that's a transaction control. So TCL itself is not there here. Okay, obviously all the data is gone from everywhere in the cluster. Okay, so still flush did not complete. So you don't have any data written.
Yeah.
So earlier I was showing you there was only backups folder. What is the snapshots folder now?
I think in Cassandra YAML, right? If you keep auto snapshot on true, you get this folder. So
why does it get this folder? What did you do to bring that folder?
Sorry?
What did you do in SQL to get this folder created?
You truncated it, right? Just now.
Correct. You got it. So you got the point. So basically when you truncate, it does an auto snapshot. That's why it created that truncated folder there. Okay. So looks like on the second node, there is nothing. And also I need to point it to data folder. Okay, there it is. It's on the second node.
It will take backup?
Yeah, it does a backup with the truncate.
You remember we had one
parameter. If you look at conf cassandra.yaml grep -i snapshot. Auto snapshot is set to true. Okay. That's how it knows to take a snapshot when you do this kind of operations like truncate. And you'll be able to restore that truncated data using that snapshot.
Okay.
Some other class. Don't worry. So we got tables created. We got some data in there. We talked about insert updates, basic stuff, right? But there are some subtle differences we are trying to understand between what we know from the past and what we know now. So we talked about all of these options like inserts, updates, deletes, delete columns, and delete. You can do a delete entire row, but you just need to provide the primary key or partition key. So how does it keep everything in sync? Like, it is doing all those different stuff. It has to know what is up to date, right? Which column is up to date? You've been updating, inserting. So remember one thing in Cassandra, every single row, every single column, every single entry is time-stamped. So even though we don't see it, we cannot see it, there is a timestamp hidden with every single entry. So based on the timestamp, it knows across the cluster what is the current view I need to present when they do a select. So every single entry you make in the database, every piece of information like a column, partition key, everything has a timestamp along with it. So across the cluster, when you're doing updates, you're doing inserts, you're modifying upserts and all that, that piece of information which you're updating, that will have a timestamp. Whatever is the current timestamp, that's what is presented back to the client. So Cassandra maintains multiple versions of each value, and the latest version will be returned to the client based on this timestamp stored along with the value. Okay.
Okay, like SCN, something like that. But of course, we should not
SCN,
compare.
well,
we should not
SCN,
compare.
no, it's good to compare. SCN is at a transaction level.
Yeah.
So here you have a timestamp for every single piece of value you stored, updated, deleted, inserted. Everything has a timestamp in it.
Every entry in this table with partition key, that entry means nothing but one row, right? So that one entry will have same value, right?
No,
all the columns, or
no,
it will
look
have
at the third one. Look at the third one as different timestamps.
Okay.
Yeah.
So
I mean, okay. it's a piece of code done in a very intricate way. So they have their own way to manage these timestamps. You don't need to go beyond that. So what we were talking about is why Cassandra keeps all these timestamps, which we don't see, right? Obviously, when we delete data, that's how it looks like. So this particular view for any RDBMS guy will look like very odd. Why? You don't have those two columns defined there, set it to nulls, and they're still there, right? Well, this is NoSQL. We don't need space allocated. We don't. In the structure itself, there's nothing. So this is where your flexible schema comes in. Structure itself is flexible. Basically, even though you defined that there are 3 columns in your table, you might have some data missing. And what do I mean by missing is not the data value is not null. It is not there at all in the allocation. So any deleted data, which is deleted column, deleted value, is tombstoned. And we'll talk about tombstones later. But once the tombstone is put, it's like a soft flag for Cassandra, say this data is deleted. And then later during compaction process, that gets removed from the storage itself. Okay. Because you know it's a distributed database and every single piece of value is also has its own timestamp attached to it. It is always important to keep your cluster, all nodes, in sync with some kind of time synchronization. And the protocols, 2 famous ones are NTP, Network Time Protocol, or CRONI. CRONI is used mostly in Linux 7. So make sure your cluster nodes are running some kind of time synchronization And if you have the synchronized time, none of the nodes are away, like, one of the node is 2 seconds behind, then it will cause issue. Okay. So time synchronization is important for your data to be properly there. SS tables, I talked about SS tables. These are the physical storage, how the files are stored on the disk. Whenever you delete data, it is tombstoned, and you can see there are a bunch of entries here tombstoned. Either they're at column level or the entire partition is tombstoned. And as I said, during compaction process, which is like a garbage collector process in Java, all these SS tables, they look at some more settings, and they drop the deleted data. That will be gone. All those tombstone data will disappear. Once the column is deleted, once anything is tombstone, it will never be returned with a select statement. Even if you write select statement, even if it is already there, you cannot see it. You cannot retrieve it. Only compaction process will delete it later. You remember deleted data earlier? So when you delete, Cassandra just puts a tombstone on it. Okay. So what it does, it just adds a tombstone. Cool.
Okay.
And when you delete a partition, it tombstones all the entries related to that partition. Once it is tombstoned, you will never see the data with select statement, or there is no way to retrieve it. And it will wait for compaction process. When the compaction happens in the background, all the deleted data disappears from the physical storage also.
Okay. So compaction is nothing like a rebuilding of the table.
Well, it is kind of rebuild, but not. Yeah, it is a rebuild. Actually, what it does is it takes multiple SS tables and verifies there are some rules to do it. Then it merges all those SS tables into a new SS table. While doing it, it will also see if there are any deleted data needs to disappear. That will also disappear from the SS table.
So if it has 1 million records and one SL table, sorry, 10 million records, let us suppose, and one SS table is like 1 million records. So it will be maintaining 10 SS tables, right?
Yeah. So remember every flush with your. Okay, let me go back to this screen here.
No, I understood. I'm just correlating.
Yeah. So every time it flushed, there is a set of SS tables. Okay, so they will be merged in the compaction process into a new SS table, and it will drop the old existing 10 or 15, whatever you have, small or big, doesn't matter. It merges the existing SS tables, cleans out, any deleted data will be gone. Any duplicated data, because you have multiple time-stamped values, only latest one it has to keep. So it will do all that.
Okay, got it.
During the compaction process, it's a node to node, meaning every node needs to do compaction.
Okay.
So tombstones are purged during this process. Let's look at a few more examples of what we can do with CQL. So let me put it here. Some of this I'm not really, we are all experienced DBS. I don't want to really type this command, show you what is happening in the background. Okay. So you insert some data, and after some time you realized you need a column. You can add a column, no big deal. I'm adding year of birth column, and then there onwards, all the year of birth also you can insert or update or upsert, whatever you learned so far. You can drop the columns based on that syntax. Okay. Now this one is important. So we have comments even in Oracle, and Oracle supports table level comments and column level comments. Let me show you a describe users and how does it look like. So you see, describe table will show you all the columns you have, and it has that Bloom filter settings and all. Some of this information is not important for you. You can see the primary key information is written here. Some of this information is more like, how do we do the compaction? What is the strategy? Whether we are compressing data or not, CRC checks, local DC repair values, default time to live, so on and on and on. So these settings I'm not discussing right now.
So these are like attributes.
Attributes. You can say every table has these things at the table level. Okay. What we want to see is there is one comment column here. And how do you set up that comment? Let's say in Cassandra, comments at column level are not supported. They're supported only at table level. So how do you do the commenting is just basically this is the syntax, copy. I'm just going to run, nothing big. Okay. So once you comment, anybody who is describing the table can see that comment here. Okay. You can actually overwrite your previous comment with update by just doing that with. So because you're not updating a column within the table, right? This is outside settings. All you have to do is that with keyword and your syntax is displayed here. Updated, and then you can save that. With is the keyword you use to set the attributes of the table. As you said, as you mentioned, these are attributes. So here is your updated comment. Internally, this is nothing but on the system schema, it is running an update statement. When we get to this collection data types, generally what happens is we talked about SQL supporting like advanced data types, which come from like Java side of it. Like any of these languages will support tuples, sets, maps, all those new kind of data types which they want to use. You can basically do two things, right? One is as a DBA, you create the structure and you forget about how to use it because your Java developers will know how to use it. Or you understand the basics and you know how to use them and what not to use. And then you go guide them and say, hey, you know what, don't use this, this style of coding or use this style of coding. So collections, tuples are like, something new and we generally don't try to use them. But obviously application requires them. So they will come to you with a table requirement where you need to provide them these data types. So let's understand those. There are also UUIDs and time UUIDs. Like, once you're good with the basic stuff, you can look at those. There are also frozens and inets. Inet supports storing IP addresses, network elements and stuff. So let's see what are these collections, because these are not your standard type of data types. What you can do is, there are three collection data types we are looking at here, all three of them in one slide, so you know the differences between each of those. Okay, so let's talk about set. Set is group of unordered unique elements. So you cannot have duplicates and they will not be ordered. Whatever you insert, it will save it that way. And then it doesn't go bother about like, altering the storage or anything for that. And when you're selecting, they will be returned in a sorted order. Okay, that's the behavior of Java. And the handling these data types, Cassandra itself doesn't have its own implementation. What they do is they take whatever is in Java, just implement it as if there is an API, and then Cassandra can use it. So one new word here you have to always understand and recognize whenever there is an overhead. Read before write. Okay. So for example, when you do an update in Oracle, let's say update users where user ID is 10. What Oracle has to do is it has to first verify that 10 exists or not, right? That is called read before writing, because it doesn't blindly update, right? it has to go read the data and make sure that row exists. Only if that row exists, it will update it. So in Cassandra, we talked about this yesterday, remember? When you're doing an update, it doesn't have to check whether that value exists or not. All it does is it converts it into an insert and then stores the data. And the merging of existing data, if it exists, or if it does not exist, it's a new data. That all happens in the background with the compaction, SS tables and all that stuff, right? So Cassandra does not have this overhead of reading before writing. Even if you do an update, it just does an update. Who cares whether the data exists or not? It will just make it a new data. So read before write is an overhead. Remember that. We don't want to do this if not required. So you will try to avoid anything in red here, which says read before write overhead exists here. So in the set operation, like whenever you're doing update, insert or something, your set will not have read before write overhead. Compared to the next one, which is list, I have put this in a red color here. This will have a read before write overhead. Remember that. Okay. So what does list do? Group of non-unique elements, meaning you can have duplicates. Handle element using its index, meaning you can say, okay, I have 5 elements, give me the 5th element or the 4th element, which is not possible in the set because set will just give you all 5 elements. And list as a overhead of read before write, because you're now allowing API to say, give me the 4th element. It has to first figure out if that data exists or not. So it has to read before writing data. Same way, that's some properties about the list. Now map is a group of unique key value pairs. So far what we talked about is having 5 elements. They're individually 5 elements, but map can handle key value pairs. Let's say, for example, you have customers and you want to store their multiple phone numbers. You have mobile 1, mobile 2, home, office, let's say, I don't know, whatever, lab. There are 5 different numbers and you want to store the phone number along with where the location is. So you will use map, and this can give you the key value pair storage and handle each pair individually. Let's say, for example, you want to change the home phone number. You don't have to change everything else. You just handle that particular pair. Okay, so that's the map. Out of this entire slide, I just have to give you that caution about read before write overhead. So wherever there is a read before write, that's an overhead, because every single entry you are touching, it has to read it before writing back. Okay, so that's a read overhead, and you will try to avoid such scenarios if you can. Now, how do you use these collections is pretty straightforward. So each of these set, list, and map, they're indicated with different kinds of brackets. So if you look at this, we're talking about SQL collection type set. Let me increase, let's say, to 150. Okay, so this should be much more clear to read. So if you have to add a new fraud alerts data type, fraud alerts column with a data type as set, and inside set, each of the data type is text data type. So elements inside that. Okay. So what you're essentially doing is, we had our users table yesterday, and what we want to do is to, let's say, if at all I see a fraud alert, where do I send that fraud alert? So I want to send it to like a text message, or I can send it to multiple email addresses so that user is notified about some fraud happening. So let me go to the SSH here. I'm not going to copy paste each and every command, but just to show you, we can copy paste. Okay, hold on, that was a mistake. So we just have to do host name, and then we are connected to our Cassandra, and then describe users. Okay, it's in the sales key space. So remember, you can do this, or you can say use sales, and directly you can say describe users, which is in that key space. So let me clear screen and describe users. And now you can add this new column, which is a fraud alerts data type. And you can see, for example, select star from users. You will see this new data type added to it, fraud alerts column. Okay. And data type is set data type here. There are no entries, obviously. We can make some entries using this. So if you take this and copy.
1 second.
Yeah, go ahead.
Fraud alerts, you added the column, but it should come in the last, right?
Yeah, so that is another thing. How it presents to you or how it stores inside the database is different. So it always, so this is your primary key, which is in red color. You can see some color effects here. What Cassandra does when it is presenting it to you in SQL, this will order the remaining columns in the ascending order based on the column name.
Okay, got it.
Okay. So one more thing we have to remove from our head is your storage. Oracle data types, like, when you add a column, it always goes to the end. That is because you're tying your structure so strongly. So it has to follow all those rules. And remember that NoSQL does not have that rule. So your structure is pretty independent and it is a flexible architecture. So internally, it will be storing these as convenient for the storage. Okay. So don't expect this to be in a specific order. Now, you always know that we are not going to write in the application. It is not suggested to write bring all columns using select. Instead, they will actually give the column names. And that is the perfect architecture. They're not supposed to do select star from anywhere. So they have to specify which columns they want. Okay. Now, going back to set data type, how do you interact with it? You basically put them in this special brackets here, and then you can specify multiple values for that column. So when you do this insert, I'm just going to run through a couple of examples here, and then we do a select. Let's see how the data is stored. You can see this particular fraud alerts is not a text data type. Remember, there are multiple elements in that particular data type, and Java will allow you to, pick up each element and do something with that. So if at all you have an application where if you saw a fraud happening on this account, you can send a email alerts, or let's say one of that can be your text alert going to this particular person. Okay. So these are not your traditional int or number text data types. These are a little bit more advanced data types where you can have multiple elements stored inside the same value.
Okay.
So, so you saw how to insert values. So this is how you update values. So if at all you already have some values, you can add 2 more entries to the same record. Same column, you're adding 2 more elements. If you take that each entry as an element, then you're adding 2 more elements. Syntax is just by doing a plus sign. Okay. Same way you can remove the existing values. Like if you are changing, somebody is coming and saying, hey, you know what, I don't want alerts going to this email. I want to remove that. Then you can just do a minus. Okay. So you understand this.
So when you are, when you are adding that fraud alerts, you are mentioning it is a text, right? Data type?
Well, so this is how it is done. Like it's a set containing text values.
Okay, set.
But you can say set containing numbers, set containing some other data type here.
Okay. So in our previous slide, when you are explaining, first one is a list, next set, right?
No, set, list, and map.
Oh, set, list, and map. Okay.
Yeah. So we'll follow the same order. Okay.
Okay.
So we're talking about sets here. And so here you're able to add new elements and remove elements. And same way you can remove all elements by just doing, this is similar to setting it to null. You're actually removing all elements from the whole entry you have. Okay. So remember yesterday I was telling you setting it to null means still it has allocation, but if you do delete, it will delete that allocation completely. So setting it to null is not equal to not having allocation. So there is little bit of understanding there. Even in Oracle, you set it to null, it actually doesn't remove the allocation. Oracle does not have anything called remove allocation for a column, but Cassandra has. So do you remember this slide? I was showing you, like, you know, with the blanks here without having column entry for allocation. But just know the difference between this one still has allocation. This one does not have memory allocation. This deletes the allocation. Okay. I know this particular topic is not my favorite, but we have to go through it because, you know, eventually you'll have your somebody will come to you with a development team requirement, and then you'll have to end up supporting it. Let me do one thing here. So you can see sets, we are going to use these brackets. Okay, so let me say T. I'm not going to keep this, but sets using this. Okay. So you notice that, right? Then let's look at lists. So lists are exactly similar. They have read before write overhead. Remember that. And all the other properties about which one accepts unique values or not. So here I'm showing a different example where you have multiple phone numbers for each user. And what you can do here is you just say it is a list with text data type. You can make it a number data type, and then it you just cannot store these dashes, but you can have it as number data type also. And when you use list with text data type, this is how you're going to handle your elements. You see these brackets? In those brackets, you specify multiple elements. This is element 1 and this is element 2. Okay. So you can take the existing phone numbers and add elements to it by just doing a plus. And you can see you can do it in both orders, like either you do before or after, doesn't matter. And then prepend or append does not require read before write. Remember that. Okay. But when you're doing a replace using the element specific element index like this, you want to take the second index element which is at the second position, you want to replace it. So that's what you're doing with this update operation. Replaces third element. You can see 0, 1, 2 is the element index. So it replaces the third element, and that will require a read before write. So there is a small difference here with the update. You're appending or prepending, it doesn't require read before write. But when you're doing a update like this to replace existing elements using the element index, then it requires a read before write. So you can remove the existing elements by just doing a minus, and then you can set all of them, set it to like a null, or remove all elements in the entry, or you delete the entire allocation by doing a delete. Okay. So then map. Okay, so if you understood set and list, so what we did with the set and list, why I chuckled there is because these are complicated topics. What we did here was we use this brackets to represent the set. And then let's say what did we do with the list is we use square brackets like this. Okay. Now, if you understood set and list as single elements, map will allow you to do key value pairs. So it's just multiple key value pairs in a collection. So map, you will define it this way. So just to keep it easy, what I did is both of them are text data type. Your key and value, both of them are text data type. But you can have like a text data type for location, and then you can have a number data type for your phone number. So all you do is just wrap it with map, and then you're saying secret questions is nothing but a map data type. Secret questions is, you know, as you understand, like, you know, any website which want to ask for multiple secret questions and answers, that is what is used for validation, and also when you want to retrieve your password back. So that kind of scenario where you say, okay, my question is, what is your favorite alphabet, T, and what is your favorite number is the second question, and number 8, right? That is what that particular user has provided. Only thing here is, you see map almost looks like set by using that curly braces, but only difference here is you have key value pairs. So there are two entries in the each element.
So you are storing like two values as
we can actually
comma.
we can actually see how it looks like, right? If we run this, you will go here and run it. Well, obviously first I need to add that
column.
Mm-hmm. So we add that column and then we run this thing again. We insert it. So let's do a select. You see how the secret questions will be stored inside. This is only a look. We don't know how it is stored, right? It uses some specialized Java formats. So then you can add more questions or remove questions, but you have to provide, when you're adding, you're providing key value. When you're removing, you only provide the key. You don't need to provide the value. Okay. And you can also delete a specific entry by just specifying which key you don't want. You can delete that particular key and the value is gone along with it. It's a pair which is stored. Or you just delete all the entries, all the column values. So that's how you handle your list, set, list, and map. And again, there is a note here. If you look at this particular slide, it says keep your collection small, meaning I cannot store like 2000 phone numbers in the collection. I mean, don't store. It allows you to store, but if you get a requirement to store 2000 entries per user, then don't do it that way. Then have it designed as a proper column inside the table and keep it in this format. Like, we discussed about the time series data. So this way, okay? Because these are not collections. Collections, you want to keep them small, like, where you have multiple addresses for each customer, you want to keep it that way. You don't want to, like, use collections for, like, what if the entire city, how many phone numbers are there, right? You don't want to keep it in a collection. So let's see another data type called tuple. Tuples are a little bit more advanced topic, and because key value pairs only allow you to store two things. What I'll do, I'll just drop the previous all columns we added, which are all set and list and other stuff. We don't need them anymore for our discussion. So what we'll do, we'll look at the tuples slide and talk about them a little bit. So this is also collection data type. Now what happens is it allows two or more values to be stored together in a column, internally stored as a single value, meaning when you're retrieving, the entire tuple comes out into the memory. So if this is how it looks like, tuple column name, you say it is a tuple with multiple data types in there. And whatever you're specifying here, you're going to store the internal elements in that structure, okay? We'll look at some example making it easy. Think of it as like key value pairs, but with more advanced handling. So how you specify here is, I have a tuple which is 3 text values stored together. Okay. So if you see my home phone number is this. And when should you contact me here is, this is my primary contact, secondary contact. What if it is, what if somebody is not picking up their first phone, you call the second phone, and look at this one where I have, if at all you need to send me alerts, send it to this phone number and send it as a SMS alert. So tuples have a little bit of what you say, this frozen keyword. There is a special keyword here, frozen. We saw that in the data types when we saw the SQL data types here. Frozen is not explained, but it is on this slide here. If you see this one, frozen. Now, what it is basically, you know, once you write it, you're saying, okay, I'm not going to modify the elements inside. So I'm just going to keep it that way. Okay. So here what you did is you stored your home phone number as a primary contact, 3 values, that's the tuple. And then you can say it's a frozen set of tuples. Okay. This is multi-level confusion in one place. So please see that I'm using a frozen data type. It's a set, it's a tuple containing 3 values. Okay. If you don't understand, forget it. Don't worry about it.
No, in real time, really they use this much complex data types?
Yeah, come on. If they can use MongoDB, they can use this.
Okay.
Yeah, MongoDB is much more complicated if you think as a RDBMS DBA. MongoDB is nothing you can fit into our memory.
Okay.
So, yeah, they use it. Definitely they use it. Why I'm showing you this is somebody will find this somewhere, come to you and say, hey, I want to use this. So at least you know that it exists. Okay. So anyway, there are like a frozen set of tuples with 4 different data types, and that is another example here. And then drop is the easiest command to explain. I'm just dropping that column. If you want, we can spend time talking about drop. Forget about tuples. Yeah. So then we talk about user-defined data types. This is there in every single database. Basically, you can take all your existing data types and you can use the sets. Whatever we learned so far, we can take all that and make a custom data type and then put it in a column row format. Okay, so SQL user-defined data types, UDTs, these exist in Oracle also. These are reusable data types. You define a data type using combination of existing data types and say, hey, you know what, every column in this row will use this, will be of this data type. And then whenever you see this internally stored as single value, let me say, for example, here. So at the storage level, Cassandra is just treating it as a single value. Okay, so that's what it means. Just it's storing something, and then when it reads, it is going to read the whole thing. So whatever it stored, and then it brings into the memory. While it is bringing into memory, that Java is doing its magic to convert it to the data structure in memory. So storage wise, it is just a big string, let's say, right? So this one should be easier to understand because user-defined data types exist everywhere. So basically what I'm saying is, what is a postal address anywhere? Like you will have a street number, what is the street, city, state, county, country, you can have county, zip code, all of that together is something called postal address. So you can just create a postal address by just doing this. I don't think I have any data types which are user-defined types. So if you clear screen and then describe types, you don't have anything in the database right now. I can just copy paste this code, which is basic creating a postal address data type. And then you see that. Then you say describe type postal address. You see that it looks like a table. It just does not store any values. And then you can define a table with postal data type. Okay, read a little bit about that frozen. What does that mean? And it's kind of Java terminology. So if you do a describe users, you will see this data type attached to it, like address here. Again, you see the column order. It will follow that ascending order of the column name. And you can insert data using this nice format. And then when you look at that, it looks like select star from users will look like that. So what we are doing here is we define the address data type, and then we are saying my address column inside the users table is of data type postal address, which we defined as a type. And then that is, you need this keyword. Without that keyword, Cassandra will complain.
Okay, now I'm clear.
Yeah,
I got it.
yeah, cool. So, and when you do insert data and select, it will look like this. So this particular string.
Okay, to use the frozen user defined data types, you need to specify the frozen keyword.
For adding it to the column, when we are adding the column of that data type, you need to specify that it is frozen.
Yeah, now understood.
And then it stores as if it's a long text like that.
Got it.
Okay, you see how we used it by using this curly braces. I just put like, it's almost like your key value pairs, remember?
Yeah.
Yeah, so that's the format. You see the city is the key, Orlando is the value. Instead of doing key value pairs using your map, you're doing it this way.
Yeah.
This is a collection of tuples actually. If you translate it that way, it's a collection of tuples. Only thing is you define the structure using that create type. It's a user defined data type. So then you select, and then so here because it's a frozen data type, you cannot update. You can only replace it. So what you do is just you update and then provide entirely new entry here. So that will become a new value. You have to provide the whole thing. Okay. So that's the reason you're saying here internally stored as single value, meaning you are going to handle it also as a single value. So for example, there is a box of data here, and then it has lots of bunch of different things in there, right? This whole thing is handled as one element when you do a frozen. And for some of the data types, you have to freeze it. Otherwise, Cassandra cannot handle it. So every time you read, it reads this whole thing. Every time you write, it writes the whole thing. This is where you should start knowing how not to use stuff. Okay, so because we are from Oracle side of it, we know sequence. We have a sequence, nice sequence. You create a sequence. It just runs through 1, 2, 3, 4, 5, 6, and so on. Use it for your primary keys. Very good. In Cassandra, there is something called counters. Do not use it, because if you had a sequence on a single database, even if with 4 instances as a rack, sequence does not create any problems because it's not distributed. But in a distributed environment, sequences create a lot of problems because you have to have inter-node communication to say, hey, you know what, I generated that sequence number, don't generate it again. And if you had 10,000 nodes in Cassandra cluster, Insta Cluster is the company which actually tested with 10,000 nodes of Cassandra, and it works like charm. Just like our 3-node cluster, 10,000 node cluster is also perfect. It doesn't cause any issues. So distributing
it doesn't cause issue for what?
Oracle with after 4 nodes of rack, you will have lots of troubles.
Yes.
Right. So I'm saying Cassandra in a single cluster with 10,000 nodes. Just imagine. It's a distribution of that much range. Issues like this sequences will not work in a distributed environment.
Yes.
Okay. So counters are there. They count, but don't use them for your sequence kind of replacement. Okay. So let's talk about water counters, and you will see that, you can use them. They're not accurate. Do not use them for replacement of sequences. So you have an Oracle database bringing those objects here. Oh, we have 4 sequences. Let's create counters is wrong. So here onwards, you will see some approaches which are wrong. Okay. And so you need to know what not to use, and your developers will come to you and say, hey, let's create counter because there is a sequence over there. It's a wrong approach. Okay. Now, counters in distributed environment always creates more challenges than keeping them in sync. So Cassandra has counters. Do not use them for reliable sequence numbers or something like that. So just understand how to use them for what purpose. Counter value is stored in mem tables, commit logs, SS tables, just like your regular tables, distributed across several nodes in cluster, same as everything else, right? Counters are incremented and they can be also decremented, okay? Tables with counters should only contain partition key and counter columns, nothing else. Meaning these you will be using for just to keep track of, okay, how many transactions happened today. So you will have transaction date and then counting numbers. Let's say how many products you sold, how many transactions happened, how many unique users came to your site, something like that. But they're not accurate, okay? So word of caution, they're not accurate. Now, how do you use them? Pretty simple. They
One
have
quick
their
question.
own.
So in Cassandra, we have sequences and counters, both.
No, Cassandra does not have sequences.
Okay. But counters is similar like sequences.
No. Implementing sequence-like thing in distributed databases is impossible.
Yes, I got that
Counters are
point.
not accurate. Do not use them as if they're sequences.
Okay. But the functionality is similar, right?
Yeah, that's what we feel. But once you dissect and see, it is not same.
Okay, go ahead.
Yeah. So how do we use this? Is like, as I said, remember this piece here, last one, which is tables where you want to store counters cannot have any other columns, only your partition key and counter columns. There are multiple columns, but all of them are counters. So here is how you create a table. Like say you're keeping a web page statistics table and you say web page name is this. And I have counters, like say how many views for the web page, how many unique visitors, how many likes we got, how many dislikes we got. Okay. So imagine this is your YouTube video. You have video ID and then you have that bottom here. Let me show you YouTube. And then you see this bar here, which has likes and dislikes and stuff. See how many likes, how many dislikes, and how many views and which date it was published. So some of this information, you can use counters. But as I said, they're not accurate. Okay. So here for this web page stats, what we are doing is, okay, insert into web page. And let's actually work with this so we can get a little bit more feel about it. So what we'll do.
So can I know like YouTube is on Cassandra?
No. YouTube does not use Cassandra. We don't know what they use, but obviously they're not on Cassandra. Okay. Google product. They have their own researched products. Yeah, they don't use, they only create. Okay, so insert statements are not allowed on counter objects. Okay, use update instead. You can see the first error there. We cannot insert into this table. Okay. So what we do, we update it using this. We update it and okay, let me do a select star from website statistics. And you see this. After you do update, okay. So this is another error you should notice. So when I did a insert, it is saying inserts are not allowed, use updates. When I do an update, it says in the counter value, you're setting it to 0. It says you cannot set, you can either increment or decrement. Okay. Make sense? counters cannot be assigned a value. They can only be incremented or decremented. That's what he's saying. I'll show you how to do the actual usage. So what I'm doing here is update the table, set web pages views to existing value. It could be null. I'm just adding a 0 to it and then setting it. So let's see what happens when you do this. Okay. So basically now it worked, no errors. And when you do a select, you can see what it did inside. It just made that entry of home page and it set the web page value views to 0. Now on, you can keep on incrementing it or decrementing it depending on your requirement. Okay. So another example like that, where you're setting the web page views to web page views plus 0 for which page, like products page, okay, and sales page. So you can do these two updates and then you'll have 3 entries in your table. So let me do a select star from web page stats. Okay, so this is what it is. So if you see, now you created 3 entries for your web pages, and now onwards you are going to use some update statements to actually increment or decrement these page views. So then what you do is, okay, now that you have your entries done, what you're doing here, you have a web page stats table. You're setting web page stat view, web page views equal to web page plus 1, unique visitors equal to unique visitors plus 1, likes equal to likes plus 1. So you're going to increment all these values for home page. Okay, there are 3 pages you created, but only for home page you are incrementing all these values. So if you do a select, you can see the difference now for home page. This one.
Okay, this one. Okay, page. So in like Oracle, we are not telling like next sequence, next val.
You just increment by the number. So let me take this same update. Okay, I'm just going to, what I'll do is I'll just say notepad. Let me bring this notepad here. I'm just going to build a live query here. So what I'll do is, I'll say, for example, I want to increase the number of views for my web page by, let's say, 100,000, right? You can do this because you can increment. Okay. Hold on. What happened here is the comma. This comma is not required. Okay, so I run that and I do a select star from, you can see what happened. So you see that increment from 1, it became whatever the new number is. You can increment by doing this particular line.
Then if it is not incrementing automatically, why we should
no, from your application API, you're going to send this update saying, okay, I got a new view. So you can send an update.
No,
even on sequence, you're not going to do auto increment, right? You will call that sequence.nextVal.
Yeah, that's it.
Here it is not nextVal. Here it is like you can set the value, but increment it. You can increment it by 1, you can increment it by 10, whatever your application logic is.
Mm-hmm.
So counters are different because now you can have 10,000 nodes. Every one of them can increment by 1, right? So you got 5,000 views. Now 5,000 nodes can just say increment the existing value by 1.
Mm-hmm.
They don't care about what is the value or what is the new value. They just say increment.
Okay.
And implementing that is not difficult in a cluster. You can do research later on how counters work in Cassandra, because then they have a counter cache and all that. There is a lot you can do on your own. You don't have to wait for somebody to explain, because if you look at this, right, Cassandra YAML, grep for counter, I'm sure you'll have some information there. See counter cache, how much megabytes in memory you want to keep the cache, how do you want to save that cache, how much period you want to save it, stuff like that. How many concurrent writes can be done for counters. So just like you can increment, so here we did one increment, right? So we did the increment of like 100,000, whatever we did. We can also decrement by doing a minus, very simple operation. And let's say, for example, I decremented by 5,000, right? So you remember only Cassandra counters only allow you to increment or decrement. There is nothing else you can do with it. Okay.
Yep, got it.
So that covers counters. Let me see if we covered all the scenarios for counters. I think we did. So this is just a different way of incrementing, like, you know, different values I was showing for different columns. Got some dislikes, unfortunately. And then you can do decrement of likes also. It's JavaScript object notation. So JSON is like a XML or data exchange kind of format. And Cassandra, I told you on that day that Cassandra has a wrapper. It doesn't support JSON, but it has a wrapper which can provide you an interface to interact with Cassandra in format of JSON. So what you do here, let me close this. Okay. So JSON is basically, it's a keyword here. You're just doing select star from users. So instead of doing that, you just say select star from JSON users. Actually, let me run a query on the, so you do select star from users. Okay.
So JSON is a data type?
No, JSON is a format.
Okay.
So what you see here is your existing data, right? And then all you do is your developers want this data exposed as a JSON format. They just run this command and it gets formatted. The output is formatted to JSON format like this.
Okay.
Okay. So I can put it on a notepad and show you the formatting, how it looks like. So what it does is it has 2 rows in it, and both rows got converted to whole JSON formatting. So you can see email ID became this. It's all key value pairs. Address became this. And then there are 2 entries here. So first entry is here and the second entry is here. So you can see this is a JSON format, can be consumed directly within their Java code or JavaScript code or Python code, whatever code your application team is writing. So let's talk about, compare it with Mongo, okay? Mongo does not store data in rows and column formats. It actually takes this and stores it as a binary JSON. So that is called BSON, binary JSON. Binary JSON, that's what is BSON. And this is in MongoDB, okay. So it's a pretty simple interface where you just did one keyword here, JSON star. How they implemented this? Very easy. Java has a JSON wrapper. So basically they give the Cassandra data to that wrapper. That wrapper converts it to look like JSON. That's all. Nothing much they have to do. So you can do like, you know, select email ID, comma last name. But show me the output in JSON format. So like this, instead of showing it like normal column row format. Mostly your API, which is like application developed API, they know how to use JSON very easily. So they don't have to convert their data into another format to submit to Cassandra. They can just submit their existing JSON format to Cassandra and it will be able to handle it. Same way, they don't have to ask for rows and columns. They can ask for JSON and Cassandra will be able to give the JSON. So this is when your developer wants to retrieve data in a JSON format. So let's look at one example where if a developer wants to write data into Cassandra, how can they send it as a JSON format, right? So they have this JSON document which is in their application memory. All they have to do is insert this data into the Cassandra table. They have to put this JSON keyword here. Okay. So when you do this, select star from, insert into users, we have this table already, and you do a select star from table in a normal format, you see that that JSON entry got pushed into the Cassandra database.
Yeah, good, nice.
So it's basically one keyword here called JSON. Okay, does Cassandra support JSON? Yes, it does. So your client community, your application developers, they can just use that keyword to send and retrieve data in JSON format. For us, as DBS, we don't have to worry about any formatting, any storage. We don't have to worry about that because it's just a keyword. It is a wrapper written around the Cassandra driver.
Okay.
And Java provides that driver to Cassandra, so no big deal. Whenever Java comes up with a new JSON wrapper, these people have to just implement the API, and that's it. There is nothing new they have to do.
Okay.
Okay. So pretty good. Like, you can do updates and stuff also with JSON. All you do is send a document as if it is update, and then Cassandra will just handle it like we saw so far. Whatever we did earlier, it was doing that. So if at all you're deleting data, why do you even partition it? Tell the database that you delete it at certain time and it is gone, right?
Fragmentation.
No fragmentation. Cassandra has compaction process to clean up the fragmentation. Yeah. So what Cassandra offers is there is something called time to live, TTL, or data which expires on its own. So data with time to live is one topic we discuss. What happens with time to live is you take a piece of data, whether it is a column level data or it's a row complete partition. What you do is you specify time to live. This can be done with a transaction, or you can set it up as at the table level. And then when the time expires, let's say you want to keep the data for 2 days, let's say, right? There are a lot of places where you keep the session information. So session information, every time I insert a record, that record should exist only for 2 days. After that, it is invalid. Okay. What you do is you set up time to live. At the end of 2 days, Cassandra notices that, oh, this row is expired. It will mark it as tombstoned. So we talked about tombstones earlier. Anything deleted from Cassandra becomes a tombstone. And later on, when the compaction runs, it gets deleted from SS tables, right? Now, with TTL, you can set up TTL at the table level, or it can be done even at the column level. Okay. Now, default time to live, you can set it up at the table level. With the column level, you have to set it up with every transaction. So like say I'm inserting data, say this particular column will live for this long, that column value. Okay. And then so how does this deleted data go away is based on the GC grace seconds, meaning once it tombstones, your compaction process will not delete it immediately. There is another setting which will define on how long it has to keep it before it really deletes. But remember one thing, once anything tombstoned is gone, you cannot see the data anymore because it's almost like a delete. Okay. Instant delete kind. Okay. It just doesn't give it to the client. So let's look at how this is done. Okay. So first thing I will do, I'll just go back into the table and say, clear the screen, describe users. Okay. What I want you to notice is there are two things here to notice at the table level. So you see the first highlighted value, which is default time to live, is 0. meaning it is disabled. And these entries are in seconds. So if you say default time to live is 20 seconds, you can just set it to 20. And then after 20 seconds, whatever data you're inserting after that, after 20 seconds, that will be tombstoned. You will not be able to see that data anymore. I'm saying after 20 seconds, data will be gone, but they will still live in the SS tables until that GC grace seconds is also passed. Okay, so that's an extra caution they have put so that compaction itself is not running too much overhead.
Then anyway, it is deleted, right?
Correct. So you don't want the compaction itself be running all the time, right?
Oh, makes sense.
You don't want to have that compaction cleaning out every second. So instead, they put that grace seconds, which will delay the compaction. It's a lazy cleanup. So you know that it is deleted. You don't have to clean up right now. It's already gone. But cleanup will be done like every night, every 2 days, every 3 days, depending on the grace seconds, it will do that cleanup. So it is not overkilling the cluster itself by just doing cleanup jobs. When it runs, it will honor this grace seconds and not touch the data if at all it has not crossed the grace seconds.
Oh, it will not touch. Okay.
Yeah.
It's like guaranteed restore point.
Well, there is a restore, but you cannot restore data. Once it is gone, it's gone. For Cassandra itself, it is, imagine it is not a checkpoint. Let's not call it checkpoint, but Cassandra knows when to clean up. So you're delaying the cleanup so that compaction itself is not overburdening the cluster.
But anyway, if you are defining 86,004, like 8.6 something.
I think that one comes up to like 10 days, I think, this one.
Okay, well, 10 days. But
yeah, by default 10 days.
But if this is very busy table, okay, and it got millions of records, and if it is like 10 days, okay, and in one day, if it is like inserting like 100 million records, then compaction, even that time also compaction is overloaded, right?
Okay, so so the compaction itself has 3 types of compaction. So this is called size tiered compaction strategy by default, but there are 3 types of compactions. So you can use time windowed compaction, size tiered, and there is one more type. So you then have to research which compaction you want to use and set it up for the table.
Okay.
Okay, so there are different kinds you can do. For each table, you can have a different compaction strategy, whichever suits you. Like say, for example, the one you're mentioning, most likely that will fall into the time-based compaction, time window compaction. So imagine every column has the timestamp. Every column will also have a TTL timestamp.
Yes.
So it's implemented inside. It's not an extra column. It's an attribute of each column.
Okay.
Okay. So TTL is a pretty interesting concept because now you don't have to manage your expiring data manually. All you say is, okay, after 10 days, this will expire and it will be gone. Okay.
So each cell.
Say. Correct. Yeah. Each cell, or it can be set at a table level. When you set it at table level, like here, let's say, for example, this one. So you see this default time to live is 20. Let's do, why don't we deal with this, right? Okay. We'll drop one column, which I don't like, alter table, users, alter table, users, drop this
How did you change it from users to users? Capital to small?
No, it was just a tab filling. It was doing it for me. I did not do it manually.
Okay.
It was just when you type this, right?
Yeah.
So something like that. When you say alter table, it knows that you're talking about a table. So you say, for example, this, it automatically converts it to small letters.
Okay. Oh, it's nothing Cassandra is case sensitive, huh? Like MySQL? Table names.
I think so. I never actually noticed.
Okay.
Yeah, no I think so. And then you can put your table names in double quotes, which you never want to do, like in Oracle. Don't do that. Okay, so let's change this default time to live setting for this users table. Okay, so I only have 3 columns now. Email ID is the primary key, first name, last name. I'll do alter table users. Okay, you remember I was talking about anything inside the columns is your regular syntax, but anything outside, which is a table level attribute, you'll use a with and then specify what is that you want to change. Okay, so I'm saying default time to live is 30 seconds or 20 seconds. Okay, cool. So now if you look at your described table, you see this set to 20 seconds. Okay.
So default is seconds. Okay.
Yeah, it's always defined in seconds. Okay. Now I'm just going to do a clear screen, select star from users. What I'll do here, just to play with this, right? Insert into users, and I have to say email ID, and then I will say my first name. Okay, and put it in this values. I'll say 1 at test.com. My name is 1. Okay, and then I'll put one more row just for fun, 2, and then select star from users. You'll see those 1 and 2 exist. Okay, these, and then I'm not doing anything. I'll just keep on doing select. You see that 1 disappeared already because of 20-second rule.
Oh, it's like a table level and it applies to each cell, everything.
Correct.
Column, every column and every cell.
Imagine it just applies to the partition key. The whole thing is gone.
Actually, this feature is awesome. Really awesome.
So remember, only problem is with this, your new DBA coming to a Cassandra project, they implemented time to live 3 years ago. Nobody remembers about it. And you keep seeing that data is disappearing.
Oh.
Okay. So that is yes and no. It's a very good option, but you should know that there is something happening there.
Yeah, but see, every weekend we do maintenance and we keep deleting like junk, like we have the attention for the customer, like packing data. We don't need on some tables, and we every 10 days.
Right.
Yeah.
Now you don't do that. You don't have any maintenance. It's all maintained. You just go home and do your weekend work.
Yeah, no, this is an excellent feature.
So anyway, there are some more examples here you can play with, but I think you understood what is a TTL and already likes it. So he's going to put TTL on every single table. Just for fun. When you see this lightweight transaction, somebody come to you saying lightweight transactions, please, this is red. So this slide should look like this. Let me make it this way so you will remember your memory. It should look like this. Okay. It is not lightweight, first of all. So remember what we are doing here is we are saying insert if not exists, meaning you are forcing Cassandra. Cassandra is the highest performing when you're writing. It just takes whatever junk you throw at it, it saves it. But now you're saying before saving it, check if it is there or not.
Okay, 1 second. Sorry, can you repeat again?
So Cassandra is very high performant write. Somebody comes to you and says, I want to do lightweight transaction. So just say no, first thing. So what is happening is that in Cassandra, you are able to run it as a high performant write engine, meaning you throw 1,000 million rows every second, it can save it. It will never lose data. You might want to just have enough number of nodes to handle the load, but it never loses data. So when I say that, what you're saying is, okay, write. But what are these things doing with the lightweight transactions, even though name is like that? What it does is before writing, please check that it is existing or not, which is like an extra load for Cassandra, meaning you're decreasing your transaction count to half. Every transaction, it has to verify if data exists or not. And some examples here, basically all it is like insert statement with this keyword. Same thing with update statement with the condition, if that condition is that. And somebody comes to you and says, hey, I want to write my code this way in Cassandra. You say, no, don't do it. Okay. So this is a bad technique, and I don't know why they call it as lightweight transactions, but that's the name given to it. Okay.
Yeah.
So we're obviously we talked so much about, how do we do this, how do we do that, one-line commands. Obviously we are a DBA, so we don't want to do it everything with insert statements. How do you load like bunch of data from different places? So SQL helps us in not only interacting with the database, but they have certain things we can do with SQL. You can see here in the SQL shell, within the SQL shell, you can say source this file name. It will run that SQL script. So this is to execute the script. Or you can do SQL sh, execute this command. It will run that command and come back out. Or the third option is SQL file, pass this script name, and it will do that for you. First, let's see what is our example. I think we are loading that SQL shell by running that SQL shell script. So we'll see some examples on how to do this. So whether you are in SQL shell, if you are inside SQL shell already, you can just do a source and the file name. And whatever is in that SQL shell script, it will obviously run that and create the required tables. Okay. Or you can also do, let's say, for example, if you go here, if you go to third node, let's say, you can do clear SQL sh. Host name is something you have to provide. Where do you want to connect, right? And then you can say execute equals to, you want to see describe sales key space. Okay. So this you want to run in SQL shell. So you can see it runs that particular command. It runs that SQL shell command and just exits from the SQL shell. So this is what I typed.
Okay.
You can see that highlight. Okay. So what I did is SQL shell connect to this particular cluster on this host name or whatever your IP address is. And I'm saying -- execute equal to, this is the SQL shell command I want to execute on Cassandra.
Mm-hmm.
Okay. Sales is your key space. So it is basically describing the sales key space and printing all of the things.
Okay. Got it.
Okay. Then you can also, because it's a shell command, you can also do this is grep key space. So you get the create key space command.
Nice.
Okay. So this is something to help with your scripting. Basically, you want to know how many key spaces are there. You can just do describe key spaces. Describe key spaces. Okay. Yeah. It's so this is basically, this helps you in scripting. So if you have to monitor or take each key space and do something with it from the shell itself. Okay. So let's look at that SQL shell files, how to execute them. Now this you can do a source and SQL shell file it will run, or you can directly run it from the SQL shell by passing the SQL script. So let's use this command here. So what we'll do, so let me show you what is in that employees SQL file. Sorry, I will do a more instead. So what this particular script file contains is basically it is using the existing key space, and then it is creating a table, and then basically a bunch of alter statements and insert into table commands. Okay. Basic script. But the problem here is we don't have this particular key space. use CAS demo key space. That key space is not there. If you want to confirm, what you do is go somewhere else and say describe this key space, right? It will give you that key space is not found.
Okay.
Okay. So what I will do, I'll just modify this file. I'll just say vi. Yeah, I'm just going to change this particular shell script. Instead of use CAS demo, I will say use CAS sales, because that is already there. Okay, like this.
Okay.
Okay. So then what I'm going to do now, let's look at if we have this employees table, right? We can say describe sales dot employees. And you can see the table does not exist.
Mm-hmm.
Okay. So what we'll do from here, we'll say SQL SH. How do we connect to the cluster? Using some host name, which is one of the nodes in the cluster, -- file equals, you generally you provide apps, OPT, Cassandra, wherever your file is, and then employees.sql. Okay.
Got it.
Cool. Simple, straightforward, like SQL plus. Okay. So it came back, no errors. No errors is good. So we go back and say, can you describe this table? And now the table exists. Because it got created through the script. Okay.
Yeah.
Now in the first window, I am already logged into the cluster. So I'll say sales.employees. And you can see the employee table. Okay. This all got created from our script.
Got it.
So no big deal. You have a script somebody provided, you just run it using the SQL shell, it gets created. If you need to create your key space even before this, you just take care of that first. Okay.
Sure.
Then let's look at one more option here with the SQL shell. Okay, so this is SQL shell description on how to use it. Now you definitely want to copy data in and out. Okay. So first thing I'm going to say, this is one method provided by default, but this is not a very high performing method. This will be slow, and also it will not work for million row tables. These are only for small tables. Okay. So just the direction of copy, it tells you from or in or out. Okay. Copy this table from this file. File contains all the comma separated values, or copy to file will be take the table and dump it as a file.
Okay.
Okay.
But we need to follow that columns, everything, right?
Yeah. I mean, it does some of the basic formatting for you. I'll show you the commands, how it looks like. But remember that this particular method is suitable for 1,000 rows, 2,000 rows. Not suitable for million rows. Your database most likely contains more rows, and you will not be using this particular command to copy paste. I can show you what is in that CSV file. It looks like this. So I'll say more US daily average temperatures.csv, and it looks like this. So basically it has state, city, month, day, year, average temperature stored in a comma separated file.
Mm-hmm.
Okay. If you, this is a little bit old file. If you want a new file, you just get it from this particular source. You can go here. They have a lot of source data from like weather data or other places. Like I can check if this particular link is still valid or not. Let me, because this was a couple of years ago, I got this data. So if they publish this, you can get it from here. See, temperature data files for specific areas, international sites, all sites, or so on. Okay. So this is where you get the data and then use it for your learning.
Okay, got it.
Okay, so you create the temperature table. nothing special, right? It has the temperature columns. We saw this before. State and city is your primary key or partition key. Year, month, and day are your clustering columns. Once you create this table, you specify where your source file, CSV file is. What you're doing here is copy into this table with, these are the column names in the table. Your delimiter is a comma because it's a comma separated file. There is a header inside the file. You saw that when I was showing you the file itself. Let me show you here. This is the header of the file. So you're saying header. Yeah, there is a header inside the file.
Yeah, so header is mandatory here. Okay.
Well, you can say header is false, right? There is no header.
Okay,
if you don't have a header, you just say header is not false. And if at all there are null values in the columns, then inside your database, those nulls will show up as -99. Okay, so you can specify what do you want to show as null, right? If you say null equal to -99, inside the database columns, if at all there was a null in source file, it will put -99.
Okay, if I don't want anything, then
I just open close.
Okay.
Yeah.
Okay, this is same thing like SQL loader, what we are discussing.
Correct. Correct. So again, remember SQL loader can handle million rows. This one will not handle million rows. So then you basically look at the data. It's nothing special. Only thing special here is that limit. You are just saying only show me 10 rows. If you want to load from the file to the table, you're using this from. If you have a table and you want to load it, download the data into a file, dump it into a text file, comma separated, you're doing it this way. You say, take the table, these are the columns, and you want to write it in this file using whatever delimiter you want. You can say whether you want the header or not. Header is true or false. And nulls will be represented as NULL as in the column value in the file. So one is a copy into the table, one is copy out of the table. Again, as I mentioned, you're not going to use this when you have like million rows. Okay. Now in the beginning, I don't know if you remember, I mentioned that Cassandra is a data store, and there are a lot of other things you have to learn along with Cassandra. So that we'll talk on the last session.
Okay, the tools.
Yeah, there are tools, not tools, there are complete softwares you might want to learn, not just Cassandra. So Apache Spark is one of them, and that's how you'll be doing your ETL. Okay. And DataStax Enterprise comes with a default integration of Spark. DSC, we talked about DataStax, right? So that comes with the Spark. But with open source, you have to learn how to integrate it. There are certain steps you have to do to get your Spark working with open source Cassandra.
So if anyone wants to implement for companies, by default, they go with the DataStax Enterprise.
Not really. I mean, there are a lot of companies like Netflix who use free versions.
Okay.
They don't really use DataStax.
Okay, but they have their own engineers to troubleshoot then. Anything happen?
Yeah. So what we'll do, we'll start with SQL SH today, and we get that error. Okay, so you want to debug why your SQL SH is unable to connect. Okay. First of all, node tool status. You're on one of the nodes of the 3-node cluster. You see all the nodes are up and running. Okay. So what you see here is the data center is East DC. You have 3 nodes in that data center. Those 3 nodes, if you see, UN represents they're all up and normal, up normally, they're running. And you can see the other information, but you notice the IP addresses. These are the IP addresses where it is listening. Okay. So each node can have multiple IP addresses. In this case, SQL SH was trying to go to localhost, which is the 127.0.0.1. But Cassandra is not listening on that localhost IP. It is listening with the actual physical IP here, this IP. Okay. So what I do is, there are two ways to connect to SQL SH. One is you can do SQL SH with IP address. Okay. Now that IP address is one of the nodes in your cluster. Or let me just exit. And then you can do SQL SH host name. Okay. What does host name give you? Command. That is your host name, right? Current host. Now, instead of typing the IP address, you can do eternal 3. Right?
Correct.
Okay. So far so good. We need SQL SH to provide one IP address of the cluster node where I can connect, right? But what I generally do always, right? You must have noticed, I use these special quotations here, right?
Correct.
So whatever you put inside, that is going to produce output. Is, say, for example, echo this, or you can say echo ifconfig, or you can do whatever you want here, like, ls minus l. That whatever output was given from that command is produced as a single line output. So what I am doing is SQL SH. In the special ones, I say host name. Okay, now you can put anything here. You can put date. Okay. So it will produce, what it will produce is basically, if you look at echo date, right like this, you see what it did, it replaced that echo date. Today is fun day. Okay, I want to echo something, and you see how my date gets interjected in between, like here.
Correct.
I can also do one more thing. Let me clear screen, right? And then let's say today is fun day. Today is, we will try to, okay. And you see what I did there with the echo command. I'm just putting the date, which is coming from a shell command. And it gets inserted anywhere you put that thing, right?
Yeah.
So same technique I'm using here, SQL SH, and I'm saying in this special quotes, host name. So it connects to the local host. You see the host name is providing this whole string, and then the port, it is by default port number is 9042, and then it connected to the SQL SH.
Yeah.
All good?
Yeah.
Okay. So that was the explanation for SQL SH, how we are connecting to our cluster using SQL SH. Retrieve data using select statement. Okay, so why select statement is so important for us? Like, why there is a special slide for this, and we need to discuss about this. You remember when we were doing our initial discussion about how Cassandra data modeling is, right? We talked about one slide where we say how Cassandra data modeling is, like, based on what. So let me find that slide. So we were trying to install, configure data modeling. See? Okay, so Cassandra data modeling is based on query-driven data model, meaning you, even before you create your table, even before you store data in it, you should know how you are going to retrieve that data. Okay, that makes it very important that you understand select statement. Cassandra select statement is not like any RDBMS select statement. And if you don't do proper select statements, then Cassandra is not a right platform for you, for your application. I mean, when you say you is not a person, is application. Okay. Okay, so Cassandra, so far whatever we learned, right, whatever 12 hours we spent, that's all waste if we don't understand the select statement properly. And select is not like your RDBMS select, so it is very important to understand what we can do and what we cannot do with Cassandra's select statement. Okay. So what we did is in the previous session, we created a few tables, a key space called CAS demo. So that is still here. So you can say describe tables, and then you can see what tables exist inside that particular key space. And what you see here is the 3 tables you have. Select star from, you can do describe employees. We'll use this table. And what you see in this particular table is you have a primary key. So all the entries are grouped using department ID. That is your primary key, right? Employee ID is the clustering column. Remember that concept we talked about? So all the records from the same department are stored together in one partition. Within that partition, based on employee ID, all the records are stored in ascending order. So because department ID is the partition key, okay, all the records which belong to one department are stored in a same partition, one partition, right? It's a partition based on department ID. Within that partition, because of employee ID is a clustering column, all the records, all the employees who work in the department based on employee ID in a ascending order, because we specified that here, it is stored in ascending order. All the records for employees based on employee ID are stored in ascending order.
Yeah.
Okay. That much we understood there. Now, what is important for you to do is you can, for select statement, you can specify which columns you want to see, right? Employee name, employee salary, right? Emp salary, whatever columns you need. That is basic stuff. You need to tell what columns you need from which table, right? Now, remember with Cassandra, you are going to provide the partition key. That is your where clause, okay? Where department ID is our partition key, correct? Let's say, for example, department ID is 100. So this is how you retrieve data from Cassandra using that partition key. You have to provide the partition key. Okay. Now, if you don't provide by default, what Cassandra will try to do is it will try to bring the records and then you can do some paging here. Okay. But if there were 1,000,000 records, this is a very bad query. You're not supposed to do it that way. Okay. Now, what we did here was, you look at this particular query, what we did was select employee name, salary from employees where department ID is 100. That means a specific partition, we are picking up the data. Okay. Let's add one more column to this because I want to know what is the employee ID. So I'll add employee underscore ID column. And you can see in this department by default, this employee ID is stored in ascending order. Now you can do order by EMP ID because it is stored in ascending order. You can ask it to reverse the order while displaying it. You can do this easy. But what you cannot do is, let's say, for example, I want employee name descending order. Because employee name is not a clustering column. Okay. Cassandra will reject the query.
So you mean to say like even we give explicit order by also it won't do?
Correct. So this is where you have to understand what is the limitation and why it is a wrong thing to do. Because in the beginning itself, you discussed, you had meetings, 30 hours of meetings with your app team, said you are not ever going to query the table like this. And then only you went and created the table. Now your app team cannot come and say, hey, we are changing that 30-hour meeting discussion. Then you have to redo your table design.
Okay, got it.
Okay. Yeah. So once we understand that basic stuff, right, we want to go further and see what we can do with this select statement. But look at how many rows are in this table. This is just a very small table, okay? So if you do select count 1 from employees, okay, there are only 106 rows. So it's all good, right? It's a very small table. It's not even suitable for Cassandra as a big table, big data. Okay, first of all, this count statement, is it correct or wrong?
We should not use count, but yeah.
Correct. So even in RDBMS, if you have a million row table, you don't want to count how many rows are there. That's a wrong way to look at the data, because it doesn't matter how many rows are there. There is a table, there is some data. In Cassandra, when you write this query, when the table is small and when it can perform this query, it will do it. But let's say, for example, I have another table here. I'm just going to show you the structure first. I have this USA daily average temperatures table. What it has is, in US, there is a state, city, year. Year is stored as small int. You can see the year itself is stored separately, month, day. What is the average temperature on that day in that city, right? Now understand the partition key here. Partition key is a combination of state and city. In that partition, then you have clustering columns of year, month, and day. Based on that order, it is storing the temperature. Okay. So if you look at this particular table, this is a sensor data table, and this will have lots of rows. Okay. Because, you know, year after year, we are storing day after day, a lot of data in this. So imagine now you have this USA daily average temperatures table. You want to count how many rows are there. As I said, you know, it will look like, okay, the query itself is correct, but what will Cassandra do for that? So it is trying to run, and then it gets a timeout. You see the read timeout. Now remaining message is useless. Okay, it got a read timeout saying I cannot perform this read. You know why? Because you're not using the partition key. You're running a query which I need to go to every single node in the cluster. I have to do a full cluster scan and ask every single node to count how many partitions it is handling. And then in that partitions, if any rows are there, how many rows are there, and then combine all that to give you data, right? Now, Cassandra is a, you know, hyperscale, meaning you can scale the cluster live while the cluster nodes are up and running. You can add new nodes and remove some existing nodes. Meaning, in that kind of distributed environment, you're not supposed to do this kind of queries. So it basic implementation is, okay, by default in 10 seconds it will time out. Okay.
Can you do same thing? Select the count of a partition key column. Can you put it there?
Whatever you do, it is going to time out.
Okay.
That is the behavior. Yeah. That's how it was designed. Okay. So you'll say state, comma, city. That is your partition key. Okay. Now it gives you much larger error because you're trying to count something Cassandra doesn't even understand what you want it to do. It's not even implemented. Look at it that way.
Got it.
Okay. So what we understand here is it is important to query your table with having the partition key in place. Okay. Let's do one thing. Let's just look at the data just to get some feel on how much data is there and what kind of data is there. Okay. So what we can do, limit 5, meaning I don't care which order, which rows you're bringing, just give me the 5 rows, whatever first comes, okay, from the cluster. So it just goes to, a request goes to the cluster, and randomly any node returns 5 rows, it will show that. So limit command is very important, and use it whenever required, okay. So what you see, the data looks like, okay, there is a state, Florida, city is Tampa, St. Petersburg, year 2015, first month, first day, second day, third day, fourth day, and so on. And the average temperature on that day. So that's how the table looks like. All good?
Yep.
Yep. So simple thing now is, let's see what we can do with this select statement. So I'm going to select all columns from this table. Where clause is what we are going to spend a lot of time understanding what we can do, what we cannot do. Okay. Now state is the first column in your partition key. So we'll say state equal to New York. Okay. Remember that data inside the table is case sensitive. Okay. So what it is saying now, you got an error actually. Say state equal to New York. Now remember what is your partition key? State and city.
State and city.
Correct. Combination of state and city. Now there is one more thing. Your developers, what they will do, they'll run this query and they will read carefully. They'll do some internet search. And then you see here, last wording here is use allow filtering. Okay, so they will say, oh, you know what? Cassandra itself is telling me to use allow filtering. So they will put this keyword here. Okay, and then it will run. So what did allow filtering do just now when the developer or anybody who executed this query is, we have to understand as DBS, we have to understand what they did just now is not just full table scan. They're actually saying it's okay. I understand allow filtering will do something, but go do the full cluster scan and show me the data. Okay. So allow filtering is extremely bad. Remember that. Now, I don't know why Cassandra should even suggest using this allow filtering here. That option is there, but we have to know why it is bad. Okay. So let's stop that. I did a Control-C there to stop the output. And let's go back here and understand this message again. So we are giving only a partial partition key, which is only state, but we are supposed to provide the city also. That is the reason it is saying, okay, you know what, you cannot use the partial partition key to filter. You need to provide full partition key. So what is city? Let's say there is a city called Albany. Okay, Albany, just in up. Oh, I'm typing in a wrong place. Albany in uppercase. It says no rows. Okay, because I told you the data inside the table is case sensitive. So what I did here is just put the proper case sensitive entry for Albany, and now it is working. No issue with this, right? Cassandra does not complain because you provided the full partition key, the state and the city for filtering. This is the proper way of doing a select using the partition keys. Okay. All good?
Yeah.
So let's do one small thing here. I'm going to use another window here. So you'll say, for example, I want to run a SQL statement, SQL SH, okay? Connect to host name and then execute command called describe cas demo dot table name is this USA average temperatures table. And then close this and run. So we'll keep this here for reference. And you can see the clustering column year, month, day. That is our order. Okay. So what we can do next is.
So
yeah,
you mean to say like it's a primary key is like 5 columns?
No, partition key is only state and city. That is your primary key column. And then you have 3 columns listed as clustering columns. So within that partition, how data is ordered to store.
Okay. No, this is syntax or we need to mention it like this when we go with clustering fact order.
Well, that is the syntax. You have to provide it that way
okay.
according to your scenario. So year in descending order, that's what I specified. In your case, it could be different order. Month ascending and date is ascending. Now, this is what your app team is saying. This is how we want to store, because that's the high performant result set. We want to take that result set and display it on the web page.
No. Sorry. My question is like in primary key, state and city is the partition key.
Correct.
Right? Okay. So why we are mentioning in the brackets year, month, day?
Because those you're defining them here as clustering columns.
Okay.
And then specifying these are the clustering columns, but order by is ascending, descending order.
Okay.
Okay. That's a 2-portion. So 3 portions, let's say. One is your partition key. Then in that primary key, you're saying, okay, I'm going to use these 3 columns as clustering columns. In the clustering column clause, you're specifying what is the order of those clustering key columns.
Got it.
Okay. So we'll keep this view here so that we can come back and refer to our structure, because I cannot remember the whole structure all the time. What we'll do is we'll run another query.
So one last question.
Mm-hmm.
So can you go to the syntax?
Yeah.
So whatever the clustering order columns you are mentioning here, right? That should be part of the primary key.
Correct.
Okay. Makes sense.
So without specifying day here, you cannot put clustering column day ascending.
Yeah.
Okay.
My doubt is clear.
Yeah. So you need to specify what are your clustering columns, and you need to specify the order of those columns. If you don't specify the order, it becomes ascending order by default. Okay. Okay. So this is the query we were running earlier. We are going to now continue to base our query based on this. Your state and city is always New York and Albany. And then we'll see what else we can do with it, right? Because we have year in our clustering columns, we can do filtering on the year based on year. Okay. So let's say show me only 2014 data. I don't want to see everything. So you can basically, I'm going to just Control C here, but I'm going to go back up and show you the query again. So I added this because year is part of the clustering column. You're able to filter that. Using that, you're able to run a where clause. Okay. That's kind of pretty straightforward. Basically what you're doing here is you're just saying, okay, state is New York, city is Albany, year is so-and-so. And let's say, for example, I want month equal to 4. Okay, let's say, for example, in our structure, if you see, we need to specify year, month, and day. That is the order we have. So can I skip month? Let's say, for example, day is greater than or equal to 30. Can I do this? So it just comes back immediately, says, hey, you know what? You're using day without giving me the month. So give me the month and then you can do filter with day. Easy to understand, right? It's just following that order of what you specified in your create statement. Okay, I want to say 4th month. In that 4th month, give me all the entries where day is either 30 or more, meaning 30 or 31st. Let's say, for example, I'll take that for May. You'll get 2 rows.
Yeah.
So basically what we are saying is whatever you're specifying here in the partition key is not only defining how you're storing data, but you will be able to do where clause, but you have to follow that order. Okay. Let's do some range queries just to give you some idea about how we can do some range queries. Okay. So let's clear screen and I'm going to just get rid of all this until year. Now this syntax is very familiar syntax, nothing new. Year. I want to get 3 years. Okay. 2014 and 2015. And 2013. Let's say 3 different years I want. Okay. So you can just do year in like Oracle. Okay. And then you can do and month equals 5, let's say, or 4, and day is greater than or equal to 28th. Okay, looks clean. It's the same syntax like any in clause. You're just doing a range query. You're just using 3 different values for your year. Okay. Now remember, it is still hitting the same partition. Year, New York and Albany. All the data for New York and Albany is stored in one partition, and you're still hitting the same partition. Okay. So if I challenge you with this, let's say, can you do city in Albany? And let's say, for example, give me one more city, Rochelle. Rochelle.
So Rochelle is in different state?
No, it's in New York.
Okay.
New York State, different city. You cannot, okay, you were able to do it. I was not expecting that. Because you're going across partitions. Remember that part. Okay. What you did with this particular query is, we are actually saying, I'm giving you only a partial state information, but city is, there are 2 different cities, meaning that is 2 different partitions actually. But it is able to work. I don't know why it is supposed to actually not work. So I was...
So we can't give like this California and city, California city, Bridgeport, something, Bridgetown, something, different city?
Correct. You can give, but what I was trying to say is you're not reading single partition here. You're reading multiple partitions.
Okay.
So you have to imagine what is the problem with this query, okay? Because it's going across partitions. Let's do one thing. Let's add our complexity of year in, okay? And let's see what happens. 2000, let me just copy paste from here. I don't want to type this whole thing. Because I'm going to say year is in this range of 3. Okay, so it still works. But remember that now Cassandra, what it does is actually it has to parallelize this query. It has to ask 2 different nodes. Say, you know, do you have Albany information? And there will be another request for Rochelle information. There are 2 different queries, and those 2 queries are running separately. And then when the result comes back, it all gets combined. You remember that read path?
Mm-hmm.
Yeah, that's what it is doing right now.
Okay.
But only thing is you have to identify that you're not going against one partition, but you're going against multiple partitions.
But as long as we are following the standards of the primary key and clustering order, right? It should
Correct.
not matter, right?
So for us, it doesn't matter. Cassandra is going across and distributing that query. So it is able to actually do the distributed query.
Okay, but is it a good way of writing or it's not correct?
No, this one is okay. See, wherever Cassandra complains about it, when you get that red message, say, you know, I cannot do it, that is a bad query by default. So Cassandra will complain if your query you submit, it will complain about something or the other. It will say, hey, you know what, you're not giving me the proper input. So whenever you find that kind of thing, right, don't allow your developer to go and find alternates. Ask him to fix the actual structure. Okay, so what I was saying is, as long as we don't get an error from Cassandra, that means our query syntax is okay. And if at all your developer writes a bad query and then he comes to you and says, hey, you know what, why is this not working? Even though I'm writing a very basic select statement, there is something wrong with the select, the way they're trying to query the table, or they're trying to run a full cluster scan or something like that. Just look at your structure of the table and tell them, you know what, you're not using the partition keys for filtering. So then they can go fix the query. Okay.
Okay. And one more last thing. Can you come to that select query? Where did you
the one we are running here?
Yeah.
Okay. This one is running on a single state, multi-city, and multi-year query.
Okay. can we, in place of select star, can we put the node name also from where it is retrieving?
No,
Something like
that is token information, and you actually want to leave it to Cassandra because you don't know where the data lives, right?
Okay.
Yeah.
Like how we choose a row ID, right? Like that, I thought, can we choose from which cluster it is coming?
There is something called token ID. And I don't even want to tell you about it because the token ID is, we should leave it to Cassandra to manage it.
Okay.
Murmur 3 algorithm. Think of it as internal.
Okay.
So let's say, for example, in Oracle row ID, they have this encoded 64-bit address which tells you which data file, which block, which extent, which block, and which row. That is your row ID actually. So it's an address to the row, right? Now take the same concept and put it in Cassandra. Cassandra is a distributed database. Now you can have 100 nodes, 2 nodes. We don't know how many nodes are there. And then giving you a proper address of where it lives is going to be complicated. If you think of SS tables are immutable, there are multiple SS tables for each data piece, right? So instead of exposing that complexity, they just give you a token ID. But we don't even want to look at the token ID because it looks like a long number. How does it help us, right? If you want to see the token IDs, you can see here, node tool, describe. Hold on 1 second. Not typing on the wrong window. Describe ring. And that will, what does it say? Not to describe ring, key space is missing. Let's say CAS demo. Okay, so you see all this information comes out. So you see this token range. This is the token range. This is the starting number and this is the ending number. And the endpoints are these 2 servers where it is storing data. So you can see information, but how does this help us? Like this token number, right? We don't know where that lives. It is on multiple nodes and multiple copies are kept in multiple nodes. Okay.
Yeah, got it.
Yeah, it just becomes complicated to look at how it is storing data and all.
So, but for my understanding, each, of course, this is the concept. Each row is nothing but one token ID.
Well, no. Token ID is just an address of where that row is.
Yeah, that is what I'm telling.
Correct. Correct. If you think of it as an address, yes, that is the inner concept of the token. Okay. Yeah. So you can do column aliases just like this. I just pasted a query. Look at it for a second. Column aliases are possible. Describe employees because we're using this employees table for some examples. Let's do describe employees. Okay. So you can see employee table is a little bit larger and it has a lot of columns here. Main thing you need to understand is the primary key is department ID. Only department ID is the partition key. In that, employee ID is a clustering column. Okay. Cool.
But it should be another bracket, right?
Correct.
When you are saying.
So only when you have a single column, it doesn't show that optional second brackets.
Okay.
That was the reason I wanted you to look at it closely. Because we are comparing between the previous table has multiple columns, which is the compound partition key, if you remember. Now, what we'll do, this employee table we are using, right? So what we'll do, our regular query. So we'll just say, I'll copy paste one query here. So I don't want to see all the columns, but only few columns. And then let me show you the query itself. So let's look at this query. So this is pretty straightforward, right? Department ID is your partition column and you use that for filtering. We checked that before. Okay. Now in this table, in this partition 50, your employee ID is stored in ascending order. And I told you that you can do descending order also. Like if you need to show in a different order, you can do this query. Let me copy this again. Okay, and then let me show you the query. Query now looks like, previously I was not specifying order by, now I'm specifying order by. Okay, and in Cassandra, this is not a bad query at all. Because your ascending order, descending order, the data is already stored in order. So it just has to reorder it and to give you the data. Okay, so one discussion we had earlier, I will try to repeat that. You are not going to do by name. This will not allow. Because employee name itself is not part of partition, clustering column. Okay, Cassandra will not allow that. So let's try to see what happens if you learned that allow filtering, right? Even with allow filtering, it doesn't allow. Let me explain, right? Your order by employee name. Employee name is not part of clustering column. It's not a clustering column. Okay.
Yes.
Cool.
Yeah.
So we did some more queries with that. And what we'll do next is, let's say you can do partition range scans. Okay. So within a partition, you can do a range scan. Let's say, for example, you have this query we understood so far, right? Where department ID is so and so. And then you remember employee ID is your clustering column. So you can write this. You can say employee ID between 180 and 190. Okay. So you can do a range scan on the clustering columns. Okay, let me iterate it in this way. Okay. First of all, in any query, okay, let me see if I can write on this. Okay. First of all, in any query, you want to make sure you have a primary key or partition key, right? In a where clause, you want to make sure you got partition key, correct?
Mm-hmm.
Then if your developer wants to do some more filtering, let's say any range filtering or any other filter, okay? So any other filters are only possible on clustering columns, correct?
Mm-hmm.
Okay. Then after those two rules are met, then you can have an order by if you want. Okay. Optionally, order by for clustering columns is allowed. All good?
Mm-hmm.
So these are the three rules for your select statement. Whatever you do, you follow these three rules. You say, give me the partition key for the filtering, right? And then do you want to filter more based on the clustering columns and follow their order? Okay, that is also important. You have to follow the order of clustering columns. Order of clustering columns is also considered. Correct?
Yeah.
You know what I mean by that? I'm talking about the order you wrote in the create statement. You said these are my columns in this order. So I'm telling you, if you understand these points with select statement, you are successful with Cassandra. No, none of your developers can come and fool around you.
Okay.
Okay.
So what kind of issues they come to us?
They will never write the queries like you gave them to write. They'll keep on changing these things and keep on telling you, complaining, say, hey, you know what? Basic select statement is not working. Because Cassandra is not designed that way. You have to understand that you cannot write whatever you want.
So for the developers, we need to educate them.
Exactly. So it's part of your job for yourself to make sure they understand how to use it.
Got it.
Okay. So far so good. I haven't talked about anything like lower function, upper function, string function, substrings, nothing, because they don't exist.
Oh,
simple.
Okay.
Okay.
So they don't exist on the partition key also.
No, nowhere. You don't want to do anything more than just getting the partition key. It's only used for retrieving data, right?
Mm-hmm.
I mean, storage wise, there is a lot Cassandra is doing for us. Okay. So we did a pretty good chunk of select statement. Any questions?
No. So have you written somewhere this best practice? Of course, all these are in my mind right now, but have you written any best practices for the like this?
There are many things, many places. DataStack's
Okay.
written this many times.
Okay. Fine.
And the problem with this is you cannot go and read anywhere, because you have to just embed it in your brain that Cassandra, these are the limitations. Over the period of time, you will get it, because that's what you did with Oracle. You practiced a lot, and then you know what is the limitation of Oracle.
Mm-hmm.
And then when developer comes to you, you will immediately say, hey, you know what? You're doing a full table scan. Don't do it.
Yeah.
And then you also know, let's say, first thing they come to you and say, hey, my query is running slow. You will first immediately check indexes. How do you know to check the indexes? Comes with experience.
Yeah.
Same thing with best practices with Cassandra. You keep practicing, you keep talking to your app team. Remember, DBAs were sitting in a closet, not talking to anybody before. In DevOps environment, we are supposed to work like a team. They're supposed to come to us and say, hey, you know what, I need this table. You are going to go back and say, hey, you know what, explain me what you're going to store here and how you're going to run your selects.
Mm-hmm.
Then only I'll give you a table, because you need to understand that Cassandra is not like you create a table and then forget about how you retrieve. One big question I always see is, how do you do your business analytics, like business BI, business intelligence. So obviously you need some standard aggregate functions like min, max, stuff like that, count, stuff like that, right? So what aggregate functions are there and what can we do with them? Let's just do a quick review on that. Okay, so what we'll do, select count from employees. You know this works. I already told you, do not do this on a long, large table. It will actually time out after 10 seconds with a read timeout. So let me do order by average temp. Tell me what is wrong in this query compared to the next query. First keyword itself is telling you what it is. Okay. When you ran a select count on a large table, it will run for 10 seconds and then read timeout. It'll say, you know what, you're not supposed to run this because it is going across the clusters. Okay. In the second case, there is a syntax error with the command itself. That's what it is saying. You're asking for something wrong. I cannot do this. So syntactically, it is wrong. You cannot ask. Even though it looks very doable, in Oracle, you can do this. In Cassandra, you cannot. Okay.
What is wrong here?
Because you're not supposed to do order by like that. You have to do first filter where clause using partition key, filter using clustering columns, then comes the order by.
Oh.
Yeah. Average temp column is also not there. Let me fix that and see what happens. Okay. You get the same thing. There is no difference between these two queries, whether the column exists or not. This is a syntactical error. or semantic error, let's say language error. You're not supposed to do order by.
Okay.
Okay. Because you see here, now you can read a message very properly and it tells you that you're supposed to do the filtering first. Okay. Remember only thing, right? Whenever you run a query, it clearly tells you what it is. First of all, is it a read timeout or is it an invalid request? Okay. Yeah. If at all read timeout happened, why does that happen is because you're asking it to go across the cluster nodes and say, hey, you know what? I understand that you're doing a full table scan, full cluster scan, but just do it, I don't care. So allow filtering. Again, remember this keyword exists, but it is bad. Do not let your developers use it. We'll give it a minute to see what happens.
So if they, can we get, can we put a alert saying that what are the queries they are using and what kind of
you don't need to, because it is written to the debug log. So if you look at your logs folder, in the logs folder, there are a bunch of files here. One is called system log, which is basically just a regular log of what Cassandra is doing. And then there is a GC log, which is, you see this GC log, that is the garbage collector log written by Java. And then you have a debug log. So the debug log will have an entry for these wrongly executed queries. Okay.
Okay.
So we can just look at a tail of the debug log. And you will see, let me see what it was doing. Okay. So debug log is wherever it is doing something big, it will always debug. It will write it in the debug log. Okay. Cassandra was deleting SS table. For some reason it was deleting. I don't care why, but it made that entry saying I'm deleting this. Okay. And also you can see it was flushing some big table, either from memory to disk, or during compaction, it was doing something. So whenever something big happens, it writes it here. And same way in the debug log, you will see this wrongly written queries, like somebody writing allow filtering and all, and not using a statement without where clause. All those wrongly written queries will be logged into the debug log. Okay. And here are your most recent one you wanted to see, right? See, aggregation query without partition key. That was your where clause was missing in the query. And then also it has this timeout. So somebody was executing something and it got a timeout.
So we can't get original query?
Only when query itself is really bad, it also records the query. Then you can actually go back to your app team and say, hey, who is running this query?
Oh, okay.
See, here we were just doing a count, right? Imagine you're actually doing a filter and then you're not doing it with the partition keys, then it will complain about it. I'm missing the key space specification. That's why it is complaining. So I'm going to set up the key space and then I can run it. Remember, you can always run it with the key space specification here, right? But then if your app is having a config file, then they will store this key space only in one location, in one config file location. Okay. So what I did here, can you look at it? It's a very basic thing. Group by. Where department ID equal to 110. Okay. What is the difference here? Okay. So here, first of all, what you don't see is the where clause and the group by functions, right? Group by clauses. So what it did here, department ID, it just picked one department, but it is counting all rows from the table. Remember that count function is giving you all rows from the table. If I do a count of the table without any other columns, it is going to tell you the total count of rows is 106 rows. So just understand that your group by functions are not same as Oracle. They will give you wrong results. Here you might be thinking there are 106 entries in department 110.
Yeah.
This is incorrect.
Exactly.
What it did is it just counted how many rows are there in the whole table, and then it gave you one department ID, whatever it found first. Okay. So group by clause itself does not exist in Cassandra.
Okay.
Okay. So just know where it is wrong and where it works. Okay.
Okay. So, okay. Makes sense.
Makes sense. Yes. So obviously I explained about counting from a larger table. It gives you a timeout. Okay. So you will see two different things, right? You will see warnings and the errors. So this one is a warning. And good thing with SQL, if you properly set it up, you're looking at the proper terminal. Your warnings are yellow color and the errors are in red color. You don't have to do anything special for that. Look at this query. Tell me if everything looks okay. We've been using this table for a long time now, so you should remember the structure.
Yeah, both are the partition key.
So you provided the full partition key. That's why it gave you the proper result.
Yes. Yes. Okay. I don't see any issue.
Yeah, that query is correct actually. That was a trick question. Because you provided the full partition key, it counted how many rows are in that partition properly. Okay. So next question we'll see here. We're just taking employee name and salary where department is 30. Okay. What you want to figure out is what is the minimum salary, maximum salary, and the total sum of the salaries paid to this department. Simple query. And it works. There is no group by requirement because the group by clause itself is missing in Cassandra.
Oh, just now you said like we don't have aggregate functions. We have.
That's why if you look at the slide, there was a interesting way to say there are standard aggregate functions.
Okay.
Not the special ones. Anyway, you can do basic stuff like min, max, and sum. Okay, what happens if you remove the where clause? Let's try that. Looks like it went across the whole cluster looking for everything and then giving you the result. Output contains one warning also along with it. Whether you use SQL SH or use the DataStax Developer Studio, or you use what is that tool we were using, Dev Center, it will provide that warning to the user. Meaning if it is your developer, he'll see the warning. It's about learning whether he takes any action on it and does the queries properly or just goes blind and does whatever he wants. Remember one thing, right? Your application has 5,000 timeouts every day. It's a wrong, something is wrong. You have to seriously go and look at the design and change their where clauses. So it's all about the table design. Remember that slide I was showing you earlier? How do you design your tables for Cassandra? Data modeling is very important. Okay, let's look at one more query. This looks good. All cool. I want to find out minimum maximum of New York, Albany city. For whatever data we have, we can run that. Or we can use extra filtering by doing a where clause and year equals to 2012. What was the min max in 2012? So keep keep doing this again and again and again and put that thing into your brain that your partition key is most important. Then you have clustering columns. In that clustering
And that
columns, you
should
can
be
follow
also in
the order
order.
of clustering columns.
Yeah.
Correct. So we saw the standard aggregate functions. Okay. Now, what if you want to do very complicated stuff like, okay, hourly sales? Tell me how much we sold in the past hour. Not possible. You have to use something else. We'll talk about that later in the advanced topic. Now, like any RDBMS, we also need to check on the system key spaces, system tables, and system related data, right? So let's explore a little bit about system key spaces. So what we'll do again, go back into SQL SH again, right? So if you do describe key spaces, key and tab and fill it, right? You see some system key spaces by default, they exist. So there is a system schema, system distributed, system auth. These are key spaces created by Cassandra and they're maintained by Cassandra. So like sometimes they allow updates, but what we need to understand is what these key spaces are, what we can do with them. Just like any key space, so you can just do use system, and then you can do describe tables, and you can see what tables are there. Now there are a bunch of tables there. What we can do is to understand, we are on a 3-node cluster. We are connected to one of the nodes. We don't know which one, but we are connected to. Now what we can do, we'll use this. Let's use the dev center, just so it is easier to look at when we are querying this data. Remember we downloaded this a while ago, like we were checking the client. So what we can do here, you're specifying where you're connecting local. I already configured that connection. Key space will say system key space. Okay. There are a bunch of tables, but what we'll focus on is a couple of them which we know. So what I'll do is I'll say, okay, I'm connected to one of the nodes in the cluster. So that one you can query by doing select star from system.local. So this is where you're connected right now. Okay. Now, this could be called your coordinator node. Remember the theory from the beginning. Now, what you can see from this is the local and bootstrap completed. You can see the cluster name. What is the CQL version? What is the listen address? What is that IP where I'm connected? And you can see other information like, say, what is the release version and all. So this one tells you which node you're connected to and what is the data center and other information like that. Okay. Similarly, you can, let me just keep this here and then comment it out. Similarly, you want to know what other nodes are there in this cluster. So that will be peers table. So if you query that table, you will see the remaining 2 nodes. Okay. And then you can see all the other information, like what are those nodes running, where are they listening and all that stuff. Okay. So these are a few system tables you might want to look at. Then there are something like, obviously there is a system schema table, system schema key space. Let's say you want to know what tables exist created by the user. So you can run this query, which is select key space name, table name from system underscore schema underscore tables. These are like DB underscore tables, right? Key space name equal to CAS demo. And then you can see in CAS demo key space, there are 3 tables, say EMP, employees, and USA daily average temperatures. Those are the 3 tables. Okay. There are many more key spaces, like you saw this system distributed. There is a system traces. So you can go into each of those key spaces and look at what tables are there. And then by the name, you can actually tell what these prepared statements will tell you. Okay, all the prepared statements are stored in that table. So you can query all of them. There is no restriction because Cassandra is pretty open about what they store in their system tables. Okay, so let's look at some more topics where basically, okay, system key spaces, indexes. Let's talk about these indexes. This is an important topic. In Cassandra, so far we queried a lot of data, right? We've been querying with saying, okay, you need to provide the partition key. Okay. So indexes come with a very big burden on it. And they say these are called secondary indexes. Okay. Why do they call secondary indexes? Is by default, there are indexes for partition keys, which you don't see them. You cannot drop them. You cannot modify them. They're all maintained by Cassandra. But it will allow you to create extra indexes. But you see in the big bold, I'll make it bold and red. Okay. So this is not Oracle. So do not create secondary indexes. These are for very limited use cases. You're not supposed to use them because they are overhead for the system. So let's see what you can do with them, right? For example, our employees table partitioned using department ID. In that partition, the clustering column is employee ID. So if you look at this query, let's say your developers come and say, hey, you know what, I'm going to run these queries nonstop. And system does not allow me to run them, because if you run this right now on SQL SH, you can see it will complain. It will say, you know what, you cannot use that because employee job position is not a column which included in partition key or the clustering columns, right? So you are allowed to create indexes, but remember this red bold text first, okay? So you're allowed to create indexes using a simple syntax, create index, index name, on table, column name. And then what happens is once you create this index, okay, so let me use Cas demo, right? And I will say describe employees. And you can see this table exists, right? This is the create table syntax. When you say describe, it actually prints you that create table syntax on how it was created, okay? Now, what we can do, because your programmer is saying I'm going to run in based on that column he was telling, I created a special index here, index name something, employees, employee job position. On that column, I created an index. Let's do a describe table again. And what happens with the describe table is you'll see that index definition also. Any indexes which get displayed like this are called secondary indexes. And because of overhead, we don't want to use them in our system. Okay, I'll explain why. So now you're able to run this query because there is an index, and Cassandra will use that index to show you that output. But just because it is working, don't create indexes. Okay, let me see how to drop them by just doing drop index name. Now, let us talk about why we create these indexes. Okay. So what happened is that 30-hour meeting, you sat with the people and said, hey, what is your select statement? They told you they will always know the department ID, that is your partition key, and they want order by employee ID. That's what you came up with as the version 1 design of your table. Now, after 2 months of usage, somebody came and said, you know what? Maybe we need to also get the data using employee job position. All good? So meanwhile, while they try to design new stuff, you have this table here. This is the first table, version 1, and you've been using this in your application. Okay. So what you do is, let's go back into our notepad here. And I'm just going to get rid of some of these just by putting ... Okay. And then some of these also are gone. This is your version 1 table. Version 1, being used by application. Okay. Now your developers came and said, you know what, I'm going to do a where clause on employee job position. Select whatever from whatever, right? Employees, where employee job position is, we don't know. We'll provide you that when we run. Okay. So this is our new where clause. So you need to keep this version, but you need to have another table which is designed for this query, because you cannot run this query until you create that index, and index is overhead. So what we do now is we create a table again with all these things will be there, right? But what we'll do is we'll just add other columns. Let's say dot, dot, dot. But your primary key is this instead of something else, right? And then other clustering columns. I'm not specifying what they are. But now you'll say employees by position. Okay. So this is your version 2 table you create. After a lot of discussion, you say, okay, you know what? We'll create version 1 table already exists. We'll create another version 2 table. Okay. And then drop the index on version 1 table, because you don't no longer need that index, second index. Okay. Now what we'll do for here, this is called API 1. Okay. Because your application is using this API to retrieve employees by department. That is this API. So the API 1 is employees by department. Agreed? So your API 1, which existed all these months, your employees table is partitioned by department.
Yes.
But now they came and said, you know what? I need another API, API 2, which will ask for employees by position.
Yes.
So now you have two tables. Okay. You have table 1 and table 2. Okay. In Oracle, you generally don't do this. In Cassandra, it is completely normal. Okay. Now both API 1 and API 2 are valid, and both of them use tables. Both tables are live. Okay. Your insert is performed on both tables from application. You don't worry about how they do it. You just tell them you have to do insert on both tables. Meaning you maintain 2 copies of same table with different partition keys. I know it is not easy to take it, but that's what it is in Cassandra.
Yeah.
Okay. And let me say, let me put it this way. This is completely normal. Okay. Nothing wrong with it. Because this is big data, right? You don't want to normalize. That's what the reason you have multiple versions of the same table, multiple APIs referring to the different table versions, and it is completely normal in Cassandra. Now they can decide not to have the API 1 completely gone, right? They can keep it for overlap of 20 days and then say API 1 is decommissioned. They'll completely not use the API 1 and move everything to API 2. Okay. But inserting data into both tables is application responsibility, not us. Maintaining data in 2 tables is application responsibility. So now we understand why secondary indexes exist. To allow that 20 days transition, people can use that extra column but we are going to drop the secondary index as soon as its job is done. We are not going to keep it there, or we are not going to create multiple indexes just to satisfy some 10 developers. Okay, that is going to be overhead and on whole system. All good? So that's about secondary indexes. So imagine you tell your app team there are no indexes.
No, got it.
I'm just iterating again and again because these are the basic stuff. They think, oh, it's there, right? Create index is there. Why are you not creating it? So you have to push back because of those reasons. I love this particular slide. Anybody in favor of this? There is no explanation.
First you're dropping the index.
I mean, anything, making anything disappear. You just drop.
Okay.
Drop, right?
First of all, our job is also gone.
I mean, you don't drop it without checking first. But that's how you drop. It's as you create it, dropping is much more easy. No syntax explanation required. So I love this slide because this is resetting everything. Okay, let's talk about tunable consistency. We talked about CAP theorem, remember? We said, okay, availability, Cassandra by default does it. Partition tolerance, by default does it. What about consistency? We called it as eventual consistency or tunable consistency. What it means is, basically there are multiple consistencies available, like consistency all, quorum, or 1 or 2 or 3. What do they mean is, basically, there is a lot of text for this if you try to understand. Okay, when you're writing data, you can have one consistency. When you're reading data, you can have a different consistency. What it means is, so basically, let's say, for example, when you're writing, you want all the nodes to acknowledge saying we got your right. Okay. But what does that mean is, if you have 800 nodes, you're expecting one insert statement, all 800 nodes to acknowledge that. Okay. Same way for reads, you have something called read consistency. And you can say, for example, when I'm reading data, give me 2 replicas. Okay. I will set it to 2. That means in a 800 node cluster, if at least 2 of the nodes say, this is your data, then your read is successful. Okay. So your application can have a write setting and a read setting. Based on that, your application can achieve consistency, because you can decide how much consistency you want for your data. That is called tunable consistency. So what you need to do is to read these different available settings like quorum, local quorum, 1, 2, or 3. And then basically there is a website explaining what is this quorum and all that. That will show you what consistency you're using and how to use the consistency level. And if your application is written in Java or Python, they have access to all these consistencies. They will set these consistencies. Okay. So I need to suggest something, because there are a lot of these settings. I would like to suggest saying what you will use in a very good scenario. Okay. What I'll do is, I will say, for example, I will say for red color text. Okay. So I'll define 2 things for read and write. I will put it here. Right. Okay. When you're reading data, I would say at least take 2 nodes reply for your read. Okay. That's a very good setting. Got it? 2 nodes will say, yes, this is the data. 2 nodes will reply saying, this is your data. So 2 nodes are confirming in a very large cluster. Any number of cluster nodes you have, at least 2 nodes will respond to your read. That is a very good data you got back, consistency wise. Or second option for reading, I will use this option, local quorum. What does that mean is, there are 5 nodes. 3 out of the 5 nodes are quorum, meaning half plus 1, right? So half is 2.5 plus 1 is 3 nodes total out of 5 nodes. Local quorum means in the local data center you're connected to, there are 5 nodes. There might be a remote data center which is another 5 nodes. But in your local data center, 3 nodes will give you a consistent view. That's good enough for reading.
Okay. Each quorum means?
Each quorum means you need 3 nodes in each data center to respond to you.
Oh.
Okay. That means you need 6 nodes to respond to you. You have to wait until that consistent data check is done. Okay. Little bit more heavy for reading. Okay. Now there is for write. For writing, I will write to local one, meaning I'll just write 1 copy in the local data center. Okay. Or I can write to 2 nodes in the local data center, to 2 nodes, any 2 nodes, doesn't matter which data center, or 3 nodes. Meaning when you're writing, if I get response from 2 nodes that I received this right, we are good. I think for writing, you never need more than this. Because, you know, if you say, for example, select this for writing, all, meaning you want all 800 nodes to respond to you saying, I got your right. Is that a good design? Instead,
No.
anything like 2 or 3 is good enough. If you have a large cluster, give 3. If you have 5 node cluster, 2 of them is good. You can also use the quorum, or remember, you can also use the any setting for writes. What does any mean is, you're sending a write, any node in the cluster says, I got your right, you're good. I don't like any because I want at least 2 nodes to respond. So again, these consistency levels are set at the application level. You can work with your application team and say, hey, you know what? You don't want to use all because that's putting too much on the query. Every insert will require all nodes to respond if it is a write. If it is a read, then you're asking all nodes to confirm that it's a consistent data. Now, you can use it for banking transactions, but it doesn't mean that you get commit and rollback. That is not what consistency is for. So let's look at this. Okay, so let's say, for example, we have a 5 node cluster. Okay, for writing, so for reading, I'll just put read here for local quorum. Okay, and 2 for writing. This is what I would recommend. So 2 nodes in a 5 node cluster will confirm that they got the writing. And while reading, 3 nodes out of 5 nodes will say, hey, this is your consistent data. It depends on your own environment, on what kind of data you're reading. Are you reading flight tickets, booking data, or you're reading bank transactions? Depending on that, you decide how much consistency you want. That's why it is called tunable.
Yes.
Okay. Tune according to your environment. Okay. So batches. Somebody will come to you and say, you know what, we can do a batch and the entire batch will fail or successful. First thing I will tell you, look at that red text at the end of the slide. First of all, these batches, parts of batches are deprecated some time back. Okay. So you are looking at a begin batch and apply batch. Doesn't mean you're doing commit begin, commit rollback, not that. It's nothing to do with that. Extra burden on coordinator node. Misuse of batches can cause problems. Batches involving multiple nodes are anti-pattern. Whenever you see this anti-pattern, don't do it. Okay. So first of all, batches are not your begin and commit. So it's not for those purposes. Batches exist. Do not use them. Don't let your application team use them. These are like unwanted burden on the coordinator node or any cluster, basically. So here is one slide where, I say don't use them, and just saying they're there. Don't use them. Just know that they're bad.
Yeah,
and you can read a little bit more when you really understand the rest of the Cassandra. Then you can work on why not these things. Okay, so there are some more things here called SQL, user-defined functions, user-defined aggregates. This code can be written in Java or JavaScript. They also support Python, Ruby, Scala via jars, meaning compiled code. These are experimental and not widely used. So when I say experimental, do not put them in production. So what I'll do, I'll exit from here. You remember our configuration file? It was in the YAML folder, Cassandra YAML. Last two lines show enable materialized views true, enable SASE indexes true. Same way, there are this UDFs and other stuff. Okay. So what I'll do here, enable scripted user-defined functions, enable user-defined functions. By default, they're false already. Okay. But you have an option to enable and do not enable them because they're going away or they're experimental. You don't want to have them in your production. If something cannot be implemented in production, don't even enable it in non-prod. All good?
Yeah.
Okay, we are coming to almost to the end. So what we're talking here is how do we secure Cassandra? I'm just showing you options. There is a lot of work to do before we get there. So one is you can use SSL encryption. You can do SSL between client to cluster or node to node between nodes in the cluster. You can use users and role-based access control by using authentication and authorization. You can create users or roles and then grant them permissions and privileges on specific objects, key spaces. Then they can do select, insert, update based on what you granted them to do. But this needs to be enabled, and this can be enabled using these parameters: authenticator, authorization, and role manager. And then you have commands like create, alter, drop, list, role, or you can do grant, revoke permissions. Node tool. We looked at node tool, right? You know node tool status. There are some commands we discussed already. Node tool help will show you the full help of the node tool. Node tool version, node tool status, node tool describe cluster, info. We use some of these commands already. So you know the node tool. Node tool is the DBS best buddy with Cassandra. So that is where you're going to do a lot of stuff like say node tool status, tell me which nodes are down. Node tool version, tell me which version you're running. And describe cluster, it'll tell you what is the cluster ID, what are the different things you need to know about the cluster. And then node tool info command will give you some specific details about that node. You can play with all these commands. Node tool help will show a lot of help. And node tool is the way any DBA will interact with the cluster or with Cassandra. Okay. We use these commands randomly and you know how it looks like. So I'm just mentioning it here. This is what you need to know for administration. One of the good topics, data stacks, drivers, and tools. Obviously you cannot have just database and nothing else, right? You need other things to be there. So DataStax drivers and tools, I'm not talking about DataStax Enterprise, but what does DataStax do? If you go to datastax.com, DataStax is a company which was invented in such a way that they took the open source Cassandra, formed a company, and they write a lot of products depending on that. They have a lot of products here. You can see products are range from Cassandra as a service class, Astra, DataStax Enterprise, Luna as a subscription-based support for open source Cassandra. What we are talking about is not this services, but we are talking about tools, what they created for us, for the Cassandra community. So I'm talking about this tab here, Tools tab. Okay. So you see Ops Center. Ops Center is only for DSC, but you have DataStax Desktop, Studio, Bulk Loader, which loads data in bulk to load data or unload data like ETL. You have Apache Kafka connector, meaning you can use Kafka connector to connect to your Cassandra, do write or read. Dev Center is the tool I was using earlier, like, this is the tool, like SQL Developer. And then they have Graph Loader. You can use this for DSC to load graph data. SQL SH comes with Cassandra. You don't need anything special, but they package it as a separate package you can download. And then it, you just can run only SQL SH on your system, connect to a remote cluster. SQL SH is like a SQL SH, SQL plus. Then there is a Kubernetes operator. So these are all the tools they created for us in the community. They're all free. You can download and use them. Same way, they created a lot of drivers. So like Java driver, your application team will download this driver and connect to your Cassandra cluster, do the operations. Node.js, PHP, Python, Ruby. Now, recently I have published some articles using Python driver. So I can give you a quick run through it. So go to my GitHub, github.com, and then look for a repository called Python Cassandra driver. Now this shows, like if you look at this first one, it shows how to download Cassandra driver, Python driver for Cassandra, how to install it. And also I show you sample code, like if you go back and look at the sample demos, simple demos, like you can see what you're going to write in Python to connect to your cluster. You need to specify the cluster IPs, what is the port you're connecting to, what is the username, passwords, and key space, and then it does basic connection to the cluster. Same way you can write Python code to write some data from the tables, and everything you need for this project is published on GitHub. And you can read through and understand what is the Python code doing. So you can take a look at this, and then let me talk about other things what DataStax does. So this is all like, sales pitch. I'm not going to go too much detail into it. You can read through them. Datastax.com, you can purchase enterprise licenses from them. They have a cloud service called Astra, which is Cassandra as a service. It can run on Google or AWS. You can choose that while purchasing that. They also sell an enterprise version of Cassandra, which comes with Spark, Solar Search, and also it comes with a graph. So you can buy that product. They'll give you 1 year support or 2 year support based on your licensing agreement. Luna is a service. They will support your open source Cassandra, which you're running. Luna is the service name, the subscription you can buy for 1 year. They will support your open source Cassandra. DataStax drivers, I was showing you Java driver or a Python driver. Ops Center is a visualization OEM kind of tool for DSC, DataStax Enterprise. Studio is where you can develop your Cassandra code. Dev Center is a SQL developer kind of tool. Graph Loader is you can load the graph data into Cassandra database. Obviously, you need DSC for this, DataStax Enterprise.
Okay.
In the next slide, I'm going to show you what we should be learning as open source developers. That way we know what tools to use. Okay, these are DSC tools. Think of it as DataStax offering for money. Now, these drivers are all open source, all available for you to download and use, no charge. There is ODBC, JDBC drivers also. Remember this also you can use. This is like your ODBC, JDBC. You can connect to Spark as if it is a ODBC provider using this driver. Then there are community drivers which are not supported by DataStax, but there are a lot of other languages supported by open source. And these are the different community drivers. Again, download and free to use. Nobody is asking you for license costs. Okay, now that we are done with that, let's see what else is here. Okay, so we are coming to almost to the last steps. Okay, so let's understand. Okay, imagine we went through hours of course so far. We talked about a lot of options of what Cassandra does, how to build it. We talked about what we can do with it in terms of data modeling, Cassandra storage. We talked about create tables, how do you put data in. We talked about inserting data or updating data. Both are combined into upsert. And then deleting data. We talked about expiring data, which is with TTL, time to live. We talked about tombstones. We talked about compaction. And we talked about consistency levels. We talked about several ways to query the data. We talked about denormalization. We talked about big data, partitions, distribution, multiple nodes in a cluster, multiple data centers. It is also possible that one of your data center is in AWS, one of the data center in the same cluster is in on-prem servers, one of the data center is in Google Cloud. That is called multi-cloud support. And Cassandra does it like out of the box. You don't have to do anything special. There is a lot more to discuss in administration, and that goes into the next steps. So what I was just reviewing is what we did in this hours. We just introduced, barely scratched the surface of what is Cassandra. Okay.
Only basics?
Yes. Because it's a distributed database, it takes a long time to understand how it is even working, right? So what is our next step is, obviously we have to learn administration. What does it take to monitor your cluster? What are repairs? What are like compaction? How do you do it? What happens if the cluster, one of the nodes fails? Do you delete the node and bring it back into the cluster? Or do you rebuild the cluster? What happens one of the files is missing? How do you recover that? All that comes into administration. Multi-data center clustering is understanding how you can have a cluster running in multi-data center. This is not a big topic because gossiping property file snitch or EC2 multi-region snitch, it will do the job. We already talked about it. We don't have to do anything special. Just build them on your virtual machine so you can know, okay, you have a East data center, West data center, and then physically have servers located there. Then your Cassandra can run on multi-data center without any special settings. Okay. So Cassandra is just an open source product. It's a single database engine. That's it. DSC has other products in it. DataStax Enterprise is the Cassandra you're learning. Plus, it comes with Apache Spark. It comes with Lucene-based Solar Search. It comes with a graph. And it comes with enterprise support for your LDAP users and all. So enterprise security. And they also have support. So you got an issue with your cluster, you call them, they will support, just like Oracle support. I will tell you an interview question for me, especially if I am doing the interview and somebody else is coming in for the job. Okay.
Okay.
I will ask them, do you have experience with open source Cassandra or do you have experience with DataStax? So there will be three different answers, right? One is, yeah, I have open source experience, meaning they struggled a lot to learn it because they learned all these tools on their own. I learned data stacks because data stacks comes as a packaged edition. You're not learning much. And probably with everything you're asking data stacks guys, and they're just doing it for you as a support. Okay. Then the third option is, I know both. Okay. So if somebody says I learned with open source Cassandra, this guy knows a lot more than learning from data stacks. Now with open source, we have a challenge of how do we do our business analytics or business intelligence, and even data loading and unloading, ETL transformation. What if you want to bring data from Oracle or copy data from Cassandra to Oracle? There is something called Spark, and Spark is developed in Scala. So, or you can use Python. I would use Scala because that is much more suitable. This is what I would like to suggest. So learning Scala or Python with Apache Spark is one of the big tasks for a Cassandra DBA. Without this, if you go give an interview, personally, I will not hire you. So there is an interesting project called Elasticsearch. I'm sure you know that. It is called ELK, Elastic Logstash and Kibana. There is a product, or there is a project which is open source, which is combining Cassandra storage and Elasticsearch on top of it. That's a very, very interesting project. I very closely follow it. I have not used it, but I would love to use it. And also, just for our own learning sake, it is always good to learn Kafka, or at least understand how Kafka can be used in our environment. And obviously, we talked about having a combination of Apache Cassandra and Spark. If I'm hiring, I will hire you on day one if you know these two. So we do understand that Spark is very important, and learning Scala or Python along with Spark is really, really important for Cassandra administrators. So just keep that in mind. On the third day, somebody will come to you and say, hey, can you give me how much sale happened in past 1 hour? You cannot do it with Cassandra. You need Spark for that. Okay, you want to see the grand, nice slide? Next one. How many of you are excited? Hope you're not sleeping.
No.
I love this slide.